There we go. That's what I want to see. Okay, 1, 2. AJ, you should be hearing it now. 1, 2, 3, 4, 5. Okay, cool. So that will be the same. Okay, 1, 2. AJ, you should be hearing it now. 1, 2, 3, 4, 5. So, okay, so you need to just go on the outside so that we can check Zoom coming. AJ, you should be hearing it now. Yeah. 1, 2, 3, 4, 5. Okay, so you need to just go on the outside so that we can check.
Okay,
Zoom
I'm talking.
coming.
I'm talking from Zoom. It's AJ talking by Zoom.
Okay.
Can you hear me?
Just
Can you hear me?
change the computer audio to. I can hear
Can you
you,
hear me?
but I just need to change it.
Zoom,
Yeah.
Kaylee, wave at me and smile excitedly. You can hear me. Okay, I'm talking. I'm talking from Zoom. It's AJ talking by Zoom.
Okay, I can hear Prof.
Can you hear me?
Change the computer audio to. I can hear Prof on that.
Can you hear me?
But I just need to change. Yes, I can.
Kaylee, wave at me and smile excitedly. You can hear me. Okay, I'm talking. I'm talking from Zoom. AJ talking by Zoom.
Okay, I can hear Prof. Change the computer audio.
And this is Neville talking on Zoom.
I can hear Prof on that.
Can you hear me?
Yes, I can.
Kaylee, wave at me and smile excitedly.
1, 2.
You can hear me. Okay, I'm talking. I'm talking from Zoom. AJ talking by Zoom.
Okay, I can hear Prof.
And this is Neville talking on Zoom.
I can hear Prof on that.
Can you hear me?
Yes, I can.
Kaylee, wave at me and smile excitedly.
1, 2.
Okay, I'm talking. I'm talking from Zoom. AJ talking by Zoom.
Okay, I can hear Prof.
And this is Neville. Hello, Zoom. Can you hear me? I can't hear Zoom. I can't hear sound on Zoom. Just check. Can you see me smoking?
Yes, I could see you. And I could hear you clearly.
And you can hear me, but I can't hear you talking on Zoom. Why is that? I can't hear you talking on Zoom. Just give me a hand signal that you can hear me. Okay, but I can't hear you. Now, is that because I've done something wrong on my side? This is the Zoom sound I'm trying to hear, baby. No. Let's see if I can figure out what I've done wrong. I've done something wrong on Zoom because I had my YouTube going at the same time. Let me just check my sound. Don't speak. Meeting. You can hear me, right? Give me a hand signal if you can hear me. Yeah, but I can't hear you. Now, why is that? This is on
Can you
Zoom
hear
link.
me?
Oh, yes,
Hello?
yes, now I can hear you, AJ. I can hear you.
I can hear you as well. Kaylee, can you hear me when I talk? She's nodding, so we can all see and hear each other through Zoom.
No, I can't hear them.
I can hear you.
You can hear me and AJ, but I can't hear them in the room.
Kaylee, say something on your side. Say something through one of the microphones.
Yeah, the front microphone would be a good one.
Okay,
To one
then.
of the microphones.
Okay.
Yeah. Yes,
You
sir,
should be
just-
able to hear me better now.
Yes, now I can hear you.
Yeah. Okay. I
Perfect.
am just there's a loop at the moment that's in the venue. We need to make sure
Okay,
that
then.
The microphone.
okay the
Yeah. Yes,
you
sir,
should
just-
be able to hear me better now.
Yes, now I can hear you.
From
There's a loop. Yeah, there's a loop
So the
happening
YouTube
somewhere.
is being
I think
muted
it's a YouTube.
or sending
it's a
audio
YouTube
out
loop.
that's in the venue. We need to make sure
Okay,
that
then.
okay
Yeah. Yes,
you
sir,
should
just-
be able to hear me better now.
Yes, now I can hear you.
From
There's a loop. Yeah, there's a loop
So the
happening
YouTube
somewhere.
is being
I think
muted
it's a YouTube.
or sending
it's a
audio
YouTube
out
loop.
that's in the venue. We need to make sure
Okay.
that
Yeah. Yes,
you
sir,
should
just-
be able to hear me better now.
Yes, now I can hear you.
From
There's a loop. Yeah, there's a loop
So the
happening
YouTube
somewhere.
is being
I think
muted
it's a YouTube.
or sending
it's a
audio
YouTube
out
loop.
that's in the venue. We need to make sure
Okay.
yeah.
Yes, sir, just-
Yes, now I can hear you.
From
There's a loop. Yeah, there's a loop
So the
happening
YouTube
somewhere. I think it's a YouTube.
or sending
it's a
audio
YouTube.
we need to make sure
Yes, now I can hear you. There's a loop. Yeah, there's a loop happening somewhere.
Can you hear me? Is the microphone on? It's on, I can hear it. Okay. Hello.
If you bring that laptop here, can you? Yes. Oh, no, yes, 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 yes. I figured out what the noise was. How's the laptop? So flat, laptop. You don't use power supply can be in and the out and out. The reason being is because yeah, it needs constant power for regulation. Okay, so that is items. That's your main view there. Then I
I
will
need to
do
learn how to change things. Yeah. Are you guys aren't gonna be there with it.
easier to know.
So just sit in when you need to and see how we get for the
I mean-
easier thing out.
Andrew will sort out the item and stuff for you.
Okay, that's what I'm gonna ask. Because, so is this item going back now? So when this end from the item,
But this is the other one. Would you want to keep that one here? In case it comes like
I would say, yes. If it comes and if we need to swap, we wait for it and then we do the swap.
but the camera you're gonna need from.
It's fine, but the camera line running, so
Yeah.
just to practice. Rather than tomorrow morning.
No, no,
Do you want to leave it up?
so all get
Right,
distributed.
you need to test the audio from the in front. Bye. But Ash, you can do that in the morning.
Think this one, you know, it's big, is it?
No, it's not. You must look it out to get item up front.
What do you think of? Okay, okay, this is-
You must give me that one so that we can get item up.
Oh.
So,
Okay, it's very important.
Unless you want to take this one. And just test it in so that we can.
So what the possibilities?
Just testing.
Remember that is-
So the last time. Left and right of the foyer. Let me know when you're ready, Ash. So you just need to send me sound. Just do a click, ting, ting. And we get to headphones now. So that's audio from you.
Sam Cross, knee brace on.
Screen in the stadium. It's kiss cam time. Second largest screen in North America behind the Dallas Cowboys. Oh, she's got the Purell out.
Jamie Roberts from the 2009 tour, but Ryan O'Driscoll's attitude, as soon as he found out that he'd lost his place, was to go
My name is Cabello Vincent Njovu, president of the youth. I'm from Hillbrow. I call it
Now, in that case, I need to.
That's right. Okay, so now let me go to my YouTube channel. Okay, there. Okay, there it is there. Okay. So first I must get the shareable link. That's that one. And then I must go to Heno. Where's Heno? Heno. There we go. Okay, so that's the shareable link. Okay, good. Then I must start this meeting. Let's see, is it, what did the Zoom say? The Zoom said it is live stream, got it. And next I must go to, back to the YouTube, and I must push go live, mustn't I? Somewhere like here, I must say, I must go here, I must go there. Okay. And it should say go live. Baba, you worked yesterday, work today. Yes, it says end stream, which means it's live. That's cool. And it's muted. All right. Good. So now what I'm going to do is I'm going to test this by going outside and checking. Okay, now you say I must change cameras. So that means video. I see my HD camera only here so far. Must I go to video settings?
So you know,
Thank you.
go to video settings,
Yeah.
and then okay, just let's change this thing. Have we got another input? USB.
And that's, yo, how's it? There's one on this side.
Okay.
Let's see what happens. Is there another one? Take up the mouse for now. How's it? How's it?
This last week Friday.
Okay, I've stuck it in there.
Is it, are you winning?
I'll
What's
tell you.
happening
I'll
here?
tell you in a minute. Tell you in 1 minute. I know that I'm live. You can go check the YouTube feed. Same as yesterday, but
Remember to mute.
yes,
on...
I've done that. Yeah, look, it's muted there.
Okay.
Muted there.
Jeez, it looks like a professional setup.
But now I am still trying to find out
video
to video there.
We are live.
video settings.
Video
cool, you're live,
settings.
Neville.
Okay.
Yeah, go to camera.
Camera. Where do you see
challenge is
camera?
also to hear if Neville, if you
Okay.
can hear his voice.
Still only seeing the one
Let's see
camera.
what it-
Okay.
Oh, there he is.
But I think it's just from the laptop.
Yeah,
Just the
no, he's
delay.
going to swap it over to the other camera in a minute. The thing's not yet seeing the camera. Not in nicely. Is it in nicely? Is that HDMI? I can go straight in with HDMI.
No, you can't.
Oh.
That's not a HDMI in, that's HDMI out.
Oh.
Yeah. Just sorry, let me just check again.
We get there.
So what's changing now since yesterday?
They
Just
got
the
a
new
different
camera.
camera. Yeah.
Okay.
Let's just see why we can't see
Oh,
it
that's
here.
the camera that and
So I'm definitely live on YouTube. That's happening. Okay, that's step one.
And do we know that this camera works?
We don't know yet. We're going to figure it out shortly.
Yeah, we know it works because it's on.
Oh, the camera's showing there. Oh, you're showing the flowers. Yes. So we're just going to get the feed into this computer.
Yeah.
Feels like this USB is not so lekker. Yeah. Okay.
I wonder if this is what students feel like when you teach. Not
What?
knowing what's happening. It's a humbling experience.
Okay.
So none of the delegates arrived yet.
Henna's here. He's outside. He needs a chair, at some point. So let's see. Still nothing there. I only see the one camera. Okay, so I paused recording because it's recording on YouTube, so it doesn't really matter.
So that's the default setting that YouTube has.
Yes,
It records it,
yes,
and then it
yes.
becomes available then afterwards
yes,
at any time. Okay,
yes.
that's quite funky.
That's a small for you.
What you looking for?
I'm just looking for my. Just want to test on my computer.
Okay, I'll let you worry about this for a while.
Okay, so I've got a so one of the students is going to sit at the back here, right? So I've got a program here, so we know I've printed for them a program, a physical copy.
One's going to go on.
Yeah, I've got a one here to put in the front. I'm just going to leave one here.
It's remote today and tomorrow.
Okay.
Which is March and
Okay.
So what do you need me to do? Now they have come with USB.
Yeah, the black label.
That's the HDMI. No, it's a cable, almost like this, with the port box. Oh, see. I have a little thing in my hand.
So you were saying, I only asked you on the last minute.
Yeah. Do we know if the camera works?
Still this guy. Never.
Yes, never be. Let's get something else. Simple piece of thing. This is something else that can only go in there.
I know never be is
With that. Upper goes right.
You like that?
No, I'm just changing something quickly. Okay. Okay, so it must be this thing. Why is it not working? You must have got the height somewhere. That's working. Yeah, it's working.
So I think what they have to do is how to explain to one of the students how to switch between the various sources and how can be inset all those various.
No, it's not working.
Yeah, no, I took it out.
Let me know what the issue is. Then let me switch it off. Oh, that's fantastic. Oh, way to go. Brilliant. Okay, he's around for the morning, right?
Yes.
Andrew?
Yeah.
Okay, so you have to train one of the students whose job it is to take all the talks and put them on.
So, what do you need? What do you need? What is
They're
the?
basically going to be projecting the talks from this.
No, the computer's there's going to be a computer in the front which can project the same talk.
Okay, that's part I'm unfamiliar with.
No, it's exactly all you do is switch between the various this computer and that computer via this gadget.
Does Andrew understand that?
Okay, so we need to change that gadget.
That's how it was set up yesterday. So what they did is they switched between that.
Yeah, so they're not here today. So we are here. So I need to figure that out now.
Okay.
What is the output from them that needs to come to meeting?
But it's not beyond your ability to understand.
No.
Clearly, you've done this before. I'm just an academic. Are you also within? Okay. Or you work within us? Okay. So what's going to happen is that the presentation is going to run from that computer in the front. That's where the PowerPoints are going to be loaded.
Yeah.
So they should be able to, by fiddling on the computer, change the slides and so on.
Yeah.
And there is no computer here.
There's where's the one that's going to be set up on that, and when is the parallel?
That's all there.
So I must get another laptop from
All of them project from there.
yeah, but then they can't. How must they change the slides? Yesterday we had another laptop. I'll get another laptop.
He knows.
Yeah, here it is. So we just need another laptop.
No. The testing is good. So what is your?
Okay, so what we done was
What is your laptop? Is it this one here?
where
It's going to the front.
trying to paint the front. There's fiber running from the front. That's all. One of these it's running.
That's this one.
Yeah, it is running.
So I mean, just need to set up the laptop in front so that I can see.
Because that one run to the front and then was one for your.
Yeah, that's now them, which is now have the Zoom link.
Yeah.
I mean, the video. All I need is just the laptop to be plugged in, come to me so I can see it there.
Okay. So you're not going to use the item, you're going to use your.
I'll just mine. And this I give a video feed onto the item. Let's do that. Let me just give a feed onto the item. So you can take this.
We just switch on the other.
That's really for now. Okay, switch all your item on. let me just get your video from my side and then his input. Okay, take it out. And that's video from me.
Okay, so this come from you.
Yeah, but now you need to leave that in.
Oh,
Give him a
you leave
source.
the-
Yeah.
But you can see the
So one is camera, two is Audio check 1, 2, 1, 2. Getting sound? Happiness? One, two, audio check. Okay, so you happy with it? Okay, all good. Mic check 1, 2.
HDMI cable in HDMI slot. The mouth and the mouth of the room. Thank you. And right. Ah, you just need one cover. Okay, good. So that's as simple as that. So this is set up. All you need is power here. So just to be clear, that the speakers load their ports on this computer, right?
Morning, everyone. If anyone has their presentations and would like to bring them to me to load for today so long, you're welcome to. I'll be around.
Oops, hello. If you want to connect to the Wi-Fi, you need to look for the Wi-Fi that's called Wi-Fi. What's it called? Something limited. Wi-Fi access limited now. And it should be open. It's called Wi-Fi support limited. Wi-Fi support limited. Yep.
Do not. You can put it. A bit of a strange angle.
So when you finish then I will see the presentation here.
Yes, and it will be on the screen.
And then you point up.
Fine, remaining.
No, no, it's fine. I can just point using the mouse. And it's- Okay. Thank you.
Someone gave one to me already, so I would leave it on here. Okay.
Is it funny? But what is
I think never. I think it's on the
Hi, good morning, everyone. Can you all hear me? It's 9 o'clock and I think we'll start on time and by the end of the day see how far behind schedule we are. I'm AJ Smith. I'm an academic here at this university. So it's my pleasure to introduce or to have you all and to host you here at this university. It's lovely to see such a large venue almost filled up to capacity. Welcome to Cape Town. I think you came to the right place if you wanted to experience weather. We organized plenty of weather for you over the next few days. The southeasterly, we can guarantee that it's going to be blowing. And there's going to be plenty of weather events to talk about for you. I know that you expected a dean or a politician to welcome you here today, but the winds of change has brought me instead. So welcome everyone. But hopefully by not having politics and the flowery talk of deans at the beginning of our presentations, it actually sets the scene for a very engaging scientific discussion. So I'm very much looking forward to seeing what's going to happen here today. So on behalf of the Dean and the University of the Western Cape, very much welcome to Cape Town. I do want to say a few words about the UWC. I don't know how many of you have been here before. This campus and UWC as a university has existed since 1959, I think. By 1960, we had 166 students, and this year we have 23,000 students. The students are distributed across 7 faculties, and we offer over 200 degree and diploma programs, none of them being anything at all to do with atmosphere or climate scientists. But most of our departments, or most of the academics, or many of them at least, study events and phenomena and aspects of South Africa that are very much linked to climate in South Africa, especially extreme climates and so on, which is where I come in. And it's because of my interest in extreme climates. I'm a marine scientist, not an atmospheric person, but yet all of the marine events that we deal with in the ocean are very much affected by the climate. So within my group, and together with Neville and a group of people internationally, we do study various aspects of the ocean, extreme events as they unfold in the ocean and as they are driven and influenced by atmospheric phenomena. For example, we work on, in Angola, we are experiencing, or we have been told that many of the coastal communities in Angola are being affected by unusually choppy and inaccessible ocean or coastal water conditions called calemas. Myself, my group of students study marine heat waves, and these marine heat waves, often very much driven by atmospheric phenomena in addition to the ocean phenomena, are causing kelp ecosystems to become impacted. Extreme waves and extreme winds are causing coastal communities to have less access to the ocean. So we know definitely from the group of people who harvest kelp that they are year on year less able to access the ocean. The number of available days on the ocean to extract the resources that they need have become much diminished over the last decades. We know about regime shifts, changes in the distribution and abundance and biomass of sardines and anchovy. They now today don't occupy the same geographical environment along our coast as they did 15 years ago. At some point in the middle 2000s, there was a regime shift. Some conditions in the Southern Ocean, in the Southern Ocean and off on the Agulhas Bank changed, and the environment there today is quite different from how it was before. The resources available to people have changed. Again, all of these phenomena have links to our atmosphere and to climate. So I'm very much interested to see what's going to happen today. Aside from being an observer here today, as I said, I'm not an atmospheric person, so I'm not going to present, but I do have something to contribute later on in the week in the session on extreme events. So I'm very much looking forward to engaging with all of you over the next few days and to learn a bit more and to see all the exciting work that's happening in South Africa around atmosphere and climate and so on. So I hope that all of you, I think most of you have been long-standing members of SASAS. New this year, of course, is REACH and ECERA, which respectively look at the societal and health implications of atmosphere and climate, as well as the extreme events of climate. So it's a slightly broader meeting than usual this year. So later on in the week, we'll be joined by people who are specifically interested in those two events. So it's going to be quite an exciting opportunity for us to engage and to talk about climate and atmosphere as it influences the lives and livelihoods, health, and so on of the environment. So again, very much welcome to Cape Town, and I hope you have an amazing time here. Thank you.
Thanks, AJ. Okay, so I'm Neville Swade, for those that don't know me, and I am one of the people on the organizing committee, and I've just got a list of some administrative issues. But before I start, also welcome from me, glad that everybody's arrived. 5 days, as AJ pointed out, the first 2 days are the official SASAS event, followed by 2 workshops on ECERA, ECERA, and REACH. More details about that, but we do have 2 public events on Wednesday, one dealing with El Nino and one dealing with this previous winter that we're just coming out of in the Western Cape rainfall, the winter rainfall region. More of that later. I just want to start by thanking people, because otherwise you won't hear it if some of you leave.
So this event has been months in the planning, and I'm going to start by thanking two people in particular, Jessica Picas or Steinkopf, depending on which email you use. Where are you, Jessica? Yeah, there she is. And Malebo, where are you? Where's Malebo? There she is. Malebo from SASAS. The two of them have been really great. Then there's AJ and Melody from UWC who have been amazing, and Linda van Heerden who's in the department. And then our three students, Kaylee over there, and I think we've got Jesse and Tom outside. Kaylee is the person to give your talk to, okay? So very important that you give your talk to her at least at the tea time or lunchtime prior to your session. And you will present from here, or if you're in the alternate session, which is B, it's in the room just outside here, where it'll be set up from 11 o'clock or from tea time and later. So that's who you need to know, right? Thank you, Kaylee and Tom and Jess. And then thank you very much to SASAS and Heno and others on the committee for helping us put this together as a sort of combined event. Really grateful for it. Okay, a few things. Toilets. One, I think female is here, male through the door. Let's see. Loading talks I've spoken about. Parallel session I've told you about. If you haven't signed the registration form, you must sign it. Okay? Absolutely have to have your signature, so please do that. Your USB has got the program on it, right? In case you wanted to know. And it's a USB-C as well as an old-fashioned USB. Posters are going to go on the walls, either at the back or in the front here. Probably the back is best. And there are pins somewhere to make sure that they are available for the posters. Wi-Fi, in case you haven't heard, look for Wi-Fi support limited. That's open for all of you. And then I have one more announcement, and that's about dinner. Now, we did a survey to check to see who is coming to dinner. If you have filled in that survey, then don't put up your hand. If you filled in the survey, don't put up your hand. If you are coming to dinner, but you didn't fill in the survey, please raise your hand now. 1, 2. Okay, that's good. That's all I needed to know. We'll tell you about transport tomorrow. Good. Otherwise, we are expecting around 55 people for the dinner tomorrow night. And I think, oh, there's one more. There's a Vida coffee shop. In case you need to find one. It's around the corner here, and apparently there's some more coffee even further around the corner. If you move around, you'll find the coffee on the campus, yeah, other than coffee here. Okay, so with that, I have finished my announcements, and I'm going to invite the president of SASAS to come up and deliver the presidential speech. You will talk later. It's there. Okay. There.
Good morning, colleagues, and welcome also from my side. And on behalf of the South African Society of Atmospheric Sciences, to our 37th annual conference. So it's wonderful to see SASAS surging back after the pandemic years. And I think it's going to be a wonderful 2 days. And then we, of course, have the 3 days of workshopping. That's also going to be so interesting to one of us. Let me also start by just thanking from my side everyone who has made this conference possible this year. A big thanks to Neville Sweet, who has just been thanking all the contributors. The Applied Center for Climate and Earth System Studies Access has been really prominent in arranging the event this year. Thank you, Neville. And thank you so much, AJ host. It's really great to be here. I'm not sure how long ago SASAS was last at the University of the Western Cape. I don't think. It may have been very long ago, if ever. So we are very happy to be here. And then from an organizational perspective, you can see all the names there. We had a Medical Research Council. Access is, of course, within the CSIR. The Weather Service, Global Change Institute, and Northwest University have all been contributed to this event. And then the two consortiums that are being formed by Access, ECERA and REACH, they are important. They are really important in the context of this event, and it's focused on extreme events and climate change impacts, as we will jointly explore over the next few days. Let me start by just saying a few words about Mathieu Roux. You'll find that there's a tribute to Mathieu in our conference book this year. Many of you will know Mathieu as one of the previous presidents of this society. He was at every single conference, I think, for the last 20 years. And he has been president for a long time. The constitution, in fact, had to be changed to stop him from being president all the time. He really was fun. He really was fun of being the president. So he also always will retire, so I'm now also doing it to honor him, honor his tradition. So we will really miss Mathieu. As you all know, he was one of our most prominent oceanographers in the country. And we will really miss him this year. That's a picture I took of him last year at the conference. And he was always engaging. The students will know he was always asking questions of each other. But yeah, his legacy will live on. He contributed substantially to our science. And it's a great pity that we have to face climate change without him and without his research contributions. He could have made a bigger difference for the region. We lost him far too early. But please read a beautiful tribute that Professor Willem Landman of Victoria University wrote about Mathieu in the conference. I'd like to share a few thoughts about the theme of this conference, just within the context of what is happening right now in the world. Many of you will have noticed that it was the warmest September ever recorded by humans. That followed on the warmest August ever recorded by humans, which followed on the warmest July and the warmest June ever recorded by humans. But what you can see in this graph, that red line shows where daily temperatures in September of this year were 1.5 degrees Celsius higher than the pre-industrial average temperature for September. So you can see that daily temperatures this year have started to surge above that so-called 1.5 degree threshold of global warming. That's really important. So the so-called 1.5 degrees Celsius world is dawning upon us. And this is just some days exceeding the limit. But the IPCC's assessment in 2021 is that the permanent exceedance of that level is likely going to happen in the early 2030s. So it's now more likely than not that that level will be exceeded permanently. We've left the mitigation process for too long. And as a consequence, I think we can start to say that climate has already become suboptimal for humans. Let me show you a few examples. The first is maybe not directly impacting us right now. I'm talking about the bottom right slide there. This 1.5 degree world that is dawning is bringing a range of things we've never seen in the climate system. So a few of us have just returned from the World Climate Research Program Open Science Conference in Kigali. That graph at the bottom right was quite intensively discussed. It shows Antarctic sea ice concentration. And these were 6 standard deviations lower than the 1979 to 2022 average this past week. It's an anomaly that is statistically not really possible to occur, but it occurs. So the question that has been asked at the conference is if we've entered a brand new regime of sea ice, Antarctic sea ice. And this was not predicted. Nobody expected such an anomaly in the winter of 2023. There are still critical things about the southern hemisphere climate system we don't understand. And then I just want to talk a little bit about extremes in the context of this conference. You will note that attribution studies of attributing events, weather events to climate change are now operational. After the heat waves of June to August this year, several attribution studies were published, and they basically reached the assessment that these heat waves would have been impossible to occur if it was not for the climate change that is already in the system. That is now in terms of their duration and their intensity. They occurred across the European Mediterranean, southern United States, and large parts of Asia. But these types of heat waves have been projected to be part of our future for, I would say, almost 2 decades now. But here's a surprise that happened. In in this year, but in August this year, more than 100 people died in wildfires in Hawaii. And they occurred also during high temperatures, followed a period of drought. Possibly climate change played a role. But what is important in this case is that the Hawaii State Emergency Management Agency made an assessment of the risk that wildfires pose to human life in Hawaii last year. And they assessed that the risk is low. They didn't understand that this type of event can happen in Hawaii. And that is something that I think we should think about during this conference. Increasingly, we are going to face unprecedented impacts from climate anomalies and extreme weather events across the world and also in our own region. The question is, can our community, can SASAS help that these events are not unforeseen as they've been in Hawaii? Here's another example. The Libyan floods killed more than 11,000 people in September this year. It was caused by a weather system that an attribution study has assessed is now 50 times more likely to occur because of climate change. This is the biggest flood disaster in modern memory. Just think about this one. It's 11,000 people gone, literally within a day. Now, what happened in Libya with that flood is very complex. We all know the unstable politics, basically 2 different governments for different parts of the country. In this case, there's some evidence that people did see there is such a thing, but there was zero preparedness. So it's about unprecedented events. It's about making sure they are not unforeseen. It's also making sure about being prepared. And with that, I'll conclude. I think if I look at our own SASAS program, there's a lot of reasons for hope this week. I think SASAS is doing exactly what it should. We are strong in climate dynamics. We have a strong focus on weather forecasting across the timescales. We are strong in the physical science base of climate change. We also have our community here from atmospheric chemistry and air quality. So South Africa is still represented also in SASAS in terms of what we should do in terms of mitigation and lowering our air quality levels. I think the science base that SASAS has traditionally looked after, the physical science base in meteorology and climatology, remains strong. If you read my words as president in the conference booth, you'll see that I am saying there is something that is missing. I don't think we are linking strongly enough in our conference specifically to the climate services community, towards the uptake of our research. I think we should, as a council in SASAS and as a community, think of strengthening that part of the conference for next year. But it's good that the scientific base is on. And I think the 2 workshops will also help us in terms of that important part of uptake of our research. So with that, colleagues, I hope the scene is set. And I wish you a wonderful 2 days. Let's catch up. Let's enjoy our science. Postgraduate students, form your networks, talk to the senior scientists. May it be a wonderful 2 days of interacting with each other on our research. Thank you, colleagues. Back to you, Neville.
First, Keynote addresses from I don't have anything prepared to say, but maybe Francois can help. But I do want to say one thing about him, and he and I share a deep love of jazz, which I think goes very well with the
Right. I can certainly say something academic about Tandu. Colleagues, we all know Tandu Ndagana, who has been a prominent member of the society for more than a decade. But I think Tandu's become so well known in Africa because of his pioneering work on African climate dynamics. And it is a field that over the years have not received the attention that it should. But I think in the last 10 years, Tandu has initially single-handedly starting to build this back. And then he started to build this huge group of strong postgraduate students working with him. So it's one of the most challenging aspects of our field, trying to develop an understanding of processes by looking at the equations. And we thought it appropriate to invite Tandu this year to give us an overview of how he sees the status of dynamic meteorology in Africa and specifically in the Southern African region. What is the status of understanding? Where does he see the main fields, the main lines of investigation in this field? And also, of course, under the highlights from your own research in recent years, as we've also seen in Kigali. So it's a great privilege for us to welcome you to give this keynote address.
Good morning, colleagues. As Francois said, I come from the University of Pretoria and I work with the meteorology group there. And thank you very much, Francois, for the kind introduction and Neville for the kind introduction. And so what I will be talking to you, and thank you to the SASAS conference for inviting me to come and talk about what we are trying to do in atmospheric dynamical research at the University of Victoria. And as I was preparing for this talk, I was thinking about what to present, but we've done quite a bit of work on different weather systems like region highs and so on. But I decided to present on cut-off flow pressure systems as a test case to illustrate the type of things that we are trying to do with our students and collaborators. And the main collaborators, you can see I've outlined them there. And our hardworking students are also mentioned there. So thank you to everyone for contributing to what we are trying to accomplish in this field. All right, so you can't be thinking about dynamic meteorology without being quantitative. So if you don't like math, please forgive me. But if you do like math, you will probably enjoy this, but there isn't all that much mathematics involved. But I mean, if we are going to talk about the power of dynamic meteorology, we've got to talk about its strength, and its strength is the mathematical nature of the subject, which makes it quite powerful, and it enables us to quantify processes that occur in the atmosphere. So maybe the first thing to do is to ask the question, what is dynamic meteorology? I'm sure you've heard if you've never taken the subject at university, you've heard the name dynamic meteorology being bandied about, thrown around, and you ask, well, what is this subject? At a very high level, dynamic meteorology is the study of motions in the atmosphere for the large part, and the large part of it that are associated, those motions are associated with weather and climate, and we are also interested in the forces that bring those motions about. So now, if you are talking about motion and we are talking about forces, we must talk about acceleration, and therefore you have to invoke our old friend Newton's second law of motion, which we know from high school physics. It applies in the atmosphere as well. We introduced this at second year at the University of Victoria and say, well, for an air person, it's pointless to think about the whole thing. Well, you know, it's good to think about the whole of the atmosphere, but when you are doing analysis, you take the atmosphere and break it up into small little pieces we call air parcels. And we look at that as parcel and its behavior, and then we integrate across the atmosphere to get a feel of how the atmosphere works. Now, if you take it air parcel and apply forces to it, like a block of a solid mass, but you know, it would be a block of fluid mass in the atmosphere, and apply a number of forces to them: the pressure gradient force, the Coriolis force, the viscous force, the gravity force. And we find that the net resultant force is non-zero. That if you find that the net resultant force is non-zero, then that FSL will accelerate, and that gives rise to Newton's second law of motion and the conservation of momentum, which we usually call equations of motion. And sometimes we do scaling, comparing the magnitude of the variables. And when you do that, sometimes this term here, which is the acceleration, becomes small enough for you to ignore it and say, and so that these two terms here, I hope you can see my pointer there. Okay, so that these two terms here, these two terms are in approximate balance. I'm just mentioning that amongst many things that I could have mentioned in this equation, because it demonstrates, it's an example of demonstrating the power of dynamic meteorology, because people would tell you that when geopotential heights are close together, then you are going to have high velocity. When they are further apart, you are going to have low velocity. It comes from the expression there, which relates to the of the geopotential heights, for example. Using this equation, you can also deduce how flow is around a cyclone. It is clockwise, as we well know, and it is anti-clockwise. It is anti-clockwise around a high pressure system, and clockwise around a low pressure system, as we well know. This expression here gives us that direction. So dynamic meteorology can actually be applied as we try to do. Not only does the atmosphere need to conserve momentum, it also needs to conserve mass. If you remove a mass of air in the atmosphere, then that mass of air must be replaced by some other mass of air from some other place. And in particular, if you look at that process in the vertical, it can tell us where vertical motion in the atmosphere comes from. We all know how important vertical motion is, especially if you've got moisture at the top. You bring moisture by some process, you run the region high, and you've got vertical motion, voila, you've got rainfall. So you need to have a convergence of that at the surface and divergence of that at the upper air. And this vertical motion that arises there is made possible by the fact that is converged in terms of the continuity equation that we know very well. The interesting thing about this is that this quantity here, which is divergent to zero, is negative, negative then, and positive in the upper end. And it's continuous. There is no singularity. The continuous three-dimensional function. It means that if it's negative here and positive over there, there is a point at which it is zero in the atmosphere, and that point where it is zero means that this term here will be equal to zero, which that means that omega as a function of K will attain its maximum somewhere in the mid-latitude state. This explains why vertical motion is a maximum, not at the surface or at the top of the atmosphere, but somewhere of the troposphere, but somewhere in the middle of the troposphere, the power of dynamic nature. And then the atmosphere also has to conserve energy. Now, this is the so-called thermodynamic equation. But if you want to think about the conservation of energy, you want to do so in combination with the mechanical equation, because this alone doesn't describe how energy is conserved in the atmosphere. Because you've got to conserve energy from one type to another. As we know, energy cannot be created or destroyed. You can only convert it from one type of energy to another. This process explains that. This is just a slide I took from a second-year module I teach at University of Victoria. So we introduced this stuff quite early in our curriculum. So we year in and year out, we teach dynamic. Okay, so there are lots of things that we can talk about the subject of dynamic meteorology, but we don't have 3 years to do that here. We only have 2 hours to think about these things. But the point is that we teach dynamic meteorology year in and year out at the University of Victoria. And unfortunately, we then leave and once degrees have been completed, we find that there is very little effort or there is very little being done in applying dynamic meteorology to the extensive work that we do using synoptic meteorology. So therefore, in our research group, the broad problem statement that we have kind of like defined is that there is a disconnect between what we know about weather systems and dynamic meteorology, which is a powerful tool that can be applied to what we know. So all we are trying to do, it's not complicated. All we are trying to do, we are trying to close that. In other words, we take a well-known weather system, try and understand it from a dynamic meteorology perspective. And therefore, we attempt to quantify processes that are involved in a weather system. Okay, and we focus on synoptic weather systems. So our overall objective, our overall aim is a demonstrated applicability of dynamic meteorology principles to synoptic weather systems in particular. Hopefully, we will see applications of mesoscale dynamic meteorology sometime in the future. I don't know, but at the moment, we are focusing on synoptic meteorology weather systems, which would be large-scale systems that last about a day, and their horizontal scale is about 1,000 kilometers. And so we use dynamic meteorology, therefore, to understand the dynamical processes that underlie or underpin the evolution of weather systems in the South African domain. Our method is equally simple. We use reanalysis data sets. Thank goodness for the availability of reanalysis data sets, but we only can start from 1979 because before 1979, they are very unreliable because satellite data has not been available there. As we know, the southern hemisphere is covered mostly by oceans. So we start from 1979 to current. So usually we have over 40 years of data now, and we develop methods of identifying these weather systems objectively. We've got great programmers like Tolanang sitting over there who develop some of these methodologies of identifying these weather systems objectively. Of course, you can't do this by hand. The data is just too vast because you are talking about 4 times daily times 365 times 40 times. So we are talking about a lot of data, and we implement relative mathematical methods, mathematical diagnostics or dynamic meteorology diagnostics, and apply them to these weather systems. Not all theory is applicable to all systems. So you have to be careful about what diagnostics do you use for which weather system. And then we use what we call composite analysis to flesh out all the common and robust dynamical features and characteristics of South African weather systems. There is some criticism, of course, of composite analysis as a method, but the good thing about it is that it produces robust results that can be transferred from one weather system to another within that category of weather system. So we obtain climatological behavior of weather systems. And then this presentation, then we will look at cutoff flows as a means to illustrate what we want to try and accomplish. Let's start off by demystifying what some people have come to know as a Rossby wave breaking. One was fortunate, I did my PhD at Hopkins looking at this particular issue. I was naively choosing a topic that I thought was interesting, and little did I know that actually a Rossby wave breaking is very fundamental to our understanding of weather systems. Why is it? Because Rossby wave breaking, by definition, of course, it's the irreversible irreversible and rapid deformation of potential vorticity controls, such that they fall back on themselves and then dissipate. You know, so it's a dissipative process by its very nature. It is a dissipative process at the end of a baroclinic life cycle. Every weather system, every synoptic weather system that we see and brings rainfall, you know, like a trough, a cutoff flow in particular, is a process that is involved in baroclinic life cycles. So baroclinic life cycles are more encompassing than looking at the trough or looking at the cutoff flow as a process that's developing as you will see. We know that weather systems develop from baroclinic instability. That is why we call them baroclinic waves, because they develop from baroclinic instability. And baroclinic instability is initiated during cyclogenesis. When cyclogenesis takes place, you are actually transporting heat in the meridional direction at the surface. When you do that, then you are diagnosing what we know in the vertical direction. This framework here is called the Eliasson pump flux. And so at the beginning of a baroclinic life cycle, you will have vertical wave activity flux diagnostics, wave activity flux vertically pointing upward. And later on in the baroclinic life cycle, you will find that these wave activity diagnostics increase in size. And then later on in the evolution of a baroclinic wave, you will find that the heat fluxes are fixed up because your surface cyclone has occluded, as we well know, and momentum fluxes in the upper troposphere take effect and take over. That is when we see a weather system that forecasters know very well, that has a trough axis that is oriented in this manner, with this being the northwest and that being the southwest. We all know this from a synoptic meteorology point of view. And we can see now that actually when a weather system does that, it is transporting momentum from the equatorward side of the from the equatorward side to the poleward side of the in the poleward direction, and therefore depositing that momentum into the jet stream that it is associated with. And sometimes these lows become cutoff lows, as we well know. Now, this process of Rossby wave breaking has been identified in idealized model, and 4 types have been identified here. And that, ladies and gentlemen, then led to a study because these were identified in idealized models, and previously there were climatologists that have looked at this issue in observation. So it's well and good to identify things in idealized models, but do they actually happen in the real atmosphere? In this study, it was shown that actually these 4 different types of Rossby wave breaking occur in the atmosphere. And I highlight here that you can see many of them happening also in the South African domain, which is our area of interest. Note that when you can present them on various isotopic surfaces, sometimes presenting here and you can see that their variability is very similar to that of cutoff lows, suggesting that there might be a relationship between these events and cutoff low pressure systems. And so the other thing that we consider when we are thinking about Rossby wave breaking, it comes in different stages. In the final stage, it breaks off and a closed anomaly forms somewhere in the troposphere. And so on the one hand, this LC1 one type of wave breaking with that closed anomaly. On the other hand, we know very well that what characterizes cutoff lows in the anyway, in fact, what characterizes cutoff lows is that high potential vorticity anomaly, which then induces the cyclonic circulation. That cyclonic circulation happens because we've got that high potential vorticity anomaly, because that potential vorticity anomaly induces the cyclonic circulation. And this is also suggestive that this type of wave breaking might be linked to cutoff flows. Inspired by that idea, then the research question was raised: where does then the closed anomaly come from? Where does it come from? Because it does seem like, because it's an anomaly, it seems like it's alien to the troposphere. So by establishing a relationship between Rossby wave breaking events and cutoff flows, it was shown that actually that high potential vorticity anomaly indicates stratospheric air that is contained in the troposphere by the cutoff flow, so that induction of the cyclonic circulation actually takes place. And we showed in that study that about 89% of these events are associated with wave breaking events. If no wave breaking was found, an intrusion was found, and intrusions are a linear or less severe type of wave breaking. In a later study, a PhD student at UP, Michael Barnes, whom some of you might know, who now works in Australia, showed that 89% is actually 99%. So virtually all cutoff flows are linked to Rossby wave breaking. So it's wise to understand the Rossby wave breaking process because it will help us understand the cutoff flow. Because when you look at Rossby wave breaking, you have an opportunity to think about things from a broader point of view and start with cyclogenesis as a point of departure. Okay, so this relationship is fairly robust, and we can see when this is actually a case study showing the specific event and event to illustrate that it can happen. And then composite analysis brings out all the characteristics that are involved in this. And we show here in the study that in fact, when you are looking at cutoff flows, you will see a jet streak in the latitude and another in latitude and another one in the subtropical region. And this jet streak here has a particular function. Its function is to increase barotropic shear and which propagates across the South Atlantic. It's present barotropic shear and then propagates into. We'll come back to the role of this one, which is very, very interesting in a bit. And then, of course, Michael, in his study, further showed that cutoff flows can extend to the surface. This is a particular, this is an important phenomenon, particularly for the eastern parts, for the coastal regions, because when cutoff flows extend to the surface, they have the ability to induce waves that might cause storm surge and therefore render coastal regions vulnerable. So we are asking the question at the moment with marine scientists and the weather service, how do cutoff flows transfer energy so that waves get energy and are excited, and that's ongoing work there. And so in fact this southward or this downward extension of cutoff flows happens quite often, and in this study he showed that it happens. Michael showed that it happens about 58% of the time. And therefore, this PV anomaly is very important in understanding what's happening with cutoff flows. It is negative in the southern hemisphere, and then it's in the cyclonic circulation that causes the cutoff flow to actually form. So so in the interest of time, we show that it also extends to the surface here. So I'll skip certain aspects because I'm running out of time. I want to get to the point where we show differences between cutoff flows during the summer months and the winter months, and we show that over here the cutoff flows associated with winter months are deeper, and that is caused by the fact that you have a high potential vorticity anomaly that's associated with that. And that high potential vorticity anomaly is a result of the subtropical jet that develops during the winter months, and that and maybe to illustrate that PV anomaly is associated with that with the subtropical jet. We take potential vorticity and that happens, then you can see that the subtropical jet there induces the potential vorticity, shear negative shear potential vorticity that you find them, and indeed you find that negative shear vorticity. And of course, we also have looked issues of energetics that are associated with cutoff flows. And these are very, appear to be showing very different scenarios when there are cutoff flows and when there are no cutoff flows, where there is strong paroclinic conversion when there are cutoff flows and when there are no cutoff flows. And therefore, it would help to think about cutoff flows in the context of paroclinic life cycles. And this gives rise to Cholanang's PhD to try and get to the bottom of the role of what is called the barotropic governor in limiting paroclinic conversion that you find in the South African domain. There is another PhD that looks at dynamical relationship of cutoff flow pressure systems to convention. To conclude, we have a 10-year plan of research here that we are thinking about 5 to 10-year plan. So the first bit will be continuing on what we are doing, looking at atmospheric dynamics, and then the second one will be looking at atmospheric modeling, but focusing on idealized modeling to test hypotheses that are developed in the first part. And then, of course, the last one would be thinking about medium-range predictability using all these things that you think. I'm sorry, I ran out of time. I thought I had 30 minutes. So
Alex, we're only slightly behind time, so I think we can take 1 or 2 questions to Tandu. And then we'll move into our 2 plenary talks. So the floor is open. Please.
I think that one of the impacts would be in early warning systems, yeah? Because we want to think about medium range predictability. And when you are thinking about medium range predictability, you are thinking about early warning systems. And we know that early warning systems are an adaptation technology. So if we can use dynamic meteorology to improve the predictability of these weather systems, I think that we would render them more robust and therefore well service people better in terms of early warning systems. I think that would be the context.
Right, because we have a second question there. Okay?
Second question.
Thanks a lot, Neil. Excellent talk, Tando. Just a question on whether these predictability of the Rossby waves and cutoff flows, if that's already being incorporated into our current set of models that we are utilizing for predicting our current weather systems, not necessarily going forward, just already for the immediate medium range. Is it already included?
Well, yes, definitely. I mean, the first few slides showed you know, momentum equations, continuity of floods, continuity of conservation of energy. That is the basis of models that we use to predict what the atmosphere is going to do next from today. So all weather systems, all processes are already incorporated. But what we want to try and do is to flesh out those details. As it were, we want to do a dynamical processing of things. Baroclinic life cycles are not immediately obvious. You need to have that information in order for you to understand where these weather systems come from. For example, you saw those two scenarios that I unfortunately rushed through because I ran out of time. There is baroclinic conversion that is very strong when there are cut-off flows, and there is baroclinic conversion that is very weak when there are no cut-off flows, you know. And that information is not immediately obvious. It's something that you actually have to diagnose and calculate.
Tanya, and we'll complete with one last question.
Can you hear me? Thank you for your presentation, Prof. I just want to find out, do you undertake any research for the cut-off flows in the causing the deadly floods in KwaZulu-Natal, and what your findings were?
No. Well, yes, an honor student, Becky Makwakwa, is sitting over there. She's looking at, supervised by Solana. She's looking at Ross wave pockets. We call them as precursors of that wave event. And she found that actually the wave pocket that develops there is quite peculiar. It's very different from the climatological wave pockets that Solanangani's MSc has identified. And then the other studies, like I think there is one that came out of Prof. Chris Reason's group, showed that that cut-off flow was quite unusual, and I think as we presented at WRCP, quite at the WRCP conference, it was a cut-off flow. The reason why you've got that closed anomaly, it's a cold core system. Apparently that one became warm core. So it was basically eventually, you know, it evolved into a warm core system, which made it look like a subtropical, a tropical looking system. So it was very peculiar that weather system, and it was associated with very strong influx of moisture associated with a region high and very strong upward motion, because that core had a very strong high peaking anomaly. Stuff that I didn't show here can be used actually to explain some of the dynamics. I hope that answers.
Thank you, Tandu. Colleagues, let's give Prof. Ndakana a final applause, and thank you very much. So in the interest of time, we have to move on in the program, and Ned van Skalkwyk is already heading towards the stage. Colleagues, you will know her as a former winner of the prestigious Stanley Jackson Award. And in recent years, that was for MSc research, but in recent years, she's been working on climatology for dry lands and the relation to convection in South Africa, which is a very important topic, quite a creative research effort we've seen in the past. So that's why we thought we would like you presenting in plenary this morning again.
Good morning, everyone. So yes, before I start talking about dry lines, I would just like to acknowledge my supervisors, Professor Chris Reason and Dr. Ross Blamey there at the back. And then also collaborators with papers that we brought out on the work, Professor Dyson and Monet Gaven from the South African Weather Service, who is not here today. So last year at SASAS, I presented the climatology results of dry lines over Southern Africa. And then we asked the question, so what? So now we have dry lines. We know what more or less happens during a season, but how does that impact convection? And is it an important thing to keep in mind? So I would like to introduce the topic of dry lines by first looking at the satellite image. Often in summer, especially at this time of the year, this is the type of satellite image you would see in the morning of a severe thunderstorm outbreak. This was the 28th of November in 2013 when we had some of the biggest hailstorms, and it was the costliest event over Gauteng. But it started off with a fairly benign looking satellite image like this. And what we are interested in is this moisture boundary that forms when low cloud moves in and moisture comes in contact with very dry air to the west of it. And that is simply put just a moisture boundary or a dry line. And as Professor Nahana showed, with where uplift and so on comes from, if you have very dry air that's being heated up by the sun, then you'll start getting air to rise over here, and that air has to be replaced with the moist air to the east of the dry line. So that starts to be lifted, and then moist air parcels can be lifted to the level of free convection, and that's how dry lines can then end up initiating thunderstorms. And this is an event that we looked at, a six-day event where dry lines occurred consecutively in December 2021. And as you can see on the satellite image, the dry lines form the westernmost boundary of where thunderstorms develop. And in some cases, thunderstorms that developed along the dry line became severe, especially on day 5, where a supercell thunderstorm developed very close to the dry line, and that resulted in wind damage, especially over the southern Free State. So to look at dry line related convection, we used the dry lines data set from our climatology results and lightning data from the South African Weather Service's Lightning Detection Network. We had that available for the periods between 2010 and 2021. And we looked at the 1500 UTC time step for lightning data. Now, let me just show you what the dry lines data set looked like after our climatology. This is for the 1800 UTC time step when dry lines were found to occur most frequently. And this is just a heat map of all the dry lines of 42 years on top of each other. And we can see that dry lines don't really occur frequently in winter, but they occur very frequently in summer, especially during the month of December. And something else that's interesting is how dry lines tend to occur more frequently further west as the season moves on. So dry lines tend to shift further west as summer progresses. And because dry lines occur most frequently over the Western Plateau region, that became our study area for looking at dry line related convection. So this red square we called the Western Plateau, and that's where we studied thunderstorm convection. And at 1500 UTC, that for the Western Plateau, that's the time of day where dry lines or where lightning occurs most frequently. So that's the diurnal frequency of lightning for the Western Plateau region. So at 1500 UTC, most of the lightning occurs. So that's the time step that we use to compare dry lines with lightning. And this is just to illustrate the methodology that we use. All dry lines that passed through this Western Plateau domain were investigated. We drew a buffer around it of 100 kilometers. And then within that buffer, we looked for lightning between 15 and 1600 UTC. We also applied a minimum stroke threshold of 40. So that was a subjective analysis just to see what was significant convection. So we used the minimum stroke threshold. And then once we found that significant convection occurred within that buffer region, then that was classified as a convective dry line. And there is the satellite image of this particular case. So what we found was that dry lines are associated with convection 76% of the time in the Western Plateau area. So the drier western parts of Southern Africa. And we also found that there is, again, the highest frequency of dry lines related with convection occurs during the month of December, and then also quite a prolonged peak into the late summer months, January, February, and then they start to decrease again during March. But as we can expect from the arid western parts of South Africa, even the dry line frequencies are very variable. So huge interannual variability that we see in the second image over here, and even intra-seasonal variability between early summer, October, November, December, and during the late summer months. There is an example, this 2012-13 and 2013-14 season, we had the same number of convective dry lines, 57 convective dry lines, but during 2012-13, October, November, December had the highest frequency of convective dry lines, and then the second summer, it was during the late summer where convective dry lines peaked. We can also look at the variability between the different months. So there is, again, you can see that convective dry lines generally have more than 50% of dry lines turn out to be convective over the Western Plateau. And then we also see that the highest variability occurs during the month of March. And perhaps we'll have some time to look at that. But over the western parts of South Africa, convective dry lines tend to occur with the Kalahari heat low. And so that starts to dissipate during March. And so that could be one of the reasons why we see such high variability towards the late summer months. Then we also drew composites for convective dryline days versus non-convective dryline days for the 12-year period of the study. And what we found was that, as I mentioned earlier, the Kalahari heat low, but the western interior trough tends to be much deeper on convective dryline days than just dry lines that produce no convection. And we also see the tilted trough structure. The ISO lines are at 500 hectopascals, and that's also much deeper trough to the west of the surface trough at 500 hectopascals on convective dryline days. But during the late summer months, we see that the high ridges, the ridging high over the eastern parts of South Africa is stronger. We still see that there's a deeper surface trough than usual. And we don't see that very nice baroclinic trough structure over the west, to the west of the country. But that's also because the atmosphere changes during the course of summer. So during early summer and the post-winter months, this atmosphere is still quite baroclinic, but that becomes more tropical towards late summer. Looking at moisture flux, we also looked at the days leading up to a convective dryline event, and that showed that moisture follows a very interesting pathway before it reaches the Western Plateau region. So let's focus on the convective dryline days during early summer, and then you see quite strong moisture flux going through the river valleys in Southern Africa. That's the Zambezi River Valley, and there's the Limpopo River Valley. So stronger moisture flux in the days leading up to a convective dryline through the Zambezi River Valley. There we can see the anomalies as well, and then that leads to an increase of moisture flux over the Western Plateau region on the day of the convective dryline event. During January, February, and March, this also happens, stronger moisture flux through the river valleys, but now we start seeing moisture also coming through the Limpopo River Valley further south. And that's obvious in the anomalies, especially the day leading up to the convective dryline event, and then leading to an increase in moisture flux over the Western Plateau region during the late summer months. So it shouldn't be a surprise that we see large increases in specific humidity over the Western Plateau on convective dryline days. Over the eastern parts of the Western Plateau study domain during early summer, and then over much of the study domain during the late summer months. So that enabled us to create a conceptual model of what a convective dryline day looks like on average. You can expect a deeper surface trough or Kalahari heat low over the western interior with a sharp upper air trough to the west, and then the anomalous moisture flux traveling through the Zambezi River Valley in the days leading up to the convective dryline event. That results in very tight moisture gradients over the Western Plateau region And that blue area indicates where thunderstorms are expected to develop. And then during the late summer months, also just the deeper surface trough, but now moisture traveling mainly through the Limpopo River Valley, also enhanced by the Mozambique Channel trough that's to the west of Madagascar, and then thunderstorms developing over a larger area in the Western Plateau. So now we are looking at a comparison of the ratio of convective dryline days lightning with the total amount of lightning, just to see how big an influence convective drylines have on the amount of convection that takes place in the Western Plateau. So for the early summer months, that's the region that receives the highest frequency of convective drylines. And we see a very large ratio of lightning over the southwest of Botswana is associated with convective drylines. So that's almost up to 80% of lightning in the southwest of Botswana, and then also over there on the border area of the Northern Cape Northwest. And during the late summer months, when we have significantly more convective activity over the western parts of South Africa, we also see that the lightning activity due to convective drylines or unconvective dryline days also shift further west. And I want to now emphasize this area where we have the highest frequency of convective drylines. It has shifted west, as we saw with the climatology also happening with drylines. And now also above 50% over a large area of the Western Plateau that's associated with lightning that also occurred on convective dryline days. But if we keep focusing on this region here, when I show you the next slide, just looking at January, February, March again, you'll see that just to the east of that area where we have the highest frequency of drylines during January, February, March, that's also where we see the largest number of Cape days exceeding 1,000 joules per kilogram. So this is the number of days exceeding Cape, where Cape exceeds 1,000 joules per kilogram on convective dryline days. So that really increases to the east of where convective drylines occur most frequently. And Cape days exceeding 1,000 joules per kilogram, much less during the early summer months. And this is just showing you the anomalies of between Cape days on convective dryline days and non-convective. So we see large increases in Cape on convective dryline days, both during the early summer months and also during the late summer months. So I'm coming to one of the last slides where we looked at lapse rates, because just to try and understand the mechanism behind what causes the convection and what causes the increases of Cape on convective dryline days. So these are lapse rates in the lower levels between 850 and 700, and then in the mid levels between 7 and 500. And that's just for the entire layer between 850 and 500. So if we just look at the last image during October, November, December, we see an increase in lapse rates on convective dryline days. If we break it down between the low levels and the mid levels, we see that the largest contribution comes from the mid levels. So most likely the sharp upper air troughs and cooling associated with their passage results in steepened lapse rates. But then at the surface or in the lower levels, we have decrease in lapse rates on convective dryline days. The same occurs during January, February, and March. We will also see a decrease of lapse rates over the eastern parts of the Western Plateau, but in the mid-levels, increased lapse rates. And looking at the convective inhibition for convective dryline days, it's also interesting to see that together with those lower lapse rates in the low levels, we see increased SIN on convective dryline days. So just by looking at reanalysis data and not really studying T5 yet, it appears that to the east of the dry line, there might be a surface inversion that forms that inhibits convection during the early morning hours, and that allows Cape to build. So that's possibly why we are seeing higher Cape values on convective dryline days to the east of dry lines. And then as soon as the SIN is eroded, then explosive development can take place in some cases, or just convection takes place. But that SIN pattern was not the same during January, February, March. And that's also when we saw much higher Cape values over the Western Plateau area. So a few of our conclusions: lightning data was really a very nice way to identify convection for this study. And dry lines are important triggering mechanisms for thunderstorms over the drier western parts of South Africa. Dry line locations are extremely sensitive to moisture variations, both during early and late summer, but also interannually. And moisture pathways shift during the course of summer from the Zambezi River Valley during early summer towards the Limpopo River Valley during late summer. Convection over southwestern Botswana during the early summer months is mostly dry line related. And a deeper interior trough on convective dryline days allows a stronger westward flux of moisture towards the dry line. This increases the low level stability that allows scape to build during the course of the morning and before thunderstorm and convection begins.
Colleagues, we have time for one or two questions. Thunder?
Hello, thank you very much for a very interesting presentation. I just want to ask a quick question about the role of the trough that you see on your left-hand schematic in terms of the determination intensity, in terms of intensity determination. Because when you look at that, you might have a jet streak there, and we have the partial circulation there. We talk about that, the role of the jet streak associated with the trough in inducing more determination. Where you
Sandro, are you referring to the composite of convective dryline days? We haven't really investigated the nature of the jet at this stage. What we've just seen that there is definitely an enhanced moisture airflow through the low-level jets that come through the river valleys. And yeah, so that's where we are at this point in time.
Last question, Mr. Stefan.
Right. Sorry. Do you see any relationship between dry lines and tropical temperate troughs and or cutting blows and or frontal systems?
Well, there has been earlier work done that does show that there might be a relationship between tropical temperate troughs, especially the first day of the first days of the onset of these cloud bands, but we haven't looked at that.
Unfortunately, yeah, because of time, colleagues, we have to move on. So our next presenter is from the South African Weather Service, Christine Engelbrecht. We've all seen the heat waves in the Northern Hemisphere over the past summer, and I think many of us are wondering what's going to happen this coming summer. That will be discussed, I think, on Wednesday. But this talk by Christine is on the spatial structure of heat waves in Southern Africa.
Thanks very much. Okay, as mentioned, today's talk is on heat waves. Heat waves has been the top topic of presentations quite a few times over the last few years, and some papers is coming out on specific events on on heat wave events over Southern Africa. Yeah, but those are usually really the high impact heat wave events that we really read about. So what is being done here by myself and one of my colleagues at the South African Weather Service is to look at by using the definition of heat waves as and that is the same definition of when you hear about on the short term, like let's say, for example, the heat wave conditions we had last week over the Gauteng areas and surrounding areas, where the definition for that is used for public weather forecast is what is being applied here. Okay, so what does that definition? How does that definition works? So first of all, based on a 30-year climatology, the month with the highest maximum temperature are used for a specific location. In this case here, we've used a gridded temperature data set of maximum temperatures. What you see there is in the blocks or the numbers is indicating the month when the highest average maximum temperature occurs. Then the shading is giving you an idea of the temperature of that specific average maximum temperature. So let's say, for example, in the Pretoria area, it's that lightish between green and yellowish color. So let's say more or less somewhere between 28 and 29 degrees Celsius. And if you apply the heat wave definition that is being used here, the temperature must exceed the specific maximum temperature threshold for at least or by 5 degrees for at least 3 consecutive days. So yeah, so over the western interior parts of the country, where you can see some of those average maximum temperatures is above 35 degrees, you know, exceeding then, like say, 41 degrees for at least 3 consecutive days, it's really becoming hot. Again, then of course, some of the coastal regions, that temperature threshold is somewhat lower compared to the interior regions. You will also see there that for most months, or for large parts of the country, well, maybe you can't see this, so I must tell you, the months during which this average maximum temperature occurs is mostly during the month of January. Okay, so yeah, over most parts of the eastern parts of the country, the month of January, also for the western interior, then over the far western parts of the country, the month of February, some of the coastal regions along the south and southeastern coast, also the month of February, also along the Namibian coast, and then the month of December over places like even the month of November in some of the northern parts of Botswana, December the western parts of Botswana. So it varies quite a lot over the southern African region, and that is then also as a result, as how Lynette has very nicely described about the differences in seasonality and the weather systems that makes an impact. Okay, so when it comes to as mentioned earlier on, the definition of a heat wave takes into account the duration of the exceedance of a temperature threshold. So on this image here, this is the PDF of the 558 heat wave events as per that definition that has been identified over a full calendar year for a 44-year period, 1979 up till 2022. So there you can see that the absolute overwhelming majority of heat waves is has a length of less than 5 days. So let's refer to them just as the shorter kind of heat wave events in terms of duration. But then you can see along the x-axis, you can still see about some heat waves that it can occur up to about 20 days. And then the longest heat wave actually, and that was during a 2015-16 period, during December, January, had a duration of 28 days. Okay, that's not specifically on a specific spot the whole time. Heat waves are very dynamic. They change. They can start in one place, then as the evolution of the heat wave, the area covered by the heat wave can expand and it can actually move. It's really a very dynamic weather phenomenon. In terms of the coverage, this is now for the same data set of heat waves. And this is now the fraction. So yeah, the percentage of grid points south of 20 degrees south only over land for that 558 heat wave events. So there again, yeah, that large or the highest bar on the x-axis, that is more or less for heat waves, actually less than that covers an area of less than 1% of this region south of 20 degrees south. Then let's say for heat waves, let's say more between let's say 3 and 5% of spatial coverage. Also quite a decent amount of heat waves is also captured in that that first long bar. Then heat waves of, let's say, that covers between 5 and 10% of the region south of 20 degrees south is actually also actually quite devastating heat waves in terms of its impact on agriculture. So just imagine some of the heat waves, as you can see there, you can clearly see there that there are heat waves in excess of 20% aerial coverage. Actually, you can see just beyond the 40% value there on the x-axis. There are quite a few, I think it was about 12 heat wave events of about a 30% aerial coverage. And then difficult to see, except if you really got very, very good eyes, around more or less at around about the 70% on the x-axis, yeah, is one during the 2015-16 season, during early January, on one day, 70% of the Southern African region actually, yeah, qualified as being impacted by a heat wave event, or a heat wave day occurred during that specific heat wave event. Yeah, that is something I must have mentioned here. This is actually the maximum spatial extent during a specific heat wave event. Okay, so important question. We just think of heat waves in terms of a feature that occurs during the summer months. So just to try and quantify it, yeah, and again, the focus in this study is very much on the spatial extent of heat waves. So the blue bars is where no restriction on the spatial extent is put upon. Then the orange bars is for heat wave or during a heat wave event that at least one day must have had a greater than 8% spatial coverage for the area south of 20 degrees south, and then similarly, but for 20%, the green bars. So first of all, to note this, is that heat waves occur throughout the year, but as we all know, summer months, the highest frequency of heat waves. When it comes to the spatial coverage, yeah, from the month of September, we can start to see, let's call it the larger kind of heat wave events, and then the really extreme kind of heat wave events in terms of the spatial coverage, and therefore also a higher likelihood to impact the health sector, you know, the frail people, agriculture, and so on, is really starting from October to February. And for all of these different spatial extent criteria, the month of January is really an important month in terms of when we can expect these kind of yeah, the highest frequency of heat waves. Sorry. But just to mention here, or to show maybe, is that the month of January, December, and February, really important months in terms of heat wave frequencies. Okay. Okay, so let's just going to show one or two things here. Just want to see where my timer is. Yes, I think this time really going very slow. Sorry? How many minutes? 7 minutes left. Something's wrong with this watch. So, anyway, okay, I guess I need to pick up speed then. Okay, so this year is starting in the month of June. This is June, July, August, September, October, November, December. Oh, so you can't see it. Oh, sorry. Okay, so the top left-hand image there is for the month of June. The end of that row is for the month of September. So you remember there that larger than 8% spatial coverage kind of heatwave events in terms of the frequency starts to pop out in the month of September. So this is the region where it occurs. Yeah, over the eastern parts of the country. Then, as the summer kicks in, the spatial coverage, and I must say, this is now the long-term mean monthly, and this is now heatwave days, but not heatwave events, but days within the heatwave events. By January, on the middle row, on the far right, is then the spatial occurrence where one can see the frequency of occurrence of the heatwave days. So there you can see the month of January is really, really an important month. But then just something else to highlight. If we go back to the top row, along the southern Namibian coast, there you can see the two middle figures, the reddish blocks there. So that is then during the winter months where we can where observed heat wave events has been observed. And then again, if we go to the bottom row, let me just make sure, that the last two images there is all for April and May, and there you can really see again that western coast of Namibia into the northern part of the west coast of South Africa, and maybe not very clear for you, but also along the southern and southeastern coastal regions of the Southern African region. So we do get winter heat waves, and that is also actually very important areas, something we tend to forget. And that usually is associated with bergwind conditions, to which we can link specific circulation patterns for those kind of events. And that is then also usually when we do have our higher risk of forest fires in those regions. Okay, so now, and on this slide, what is shown here is what is called the heatwave cumulative area. So this is adapted from a paper where heat waves in the UK were analyzed. So just thought to repeat it here. So this is then for every single heat wave day during a heat wave event, the number of grid points are added, and then actually in that paper on the UK heat waves, it's converted to the square kilometer area for their purposes. Here I didn't do that specifically. Okay, so why am I showing this? Again, difficult to see here, but you just need to believe me that on the x-axis far to the right, between 4,000 and 5,000 is where this heatwave cumulative area index of that specific heatwave during the 2015-16 season, what that added up to. So compared to the rest of the 558 heat waves within this database, that was really quite an extreme event in terms of spatial coverage of heat waves. They are actually, difficult to see here, but quite a few heat waves that occurred. Oh, sorry, you can't see there. Okay, sorry, ignore that. Okay, So back to winter heat waves, and if we remember now the previous graph on the heat wave cumulative area, so that's most of that heat waves occurs during summer. In fact, only 13% of the heat wave events in this database occurs during the months of May, June, July, and August, the winter months in this study. So yeah, you can see this this HWCA index for the 73 heat wave events that occur during winter, very, very small compared to, yeah, most of the values here when the whole database is considered. So just showing you an idea of then also of the spatial extent of the winter heat waves versus the ones that occurs during the summer months. But that is to be expected. Okay, so in terms of the duration of winter heat waves, most of them 3 or 4 days. Then there are a few outliers. The highest one I think was about 10 days. And about 8 or 10 days. In terms of the spatial coverage, here you can see it's not even 2% of the spatial coverage, or the maximum spatial coverage during each of those 73 winter heat wave events. So they're really small, and they're mostly confined to, let's say, the western parts or the western escarpment areas, or the southern parts of the southern escarpment areas of the country. Okay, so now before concluding, a few maps now is going to be flighted where for the specific spatial extent criteria. So just to show where's the highest frequency for the specific spatial extent criteria occurs. So for heat waves that covers areas of less than 1% for the region south of 20 degrees south. Yeah, I hope you can see the colors there, but the lighter green of shade, the higher the frequency of occurrence. Okay, so there are, again here along the west coast, this is by far where these very small heat wave events in terms of the spatial coverage has by far the highest frequency of occurrence, showing us it can be an extremely local phenomenon. So heat waves aren't just, if we apply the heat wave definition, then it can really be a very, very local phenomenon, as one can see here along the Namibian west coast. So, and this is now for heat wave events between 3 and 5% of aerial coverage. Then we can see that the highest frequency of these kind of heat wave events in terms of their spatial coverage is focused here in the Limpopo Valley kind of region, the far northeastern parts of the country. Okay, and then a little bit of a hotspot here over some of the eastern higher ground regions as well. And also here, sorry, you can't see it, over the northern parts of the Western Cape's western half. Okay, so now this is now quite serious heat waves actually, between 5 and 10% spatial coverage. Again, that northeastern corner of the country, really an area where this kind of spatial coverage occurs the most frequent. Then if we look between 10 and 50% of coverage south of 20 degrees south, and this is now actually really, it doesn't sound like much, 10 to 15% of spatial coverage. But for a farmer there, with his maize, and such events strike, this can be really terrible. So, and now we can see that these kind of heat wave events, or heat wave events with a day of, let's say, 10 to 15% of spatial coverage for this specific domain used here, Yeah, there over the western part of the maize producing regions is where this occurs most frequent. Then this map is for 15 to 20% spatial coverage. Still, some of those western maize producing regions really having quite a high frequency relative to the remainder of the country. And that still continues for 20 to 30% spatial coverage. I'm actually neglecting the remainder of the country now, but so for some of the, that's just where the hot spot is in terms of this kind of spatial coverage. But it occurs over most of the eastern part of the country. During this, let's say, 44-year period, it occurred, let's say, in the Bloemfontein region about 7 times. So for comparative purposes, further westwards over the Northern Cape regions, there it is relatively lower compared to these central parts of the country. And then also relatively lower here over, obviously, along the coastal regions, and also the areas east of the escarpment over the eastern part of the country. So for the agricultural sector, they really, if one will, as planned, as part of this ongoing work to create the risk map, the maize producing regions is really within an area where the risk of these kind of very large scale heat wave events stay in that kind of hotspot. Okay, and this larger than 30% coverage, there were how many heat wave events now? I think it was about 6 of, yeah. Oh, actually, I can see. Yeah, I think it is 6. I think the highest number was 6 over this 44-year period. And a large contribution occurred during the 2015-16 season for this specific category of the spatial extent of heat waves. And again, the central part of the country, and specifically that really agricultural important parts of the country is where the risk is the highest. Then to end, don't have a top 20, my top 20 song list I will not share to you. Most of you will not enjoy that. But here's the top 20 heat wave events during the 1979 to 2022 period. So on the top, number 20, here on the bottom, number 1. So, and here, the date that is given here is the date with the largest spatial extent for that specific heat wave event. So the day during this 44-year period with the largest spatial heat wave extent of the country was the 5th of January 2016. That is also a day when Pretoria recorded its highest maximum temperature of just above 42 degrees Celsius. Then in number 19, during 2018, and here on the far right-hand side, it's indicative of the state of the phase of ENSO and also the strength. Then just to show you that the 1982-83 El Nino event comes in at number 5 in terms of the spatial extent. Yeah, but also to note, important, in this top 20 list are also quite a few neutral years. So, yeah, it's 1, 2, 3, 4 neutral years. That's in the top 20 in terms of the spatial extent of heat wave events. And also, as far back as 1981. So it's not just, even though the 2015-16 season was really exceptional, yeah, it's not just during that season. Yeah, 40 years ago, we did have also very, really extreme heat wave events with a very negative impact. Okay, so just to conclude, in this heatwave climatology, no restrictions were imposed in terms of the months considered. Every single day during the 1979 up to 2022, actually it's extended a little bit of, into 2023, but that was not considered for most of those climatological related kind of maps that were shown. Okay, then the months of January, December, and February, the months with the highest frequency of heat waves, with January being the most important month. Then 13% of the total heat waves in this analysis occurred during the winter months, May, June, July, August. In terms of the spatial extent, definitely over the majority of heatwave events, in terms of the spatial coverage, is less than 5% of the area south of 20 degrees south. Then there are some hotspot areas in terms of heatwave events along the west coast of Namibia, the southern parts, and then also the western maize producing region of the country, which I think is really important for us. And then just for comparative purposes, in terms of the top heatwave events, January 2016, December 2018, October 2016, January 2018, and January 1983, the top 5 heatwave events in terms of the spatial coverage. Thanks very much.
Thanks, Alex. We have time for one very quick question, and then we'll go to coffee. Yes. Yes.
Fascinating presentation. I do a lot of analysis on marine heat waves, so heat waves in the ocean. And I note that your definition of how it's applied to the atmosphere and atmospheric process is very different from how we use it in the ocean. But that's not what I want to ask you about. It's I would like to know, typically when we do a heat wave analysis, we also look at the historical trends or change in the intensity, frequency, duration, and so on of heat waves. Can you comment on how heat waves are responding in terms of increasing or decreasing in intensity, frequency, duration, and so on in the atmosphere in the context of your presentation today?
I didn't include a trend analysis in here. The data set used here has various or changes in the number of weather stations that was used to construct it. So, but what I do see is obviously a higher frequency of, let's say, heatwave events over the past 10 years compared to previous 10-year periods. Yeah, the intensity in terms of the spatial extent, even though as shown in this, let's say, top 20, some of the heatwave events in the beginning or the start of this study period is also occurring in this top 20 list. But I must say, yeah, it does seem that the frequency of, let's say, the larger scale events is occurring more frequently. But it looks like it. And in terms of the intensity, actually, I didn't show any of it here, but the temperature anomalies was also looked at. And for some of these events over the last few years, the temperature anomaly that average over the duration of the heat wave event seems to be a little bit higher compared to in the beginning of the period. But as said, this specific data set is not suited really for trend analysis. So I'm not even showing that. So that is said a little bit in quotations. Don't want to be, don't want to say that in a formal manner with a specific data set.
Thanks, Steve. So, colleagues, Neville will now make an announcement in terms of slightly adjusted time for coffee and how the parallel sessions will work.
Yeah, So we'll bite a little bit into the program. So we'll go for 20 minutes for tea now. So we'll try and get back here by 10 past 11. Listen for the bell. And then those that are in the room next door, that's the B session, must go and find Tom and Kaylee at the back to load your talks, and the others need to load their talk here for the session after tea. So you go straight into your parallel sessions after tea. Okay, good. So let's go have tea. Thanks.
Hey, my name is no, you'll never get yours. It's so too small. Yeah. Yes.
How are you? Yeah. It's mine. But no, no, no. Mine is the one I just gave you. I can tell you what, it's an Indian humor. He's saving you. He's saving you. He's saving you. Oh, can I put it on your phone? Can I send mine by email?
Mic check, testing 2. Testing 1, 2, mic check. 1, 2, testing, mic check. 1, 2. Mic check, 1, 2. 1, 2. Testing 1, 2. Mic check, 1, 2. Testing 1, 2, mic check. Mic check, 1, 2. Sounds okay.
I've been giving a lot of views here, so I just want to make sure it's this one. I did load it. I did this one. Ah, thanks.
Oh, no. No. No.
What is your plan now?
You just unplugged.
Now to the seasonal time scale, one of the most important things is in agricultural applications. Most of the time we'll present our seasonal forecast as being above normal, normal, or below normal. But most of the time you find that doesn't translate to significance to the farmers, because whether it's above normal or below normal or normal here, it doesn't necessarily mean they will have a good agricultural yield at the end. So what the whole idea is to at the end say, if we can
we can actually look at the subseasonal systems, seasonal systems like the Mozambique Channel trough, and you look at those and you combine them with the seasonal position of the ITCZ. Perhaps we can somehow come up with a correlation where we can actually use, I don't know why it keeps doing that, but maybe I should just keep speaking. And then it will give me a chance to, I don't know. Technically, I'm quite limited. Can I drink this water? It's for me. Yes. It's for me or who's it? Oh, thank you. I hope you have recorded that I lost 5 minutes. So that why did we look at the ITCZ? ITCZ is simply a convergence of the trade winds that leads to intense precipitation. So why do we want this ITCZ? Because it so happens that the ITCZ is a very important system for seasonal rainfall over Southern Africa. It actually has a relationship between the onset and the offset of the seasonal rainfall. So that's why we are doing it, and we are doing it because it's a process that we want to actually evaluate how the model is performing in that. And this is process-based evaluation has recently been used from the assessment report number 4 and coming on like that. So what we are doing is to evaluate the CCAM cable model on how it actually is able to simulate the position of the ITCZ over Southern Africa. This Earth system model that we call CCAM cable is a combination of multiple models, we will say, where you actually look at the atmospheric model, look at the ocean model, look at the sea ice model, look at the land, the biosphere model. So it is interacting all those. In actual fact, that's what we find with the Earth system model. So this is the model that we are going to be using. And basically what we are going to use is the Adam approach to zonal positioning of the ITCZ, where you actually limit the latitudes between -20 and 20 degrees. And of course, just to highlight, some of us are Christians. This Adam here is a scientific Adam, not the one from the Bible. So when looking at the ITCZ, there's a couple of things that are quite interesting. I'm not sure whether there is a point here that I can make this place, but it's not, but that's fine. One thing that I've identified here is how the CCAM model is actually able, when you look at the dotted lines, one is green, the other is red. They simulate the ensemble mean. So this, I'm using the 18 ensembles of the CCAM model. So that is the ensemble mean, and the envelope is actually representing all the other ensembles. So that's what you can see. But what I found quite interesting is when you look at the envelope for the summer seasons, and you look at the position of the ITCZ as reflected by chips and crew, you can see that they are in agreement, they are together there. And you look at the ensemble envelope in the same seasons, it's smaller. When you compare into the winter season, there is a much wider envelope. And at the same time, when you look at crew and chips, there is a much wider thing. So what you interpret that, you realize that actually whatever is happening with the observations, the model is somewhat able to simulate that. And the other important thing is when you look at this trajectory-wise, or when you look at the trend-wise, it is able to pick the position of the ITZ. Of course, it's a model, it will not pick it exactly as you have for the observation. So in this case, there is a slight northerly bias by the model that you see. So in actual fact, it is performing well when you look at this graphics, but we also need to go into much details and confirm that it is actually presenting well, representing well. So what I've done now is to use the Taylor diagrams. Normally the Taylor diagram, there's a slight twist here that I've done. Normally the Taylor diagrams, we use them when we try to evaluate the models, multi-models against the observations. But in this case, because I have one model, when I'm using the ensemble mean, and I'm trying to evaluate that model like this multiple observation. So instead of using observation as the reference, I've used the model as the reference. So the reference line there represents the ensemble mean. Okay, that's good. So when you look at that, the most important thing is, and I hope someone will give me an idea as to how I address this. When you look at the lead three, both in summer seasons and in winter seasons, you realize that there is decrease in the correlation as to how well the model correlates with the observation. But then that again changes again, and the correlation increases again when you go into the lead four. I'm still cracking my mind to try and find out why that is the case. And then again, we can also use, and this the left panel, that's the anomaly correlation coefficient. I've just talked about those when I'm presenting on the Taylor diagram. The next one is the spread error ratio. So the spread error ratio, you actually use it to try and identify the reliability of your model. And that is based on if your model is actually able to predict the error that is contained within itself through the ensemble members, that actually gives you how reliable the model is. And the other one is the input efficiency. You're actually trying to assess the skill. So in essence, for the skill, what you want is whatever the outcome you get is, it should be anything higher than -0.4. That means the model has a skill that is better than just using the mean flow, what is going to happen. So, and when you look at this, you'll see that the model is actually doing fairly well. All you want is your SPR to be as close to 1 as possible. And again, all you want is to have your KGE as close to 1 as possible. But in any case, as long as it's greater than -0.4, it means the model is doing far better than just using the mean flow of the system. And in summary, trying to catch up with the time. But I still have a lot of time here, that's fine. In summary, what we have found is looking at the austral summer, or the summer in the southern hemisphere, what we find is the SPR ranges between 0.85 and 1.28, specifically 0.85 for the crude data and 1.28 for the chips data. And then again, you look at the KGE, which is both positive and greater than -0.4. Of course, it's very low because you want it as close to 1 as possible, but at least it's better. And now when you do the bias correction, you can actually improve that because it's a function of that bias and the correlations. So that can be improved. And again, when you look at the austral winter, you'll find that the SPR ranges between 0.71 and 1.42, where 0.71 is actually the error, the blue data, and 1.42 is the error 5 data. And the KGE, I've actually intentionally put this -38.99 for the blue data, just to show that it actually, you can actually rely even slightly on the model as to how it's going to present the position of the ITCZ, especially the zonal position of the ITCZ as represented by the blue data. And again, what we also can conclude is in this case, the CCAM cable model is actually reliably, can actually be reliably applied to explore the teleconnections that you can have, which is what is now leading to my second objective, where I'm trying to look at how is this ITCZ teleconnected to other meteorological systems of importance. Specifically, the tropical temperate trough is the one that I'm interested in, because it's going to link that tropical system which we have as the ITCZ with the cloud band that covers the tropics and the extra tropics. And with that, I think I'm in time, as much as it was very difficult. I still have a minute.
Good morning, and thank you very much for the wonderful presentation. I just want to ask, I recognize that you said there are some of the biases that you've seen when you're evaluating the model. Are there any plans to correct that? Thanks.
Yes, we have plans. Fortunately, it's a nice question. I was already planning, short as I am. I can easily hide under here, but that's fine. It's a nice question. Yes, we already have a plan to do the bias correction of the data so that at least we can see how the model performs with the bias corrected.
The notion of teleconnection. So, and I've often struggled with it. Is it a statistical phenomenon or a physical / dynamical phenomenon? And depending on how you respond to that, how would you go about engaging that aspect of this?
Oh yeah, that's you actually what you're asking. Both of them are correct. Because there has to be, first of all, there has to be that statistical relationship. Like for instance, we do the correlation. So that statistical relationship leads to you studying whether there is any dynamic explanation. Because of course, if you look at correlation, you can have heads being sick and people being sick, but that doesn't mean heads are making people sick. So first you start with that correlation. After you get this there's some relationship here, then you go into the dynamics and say, is this making dynamical sense? Or it's just a coincidence. That's what we're doing.
Thank you, Tech, for your presentation. Maybe a round of applause as you sit. And we call on the next presenter. Thank you. At this opportunity, we'll call Londani Letole. Londani Letole, thank you for sitting close by. So you have 10 minutes to indulge the speaker presentation. Thanks.
Morning, everybody. So this presentation is a continuation from a project that has been going on since 2017. With this presentation, it will be more of an improvement from the verification data that we've been working with the site-specific code processing system with my colleagues, Lucy Bonivani, and Brighton and Dr. Engelberg. So the provision of accurate climate information such as solar irradiance is crucial to the energy sector for tackling issues related to climate variability and change for robust planning of energy system. The predictability of variable power generation is becoming increasingly important to the grid stability as the penetration of solar energy increases. And you can see with the load sharing that basically doing that after the workout. And an accurate forecasting of solar irradiance is beneficial to the quality of future grid electrical grid scheduling and maintenance for power production. The variety of models have there's a variety of models that have been developed applied in forecasting of solar irradiance, and there are studies in South Africa that have been conducted for forecasting of solar irradiance potential. So in the South African Weather Service, we run a numerical weather prediction model named the SA model, which is underpinned by the United Kingdom Meteorological Office unified model, in which we have a site-specific post-processing system abbreviated as SSPS, which has been operationally running at source since 2017, focusing on solar radiation. The solar radiation and the site-specific interpolated from the graded data. The forecast of the surface shortwave radiations are produced by two resolution, namely AC1 and AC1.5, at which AC4 is at 4 kilometers and AC1.5 is at 1.5 kilometers resolution. As you can see in the picture, okay, SA1.5 covers the whole of South Africa, and then SA4 covers most of the southern side of Africa and also Madagascar. The hourly solar radiation model data is verified against the corresponding hourly data from our 10 ground-based radiometric stations. Now, these stations measure global horizontal irradiance, GHI, direct normal irradiance, and diffuse horizontal irradiance. And then the SA4 initializing time is at T00 Zulu, T12 Zulu, which focus up to 72 hours. And then also at T06 Zulu and T18 Zulu, which has a focusing range of 36 hours. And then SA 1.5 initializes at all those time T00 Zulu to T06 Zulu, T12 Zulu, and T18 Zulu, with a focusing range of 36 hours. And for this case study, we just only looked at the 2020 data for both observation and model data. Now, we used the common filter, which algorithm operates recursively on the input data to produce a statistical optimal estimate of the underlying system stats. The adaptive Kalman filter technique that we applied to the solar radiation focusing error is based on the approach taken by Galenas and Pinanda. The approach applied is based on a nonlinear correction of the focus errors using the Kalman filter. The statistics from the SSPS verification outputs are then integrated into the Kalman filter to enhance the statistical results. Now, we first looked at the stats before we integrated the outputs into the Kalman filter so that we can see how effective was the Kalman filter in terms of reducing the bias. And we were looking at the mean bias error, the mean absolute error, and the root mean square to evaluate our forecasting accuracy. So first, when we look at the results before the Kalman filter, we saw that the SSPS, when it comes to the mean bias error, we saw that the SSP overpredicts with an exception of 2 points, which is at Cape Point and at Kwando, those two areas. But generally, the rest of the other 8 points were overpredicted. And when we look at the mean absolute error, we see that Nelspruit had the lowest mean absolute error, and then we also had Kwando with the very high mean absolute error, and also with the trend continued to the root mean square error. We had the Nelspruit with the lowest root mean square error, and Kwando with the highest. Now, after applying the Kalman filter, we saw that the Kalman filter showed an effect, showed that it is effective in reducing the errors in each of the 10 sites, but the degree varied in each of the specific sites. And as effective as the Kalman filter was, there was some drawback that that we saw. If we can look there at if we can just look there at the R, at the root mean square error, we see that before applying the Kalman filter, the results were 61.220, and then after applying the Kalman filter, we saw that it increased the stats there to 61.282, which is something that we're still gonna look at, and we need to play around with the Kalman filter to hopefully reduce that stats to get up with the results. And now when we compare when comparing the hourly cycle of the observation, uncorrected and corrected model using the IRIN station as a sample, there was a noticeable difference there, as you can see. Oh, all right. So we can see that the blue color is the uncorrected, and then the pink color is the corrected by the comment filter, and then the black one is the observation data. As we can see that there was a significant reduction in the stats there from the comment from the SSP, and then after using the comment filter, we saw that there was a great reduction there, which closely reflects the observation data. So in conclusion, after introducing the comment filter into the SSPS, we saw that there was a great improvement in the GHI statistics results, and the plots for the KF corrected model closely matched the observation. Now, when we look at the future works, is to provide the shortwave radiation at a specific site over South Africa in order to enhance the generation of the solar PV. Now, to achieve that future work, we need to do first a similar study on the direct normal irradiance and the diffuse horizontal irradiance, and then after that, we wanna do a comparison study on the source SSPS with the other available models in South Africa to see how to range how's the performance of the SSPS, and then lastly to study the climatology of solar PV at various sites over South Africa. And then any questions?
Just a small comment. I don't think that it's worth fighting for improvement of the error in a second decimal digit.
Sorry?
I don't think that it's worthwhile spending energy on trying to reduce the error in the one station, you know, the difference that there was up to you to apply the common feature filter. It's like on a second decimal digit, it's nuts. I mean, if you do any statistical tests on this, there's like no difference absolutely whatsoever. Yeah, thanks.
Okay. Morning, everyone. My name is Jessica Steinkopf. I'm from the Global Change Institute at BITS, and I'll be talking today about some work that Francois and I have been doing on the ENSO teleconnection to African rainfall and looking at how to project it to change in the latest CMAP6 models. So we all know that ENSO plays a very important role in the interannual rainfall variability over many regions of Africa, especially Southern Africa, East Africa, and part of tropical Africa. So there's been lots of research in these different regions, and the dipole relationship of kind of dry conditions of Southern Africa during El Niño events and wet conditions over East Africa and the reverse during La Niña events is very well established. So we then wanted to look at how the global climate models kind of represent this relationship and how this might change under climate change. So we took the We wanted to investigate the latest coupled model in comparison project phase 6 models. And firstly, I'll take you through the process, but firstly, we wanted to compare to observations and how they actually represent this teleconnection. And then we wanted to look at how it's projected to change. So we took 42 CMIP6 models, and we took the monthly precipitation values and the surface temperatures from each of these models. The models were selected based on the availability of both these variables for both the historical period and for SSP 585. So we chose SSP 585 because this has the strongest warming signal by the end of the century, and so actually the strongest regional signal. The first member variation was used for all of the 42 selected models. And then the Nino 3.4 index was calculated, or the anomaly was calculated for each model using those surface temperatures. The Nino 3.4 region was selected because it is a region strongly coupled with the overlying atmosphere. And then in order to do a comparison with observations, in situ observations would have been ideal to use, but as we know, there's limited spatial coverage of station data in Africa. So we used the climatic research unit through gridded observation data set. And so all of the model data was regridded onto that same 0.5 degree grid for comparison. And then we used the NOAA's 3.4 index for observation comparison. And then we looked at the signal. At this stage, we've only looked at it during December, January, February, as this is when the signal peaks. So first off, this is a correlation map showing the Spearman's rank correlation between our CRU, DJF, and the NOAA and Nino 3.4 index for DJF for the period 1984 to 2013. And you can see that the well-known dipole relationship between ENSO and rainfall over southern and East Africa is well captured. For those negative anomalies over southern Africa are indicating dry conditions during an El Nino and wet conditions during La Nina, and the reverse over East Africa with the positive correlations. You can see there are larger regions over southern Africa that are statistically significant when compared to East Africa. And there is relatively weak signal over northern and west. So how does this compare to our CMIP6 models? So this is obviously a lot to take in, but firstly, in general, the CMIP6 models, this is firstly looking at the historical correlations, which is for the same period, 1984 to 2013. Most models do capture well the dipole relationship, of getting those kind of negative correlations over Southern Africa and positive correlations over East Africa. But interestingly, unlike the observational correlations that we saw, the models generally show more statistical significance over East Africa than Southern Africa. Overall, they are overconfident in terms of the strength and the spatial extent of the ENSO teleconnection, particularly over Northern Africa and sort of tropical Africa. But it's also important to keep in mind that some of the weak correlations may derive from biases within the models themselves in terms of either or both the representation of the precipitation itself or this precipitation. But as I said, the important thing is that most of the 42 models did correctly capture that kind of dipole relationship over Southern Africa and East Africa. And how does it change? So this is now showing the same thing, the Spearman's rank correlation between the individual models for DJF, but now for the period 2017 to 2100, the last 30 years of the century. And most of the models, about 60% of the models, maintain that dipole relationship under a changing climate. So yeah, that was interesting. And noteworthy is there is a very strong, significant signal that kind of emerges or is projected over the Horn of Africa, and it sometimes extends right across into West Africa. You can see just by eyeballing it, quite a few dark patches with correlations over large regions. Over Southern Africa, most of the models maintain the dry signal, and there is quite a significant negative correlation that develops particularly along the west coast of Southern Africa. And that negative correlation is indicative of dry conditions during El Niño and wet conditions during but it was something that definitely compared to these ones, the historical correlations that developed and came out stronger. So but it's also important to look at kind of the multi-model ensemble mean, and rather than looking at these 42 individual models. And so what you are looking at here is the mean of all those correlations, and the left-hand plot is for the historical simulations, and the right-hand plot is for the future projections or simulations, and the stippling represents the model agreement. So the dots indicate where 2/3 of the models agreed on it being a positive correlation, and the X's indicate where 2/3 of the models agreed on it being a negative correlation. So again, we can see that over East Africa, there is a strengthening of the relationship. So it becomes the correlation value becomes stronger. But what's quite interesting is if you look over Southern Africa, is this this change. There's definitely less model agreement kind of in that Eastern Southern African region. And so the models can't quite agree on what is going to happen with the ENSO signal. And it suggests there might be a weakening of the signal, or it's just that the models are just a bit unsure of what kind of role ENSO will play under a warmer climate. So 1 minute. Okay, let me quickly then. So we want to then look at plot the composite anomaly maps for the rainfall for DJF associated with each of the different ENSO events. So what you're looking at here in the first row is CREW again. So it is taking each of the El Nino events and averaging the rainfall anomalies for those El Nino events, and that's what's plotted in the first one. Then the same but for La Nina, and then the same but for neutral events. And underneath is the same but done for the 42 models. So this is a mean of the rainfall anomalies in the 42 models for each of the El Nino events, and then the same for La Nina and the same for neutral. And what you can see is that the models, while they do get the drying signal over Southern Africa, there is still this kind of positive anomaly that we see popping up over that eastern region. And during a La Nina, it's definitely drier than we would expect it to be in the 42 main bands. And we can then compare this. I'm rushing a bit because I'm running out of time. So this top row is the same as the previous slide. The bottom row is now for the scenario map model simulations, okay, for the 42 members, to see how the composite anomaly plots change. And we do see the drying over Southern Africa remaining during an El Nino. And in fact, although the extent of the drying is less, the spatial region is more. But then during a La Nina, again, we get in this drying along the west coast instead of seeing the wetting, which is quite interesting. So we still need to look in a bit more detail about why this is happening. I'm going to be looking a bit at the daily data and trying to look a bit to see if there's change in the daily streams. But that's all I have time for today. Time's up. Sorry.
Thank you very much. Just a quick question. You've tied everything to grow data. We know that observations are not particularly reliable. Do you think those results, that the level of agreement will change if you applied it to any APUs to different data sets, chips or downside or something like that?
Thanks.
Does the literature say about the sort of relationships?
We did a paper last year that looked at, we compared CRU, chirps, and ERA 5 in terms of rainfall in Africa. And CRU and chirps were quite similar, especially in the ENSO. The ENSO composite anomaly maps, so those ones that I showed, I actually took out of that paper. And the chirps ones were almost identical. So that's why we just decided to focus on.
So I have like a similar question on the selection of the two products, whether chips or maybe a 5 rainfall product really adds much more value, especially zooming in the relationship in areas that shows like the normal discrepancy like Southwest.
Yeah, so maybe to do a more detailed comparison, we could also involve ERA 5, but as I just explained, in my previous paper that those plots came from, that top row there. Oh, you can't see it. I don't know why this thing stopped showing. But we specifically verified the ERA 5 rainfall product against both CRU and chirps. And in terms of specifically the ENSO composite anomaly maps, they were quite similar. So that is, yeah. But I suppose there's value in maybe comparing the all three. That's okay.
Thanks, Jessica. Great talk. You look at how the CMIP models resolve the seasonal cycle of ENSO. In terms of your focus is DJF, but what happens if ENSO starts shifting slightly earlier, slightly later? What does that mean for rainfall for the region?
So that's why definitely next we'll maybe start looking at the other seasons, but we just focused on DJF because that's when it's supposed to be the strongest for now.
Thank you. We'll call our next presenter, Percy. We're going to be looking at projections of change in the Southern Hemisphere, Westerlies, under low and high mitigation scenarios. Percy, for 10 minutes and just be checking on me there. I'll be looking my. Yeah.
Hi everyone, my name is Percy and I'm here to present a part of my PhD study, which is particularly looking at the response of certain hemisphere Western response to greenhouse gas concentration and the supervision of Professor Blunt, as well as Professor Cameron. Just to give you a background. Just to give you a background of the study, so the first part of my study was looking at the depletion of the stratospheric ozone recovery, which occurred in the last quarter of 20th century, where we tend to experience depletion of this stratospheric ozone, which led to the change in the atmospheric circulation.
this was particularly associated with high accumulation of ozone-depleting substances, which include the chlorofluorocarbon, the chlorine, as well as the nitrogen oxide. So this led to what we call a certain annular mulch, which is associated with them, this positive phase is associated with the forward shift of these westerlies. So this has put an impact on the location of the mid-latitude storms, as well as the ocean mixing, which entails the absorption of carbon dioxide, as well as the heat uptake in the certain ocean, as we know that certain oceans play a big role in absorption of carbon dioxide, as well as the heat. So in response to this, there was a Montreal Protocol trying to alleviate the change in this circulation associated with the depletion of the stratospheric ozone. And then we tend to experience a recovery in the stratospheric ozone, where we able to see a pulse in the polar shift of these westerlies. And then with this, we have like a gap, a less knowledge in terms of these westerlies in response to greenhouse gases concentration, which will also limit us in understanding the mid-latitude storms, as well as the ocean mixing, the uptake of heat and carbon dioxide. So this study is aiming to indicate the response of the southern hemisphere westerlies in response to these greenhouse gases, as well as the ozone recovery, which was promoted by the Montreal Protocol. So the tools that we are using are CMF6 models, 13 CMF6 models, which are selected based on the availability of the data and the variables that we were going to use. And then under these models, we use two experiments, which are the SSP 126 as well as SSP 585. So the selection of these two scenario is that SSP 126 is regarded as a sustainable pathways where there's a high cooperation, international cooperation, less burning of fossil fuel, and then moving towards the green energy. While the SSP 585 is characterized with high emission of greenhouse gases leading to extreme weather events. So under this analysis, we use two variables to understand the change of the atmosphere, to understand that we use the air temperature, so we can able to see the role of ozone recovery, as well as the role of the greenhouse gases concentration. And we use the zonal winds to understand the location of these westerlies, as well as their strength. And then we did this analysis throughout the century up to 2100, divided into a recovery period where there was a recovery period in response to the Montreal Protocol, which is between the year 2000 to 2020, near future, which is from 2021 to 2040, the mid future, which is 2041 to 2060, and then the far future will span from 2081 to 2021. So firstly, we try to understand the response of the atmospheric temperature across the atmosphere from the lower level up to the stratosphere. So the plots are covering up to 10 hectopascal, where we can able to cover the stratosphere and then able to see the response of the ozone recovery. So if you can see under this plot, particularly in the mid future, that's where we are able to see the response of ozone recovery over at about 200 hectopascal. That's where we see the location of this ozone. So we know ozone play a big role in absorption of incoming solar radiation. So in that region, which is at about 24 kilometers, we expect to see the warming of this lower stratosphere due to the role of the ozone recovery. So if you can check at the mid future, we tend to see the reduction of lower stratospheric cooling, which is being indicated by the recovery of the stratospheric ozone. And then moving to the far future, you can see the cooling is weaker compared to the past periods where the recovery was not fully recovered. And I should indicate that the recovery of this stratospheric ozone is expected to to reach its pre-industrial levels at a mid-future 2060. And then you can see as well over the lower level of the atmosphere, we tend to experience a warming of the surface of the troposphere towards the far future. And then when we look at the SSP, the worst case scenario, we tend to see that cooling still persisting over this level where we have this, where we're expecting to see it warming due to recovery. But under this concentration of greenhouse gases, we continue to see the cooling showing that this concentration of greenhouse gases under this scenario tends to overwhelm the role played by the Montreal Protocol in recovery of the ozone, atmospheric ozone. And then you can see a sharp increase in temperatures in the lower near the surface and in the troposphere, which is indicating the impact of this concentration of these greenhouse gases on the troposphere. So in response to this, we further analyzed the response of the Southern Hemisphere Westerlies under these two scenarios as well. So at the periods where the stratospheric ozone, it was not yet fully recovered, you can see that the westerlies tend to be located polewards, just to indicate. So the green color is showing the region of these westerlies, while the blue color is indicating where these westerlies are being displayed. So the first two figures are indicating really the area where these westerlies are located near the poles. And then these figures are covering from the equator up to the poles. So when we move towards the mid-future, where we expect this stratospheric ozone recovery to play a role under this scenario, we tend to see there is at least a weakening of the westerlies near the poles, and then shifting towards the mid-latitudes, where we now likely to see the rainfall distribution over the Mediterranean climate region, which includes the Western Cape region. So this scenario is indicating really that the role played by Montreal Protocol will tend to promote the rainfall distribution over the Western Cape region and other regions which fall under this Mediterranean climate region into the future. So under the SSP 585, you can see that there's a persistence of these westerlies in the poles, which is indicating a bad thing in terms of rainfall distribution over these regions. And then to evaluate, to understand the performance of these models in terms of these changes, projected changes in westerlies, we then evaluated the agreement of these models towards the sign of change, in order to see if these models are really agreeing in these hotspots where these westerlies are projected. So this plot is also showing those two scenarios, indicating the region where this model are showing a stronger agreement. So for each and every grid point, we were analyzing the agreement. It's at least 66 agreement of this model is indicated by speaking over these changes. You can clearly see over the area of displacement as well as the area of where these westerlies are concentrated. These models are able to agree with these changes. As a conclusion, we can see that the concentration of these greenhouse gases on the atmospheric in the atmosphere has got a big impact on the atmospheric temperatures, as well as the location and the strength of westerlies. So the low mitigation scenario tend to exacerbate the warming over the stratosphere and overwhelm the role played by the Montreal Protocol. So this will likely to promote the dry pollution over the Mediterranean climate region. And then as a part of finalizing this study, we are showing the behavior of these westerlies in terms of greenhouse gases concentration and ozone recovery, as well as this indicating the rainfall distribution in response to this circulation. Thank you.
Thank you very much for that very interesting presentation of the interesting work. If I have time, if there's no one else, maybe two questions. First question is, did you consider exploiting this as a seasonal or a sub-seasonal forecaster? Because now forecasting device rather. So now you're looking in climate change on longer periods, but if there should be, at least according to the dynamics and chemistry, a link which you also shown between greenhouse gases and ozone with the surface temperatures. So theoretically, you might also be able to link that with like a 2 week to a 4 week predictor of surface conditions. Have you considered doing something like this?
No, we didn't do seasonal forecasts, but then I think that's going to be one of the things that we can consider in the future. But then we're looking at the climate projections in this study. Yeah, but then just to indicate again, this study we only focus on the DJF in consideration that the response from the ozone recovery is being pronounced during the DDF season. So it occurs during the SON season, then get to be pronounced in the DDF season. Then we also analyze the response of these Westerlies during other season, but then in terms for time of presentation, we only show this season.
Perfect. Is there time for a second question? Or...
Thank you very much for the presentation. Could you perhaps summarize what your findings were for the other seasons and how they differ to DJF, especially given that in the Southwestern Cape, which you were referring to a number of times, our rainfall seasonality our rainfall is lowest than the DJF. Thank you.
Yes, thank you. So we also analyzed all other seasons, and then the behavior in terms of ozone recovery as well as ozone concentration was specifically analyzing this season, DJF season. But then, yes, there is a change in terms of strength and then the location of these Westerlies in other seasons, and then which will also lead to the rainfall reduction under the worst case scenario, particularly.
Thank you. So I think, you have to be very careful with communicating the result, because when you say, that there is a reduction in rainfall linked to change in the Westerlies in DJF, in Western Cape, there's not much rainfall that is given by Westerlies in the DJF, which is that's sort of slightly conflicting messages.
Move on to our next presenter, and Ilani. Oh, you're here already. Thank you. So over to you, Ilani. Please, go ahead.
Thanks, everybody. So today I will be presenting on scoreline definition and their relevance to South Africa in form of a case study. So first of all, I'm going to start off with where did it start, the word scorelines. So first of all, the Iowa scorelines was named from Hendricks in 1888. So that's quite far long ago. And that was in the Ohio prairies. So what happened is he used this word to describe the occurrence of phenomena over the Ohio prairies, sorry for that, in the USA, because it had similar characteristics to a tornado. Now in 1888, he renamed this to a derecho, which means straight in Spanish. So the next terminology that we get is for the instability line. That was in the 1950s. So this was used to describe a non-frontal squall line or a pre-forefront squall line as well. And this was given by the International Meteorological Organization. Then we have a line echo wave pattern that was also in the later 1950s. And this was to describe a wave-like echo pattern that was preceded a tornado. Then what they've also realized, especially Fernandez, he mentioned that the Western African meteorologists actually named squall lines a disturbance line. Then we see that in the 1990s, Anderson and Arrett, they took Maddox's definition for squall or NCCs, mesoscale convective complexes, and they realized that it does not capture for your long elongated NCC types, so your non-NCC squall lines. So then they renamed it to say persistent elongated convective systems. Then fairly in the same time, there was also the word that came out was quasi-linear convective systems. So as you can see, squall lines actually have quite a bit of synonyms in order to capture this one word. Now, this is an exploratory study focused on global squall line definitions, and they tested their relevance on a South African case study. So first of all, we go into just a quick review of global squall line definitions, methods of identifying squall lines, and then also a quick case study on South African squall lines. So first of all, if we look in squall lines, they are mesoscale systems. They can produce damaging straight line winds, large amount of small hail, large hail, heavy downpours leading to flash flooding, and even tornadoes or the occasional dust storm. So squall lines are then a subgroup of MCSs, so mesoscale convective systems. So if we're firstly going to go into the definition, according to the glossary of meteorology, we can see that it's a cloud system that occurs in connection with ensemble of thunderstorms and produces a contiguous presentation area on the order of 100 kilometers or more in a horizontal scale in at least one direction. Then Hauser, he mentioned that the length scale of 100 kilometers and time scale of at least 3 hours needs to be met. So if we now look into the definitions of squall lines, Williams in 1940, we used synoptic data in order to define a squall line. So he looked at two criteria. First of all, a narrow zone of activity, usually parallel to a surface fault front here now, and approximately 160 to 320 kilometers in advance of a fault front. The second criteria is the line activity characterized by thunderstorms, heavy rain, short-lived wind shifts, gusty winds, rapid pressure rises, and temperature falls. Then Porter and et al. In 1955, they looked at three criteria, mainly it needs to be associated with the wind shift, usually to the northwest. This is now in terms of the United States of America, at 16 to 18 meters per second. This shift occurred on a line connected by 2 or 3 weather stations, and then the wind shift and associated thunderstorm activity lasted for 6 hours and longer during the movement of the system. Now, in terms of a South African context, in also the 1950s, Stalyard mentioned that a thunderstorm belt developed parallel to the moisture belt, as Lynette mentioned, the dry line, roughly 300 kilometers to the east. He named it line scarps, which is associated with a row of thunderstorms. Then the WMO in 2022, they defined a squall line as the following: a strong wind that suddenly rises and lasts for at least 1 minute. Now we need to distinguish between a gust front from a squall, and this is because they are longer in duration. Squall lines, they need to last at least 1 minute, but they need to have 60 knots and they also increase to around about 22 knots in gust. Then they also mentioned that it's associated with violent convective activity, large cumulonimbus clouds, and can reach kilometers horizontally and several thousand feet in the vertical. Now we're looking to methods for identifying squall lines. First of all, we looked at the synoptic data method. Now we're going to look into infrared satellite imagery and then also radar. So in terms of the identification of squall lines on IR satellite image, as mentioned earlier, Maddox in 1980, he used IR satellite imagery to define ANCC. Now Anderson and Arrett, they modified the criteria and added a criterion to identify squall lines. So this is what they then said. The size needs to have a continuous cloud shield, so your IR temperature less or equal to minus 52 degrees Celsius. The area greater than 50,000 square kilometers. Now that's quite massive. The initiation is when the site is split net. Duration needs to be longer or equal to 6 hours. Maximum extent is when the cloud shield reaches maximum extent. Shape is when the eccentricity is less or equal to 0.2. But that's different than for NCC. And then your termination is when the site definition is no longer met. Now, in terms of radar, so there is a criteria that is specifically for squall line that was developed in the 1980s and then also in the early 2000s. So if the region of interest has a reflectivity of 40 BBZ and higher, the length needs to be 50 kilometers or greater. The length to width ratio needs to be 5:1. The duration needs to be 30 minutes or longer. The initiation is when the length and the length to width ratio of first met. And the termination is when any of the first criteria are no longer met. Now I'm going to go into the case study. So 31 January 2018, there was quite a severe squall line that occurred over the central part of South Africa, which is Free State. So as you can see here, 2 children were injured, roofs on formal settlements blew off in Brandford and Kenison. And the most significant impact that occurred was that 19 miners were trapped underground at the Beatrix mine due to Eskom power lines that was damaged. So if we look at the observational data, this is now in Zulu time or UTC. So 21, you can see that the temperature at Belfast was 21 degrees Celsius and the wind direction in BC at 30 kilometers per hour. However, an hour later, when the squall line actually reached Belfast, you had a temperature drop to 13 degrees Celsius. The wind direction was southerly, wind speed 56 kilometers per hour with a wind gust of 102 kilometers per hour. Now I'm going to test the radar method for identification. So I've highlighted where Belfast and Beatrix mine is. So first of all, at 2129 UTC, you can see that the length was 261.38 kilometers. This is now from Webster in the Free State to Sing in the City. The width was 42.86 kilometers, and the ratio then was 6:1. And then the duration was more than 30 minutes. Therefore, the criteria is met. However, if we now look into the satellite imagery, so what I did here is I just took the satellite, IR satellite imagery and just displayed all of the temperatures that's less than minus 52 degrees Celsius. So now we can see that the area, if you calculate from the radar method, we can see that it's around about 11,203 square kilometers, which is not close to 50,000 square kilometers. However, the eccentricity is 0.16. So it does meet some of the criteria, but not all of them, and especially the area. But considering that the area for squall lines for the IR satellite imagery method is more tailored for the United States of America. So now, in terms of summary, the South African squall line case of 31 January 2018 met the criteria for identifying squall lines using radar data, but not with IR satellite imagery. Just quickly coming back to my master's topic, which is identifying of investigating South African squall lines and their associated atmospheric conditions. The first aim will then be used in order to address this issue by creating a decision tree to identify South African squall lines. The second aim is also then to determine the atmospheric conditions associated with the life cycle of African squall line, which in the hope we will better know and understand South African squall line. So yeah, that's all. Thanks.
Thanks, that's a great talk. I would recommend dropping your cloud temperature from MediaSat from probably -52 to -42, because as you suggested, it's based on the American mid-entry definition. So just drop that down and you'll be fine at 6 boxes with MCSs.
Thanks very much.
Thank you very much. That was a wonderful presentation. I actually was fascinated with some of the things that you found in the area where I come from. The question is, your findings in your master's from those 2 mines that you mentioned. Did you go back to the mines and present your findings? And what was, if you did, what was the reaction? What was the response?
So unfortunately, no. So I was actually with the forecast during that time, situated in the weather office. But no, we did not go back.
Thank you.
Yeah, that would be quite interesting to show them what caused the impact.
Okay, everybody, my name is Kusun Bati. And I'm the associated with organized conviction of 20% of people. Let me just give just to describe what organized conviction is. This term refers to deep convection that is organized into level scale convective systems, which is the family comprises of your squall line, your middle scale convective processes, and your supercell storm. So why are we worrying and studying the organized convection? We all know that organized convection is associated with immediate disasters. So we're trying to mitigate the risk of environmental disasters, and all this is likely dependent on the weather and climate change. We need this information in order to better manage water resources, public health, renewable energy, and hazard transition. Over Southern Africa, it is widely understood that convection is a almost rainfall producing process. So this MCS appears organized grouping of storms that occurred in the tropic and mid-latitude. In many parts of the world, atmospheric convection is often understood to be resulting from the downward of the boundary layer. So this research will focus on extreme weather events associated with organized convection over Gauteng. And I'll be looking between October to March, and the period that is going to be covered is 2015 to 2021. And this is just the first preliminary attempt to classify synoptic scale circulation responsible for extreme weather events associated with convection of volcano. Basically, the reason why this study is conducted over Gauteng is due to the fact that Gauteng province is highly vulnerable to extreme weather events associated with convection, but also, as we know, that Gauteng is an economic hub for the country, coupled with high population density. So my data sources, South African Weather Service and the European Center for Medium Range Weather Forecasting. So the variables that are going to be analyzed is the information that is sourced from KILAM, which is a document that details all the notable weather related events at a specific location and time. And the confirmation we use with the station data together with the calculation for heavy rainfall, which is on soils, it indicates that heavy rainfall is when about 50 millimeters of rainfall is received in the area in 24 hours. And then reanalysis data is going to be around 5 hourly pressure and single level variables, which is okay for relative humidity excess. So I've sourced data from KILAM in order to give direct doubts that Gauteng province is really vulnerable to extreme weather events that are associated with rainfall. So when I plotted, it showed that Gauteng is leading about 27%, with KZN coming second, and then the least affected or vulnerable to these extreme weather events is Northern Cape. And then this is just a scoop of what KILAM looks like. And then these are the events that's where we selected over Gauteng. And then it is good to note that we have two extreme weather event related rainfall events in 2015 and 2016, which coincided with the occurrence of El Nino season, which we know, as Jessica highlighted, that it is El Nino is usually associated with suppressed rainfall over the subcontinent or Southern Africa. So this talks to preparedness because you can tell the impact that the first case, there were more than 500 houses that were destroyed and over springs. So that means while we are preparing for an El Nino forecasted season, we should also be aware or not discount the chances of these extreme rainfall events occurring. And then this is just radar observation tools just to track the intensity and the storm movement. And so, and it's also great to note here that there is higher, over the area of interest, there is higher reflectivity of up to 40, as Ellen has mentioned. And then you can tell by higher reflectivity that there was a presence of storms in both cases, and they both occurred in the afternoon. Then I will go to observe events and their synoptic circulations. We have a surface chart that shows the presence of an anticyclone southeast of the subcontinent, coupled with a surface low in the interior, working together. And this anticyclone is bringing moisture from the Southwest Indian Ocean into the eastern part of the country. Also, the low pressure system is driving moisture from the tropics. So when these two unstable air masses converge, there is some sort of not so well defined dry line, but it's sufficient enough to trigger the uplift. And then the higher values of Cape also indicate the possibility of convection activity occurring later in the day. And then we can see There's in the middle levels, we have a presence of a westerly wave, which is known to produce the variations in the intensity of convection. And then usually we have the convective activity occurring just ahead of those perturbations. And then as well, you can see the convective precipitation was observed in the day, as well as the landscape precipitation, which might be resulting from the stratiform cloud. The second case is also almost similar, just the difference is that we have the cutoff flow in the mid levels sitting just by the west coast. This location has been found to have substantial in the rainfall received in the south coast, east, and also in the interior. And we also know that cutoff flow is also associated with the deep moist convection. So in closing, with the study, it is seen that these convective activity, they are not only influenced by the surface pressure systems, but also they are coupled with the small to large scale perturbations in the middle levels. So this can assist in forecasting by using the pre-existing conditions and simulating features of these activities to determine if conditions are conducive enough to the development of organized or extreme convection sufficiently ahead of its occurrence. Thank you.
So again, very fascinating current work that you're doing. It's very impressive because according to the statistics you presented, the drier areas are becoming drier and the wetter areas seeming to be much more wetted, according to the data that you presented. So in essence, what I'm saying is Western Cape areas receive unusually high levels of rainfall. So it's KZN and Gauteng. And that is, the results are that infrastructure and human lives are at stake. I'm hoping that you would make some kind of recommendation to the Disaster Management Center to avert much more damage and to human lives and infrastructure. Thank you.
Thank you for your attention and for the engagement that we've had in this session in climate dynamics. I'll hand over to give us a few announcements, but thank you for the time.
Okay, folks, we're going to break for lunch. I want to tell you that the final component of our foodie bag package is involved at the end. It takes about 6 seconds here. Okay, so then on the other thing, and Melody will not be there.
Like here.
Darren? Darren?
Then I think PowerPoint would be better. Yeah. Oh, okay. Mind if I rename it? Don't it? Oh, yeah. Yeah. Maximum. And that's what viewings. And then the one talk is on. Yes. Yes. Not yet. On the best. What is okay. Now let's minimize this right here.
Yes, definitely. And, sorry,
It's a video. Okay. Where's the USB gun?
yes.
Okay. Well, I'll tell you the situation is that we delegation. Thanks. Right.
So, colleagues, just realized that the time is
Colleague here, this is our next door. Yeah.
Yes.
Pardon?
Yes, it's just there's.
Oh, yeah, no. No, you don't have to, but.
So you want either to,
So like I don't become late.
I see, yeah, yeah. For if they delay, oh, but yeah, never mind. You have to click now. Yeah. Yeah.
Straight outside, so I'll miss yours. No.
Okay, so you want to start now? Yeah. Okay, I think we can begin. So with the posters. Hello.
So we can hang the posters after this session. There'll be another poster session, no? So we can finalize that because we have to get going with the session. So if you can all settle down and, get on with it. So this session will be about climate change impacts, which is a relevant aspect in the context of the present conference. So the first speaker today or in the session will be Mohau, and he'll be explaining to us about climate change impacts on key components of the renewable energy value chain. So,
all right, thank you very much, Chair. So what I will be presenting on today is basically part of a research and development project that the CSIR is doing in partnership with ESCOM. So this has been a long ongoing project. I just joined in its second phase, but the work got started by colleagues like Francois and Johan Malherbe, who are also in this room, so they would know about the direction of travel of the project. But I'm not going to try to present about the latest research findings on this project, but I would like to touch on the conversational aspects that goes between climate atmospheric scientists and the engineers in terms of finding out what could work for resilience. And this is just to paint a picture on where are we in terms of thinking around climate hazards and their impacts on the energy sector. Also, I would like to get your feedback in terms of this research direction and approach. And maybe we can figure out how the latest available climate science could provide value for resilience in the case of the energy sector in South Africa. And probably we'll figure out also areas where collaboration could build on the work that has been started in terms of the climate science and the energy sector aspects of this work. So the climate science base for the project is basically the use of F-system model to simulate the climate, and these are informed by the standardized emission scenarios. So the model that we use here is a CKM cable, which has been developed by the CSIRO and extensively evaluated and worked on in South Africa, including the CSIR. So this model is run as a global model, and then it can also work as both a dynamical downscaling as well as a global model. So, however, lately we are also trying to apply statistical downscaling approaches in various areas to improve the signal, especially when we have good evaluation observation data sets. So, and the outputs of the work fits into impact modeling. We have colleagues who are more into hydrological aspects of the impact modeling. Also, there is also a lot of effort in terms of power system specific models that are being informed by the meteorological variables that come out from this model. And in the end, the work goes into aspects of risk modeling, which integrates the hazard side, as well as some other data sets that help to quantify and understand specific risks for the energy sector. So in terms of the pipeline of data from the model outputs into the various areas application, actually what works is so we do have aspects that cover natural variability, climate change signal, as well as a proper quantification of uncertainty. And so we have also the risk screening tools that are actually incorporated to quickly approximate and identify the relevant time periods as well as relevant events of interest for various aspects of the energy sector value chain. And of course, we also think of what are the extremes, as well as what are the events that should be looked at for specific aspects of the assets. So this is the kind of climate data pipeline where you look into long-term adaptation planning, and you select the time and periods appropriately. As also you look into the issues of resource adequacy, especially when it comes to the power production. And then, of course, all this information fits into the production and cost modeling, or even when it comes to aspects of expansion of the grid and the asset itself. This information actually informs the standards, as well as the approaches that could be taken in terms of going forward into the future. So when it comes to the energy sector, in talking in general, all the timescales are actually relevant, from short range, medium range, all the way to long range. They're actually, if you can have data at these timescales, somebody in ESCOM will be able to translate to a relevant area of application. For example, when we think of extremes like heat waves, the teams that are working in transmission and distribution lines often would take that information and be able to tell you what kind of impacts are relevant on the side of ESCOM. The same happens to assets like transformers. They're sensitive to changes in heat. You have thermal generation, like nuclear and non-nuclear energy generation. When there's extremes in terms of heat associated with climate change, you get a reduced generation capacity. So even in the case of solar generation, you find that there are components that are actually sensitive to climate parameters. So, however, in this conversation, what is really critical aspects that when we talk between atmospheric scientists and engineers, is the issue of data consistency across integrated model domains. So here you are basically thinking of a technology adaptation pathway. And for example, aspects that come in are things like capacity expansion, cost reduction, and power flow and stability. So from the climate science, we would have, for example, outputs from long-term climate model simulations of thinking of the hazards, as well as the weather hazards that would come at short time scales. And this information, of course, you have this model granularity. And when it comes to the services that are relevant for the sector, you need, again, to do the mapping. For example, all the hazards, you find that most of the hazards, hurricane, floods, air temperature, heat waves, and solar and wind and lighting, you find that they actually affect various components of the value chain. And of course, once you have mapped the model outputs against where they could apply, is then that now you can start thinking around how to build resilience. So we had conversations around understanding the thresholds of relevance. For example, when you're thinking of PV power plants, there are certain thresholds where they actually, temperature thresholds where they don't work as effectively as they should. And this information, if you are just a data analyst or you are basically coming from a different field, you might not know exactly how to uplift information that would help their decision making. So we start to have interviews where we sit together as a group and say, okay, what are the critical thresholds in terms of temperatures, precipitation, and other aspects that would change your line of operation or will probe new types of decision-making workflow. And this is the work that is in progress. So just to drive the point home and to demonstrate, in the case of thinking of risk to weather condition for the wind powers, they would have what they call a cut-in and cut-off kind of wind speeds. And when this cut-off wind speed is exceeded, you have a situation where your wind turbine is no longer working. And these critical thresholds are known, for various types of technologies. For example, here what you see is basically an actual wind versus a calculated or a model wind speed. Of course, with statistical models or data-driven models, we are actually able to get a kind of models that actually can get very close to your observed signal in terms of quantifying the power production that you can get. And also with the models, you can basically try to integrate climate information and get a sense of if you go into the future. These cutoff thresholds, what is the probability that they would get exited, or what is the signal in terms of getting into thresholds where you know very well that the stability of your generation is likely to be affected. So these are some of the things that once you have got relevant information from the experts in the power sector, then you try to get the model outputs and make sure that you quantify the kind of aspects that would be helpful in terms of their decision-making processes. So, we basically, of course, in engineering space, there are scenario reduction techniques that are applied to ensure that if you, both the diversity of the details can actually be mapped into the aspects of risk that they would mostly think around. So in summary, what we can do is to leverage from various data sources that we have. And in the end, what you want to achieve is to be able to bring climate risk and adaptation into all areas of their business. For example, when it comes to expansion, things like spatial disaggregation of climate information becomes critical. This is where you basically want to be able to map the location of assets as well as the type of assets to specific patterns that you can uplift from your model outputs. And and next, you also want to get your impacts to be represented in such a way that they cover all the areas where the assets are located. Here's an example of an analysis that led to the quantification of the number of heat waves. Christian has already introduced the definition that SASAS. Christine has introduced the definition that SASAS uses in terms of defining heat waves. We've just used exactly the same definition and try to get a sense of if you think of the future scenarios around the temperature thresholds relative to a specific baseline. In this case, we look at the 1.5 and 2 degree warmer worlds, but we are not using exactly the same baseline that you typically use around the pre-industrial period, but we just try to get a sense of whether there is an increase or a decrease in terms of the number of heat waves. We do the same thing around intensity, because when the heat wave intensity increases, certain components in terms of, for example, the transmission line also buckle up and they start to be inefficient within the transmission aspects of the assets. So these are some of the outputs that are really interesting to ESCOM, and they want to get this data translated in a manner that they can run through their adaptation planning strategy and system hardening options evaluation. So they would typically have matrices where they use to decide whether they would either harden the system or they should actually consider a replacement in terms of the technology options that could be used. So now still in the case of reacting to the impacts, we also bring this climate risk and adaptation into operation planning. So the CSIR produces a regular seasonal outlook, which is more like a bulletin that talks to aspects of the seasonal variability. And this information is really valuable in terms of the scheduling, operational planning. For example, in the case when we have seasons that are extremely wet, we already know that ESCOM would typically struggle with getting the coal at the right conditions such that it can be pulverized and be used for generation, and we end up getting load shedding. But if they are informed in advance in terms of the variability, sometimes they can plan slightly differently in terms of improving the operations. So all this information actually turns out to be relevant in terms of the adaptation, early warning, and building resilience. So going forward, we would like to bring more focused output at varying resolutions to better understand uncertainty in the predictions. Also, at least we think for those areas where convection is relevant, it would help actually to have a 4-kilometer model that can resolve processes that are often overlooked by coarse resolution models, especially in those areas where the assets are located. And also to explore the processes that drive climate variability and their teleconnections, because sometimes getting to understand processes at a synoptic scale and even further, it's really important, because you can actually bring more confidence in terms of the patterns that are shifting, especially on seasonal time scales. And also, we would like to engage with more institutions to develop tailored services that can be of value to the energy sector in the country. And of course, what we have now will benefit from continued evaluation in terms of how much science is contained in these models, especially the newly configured seasonal forecasting experiment that we are using for these bulletins at the CSIR. Thank you very much for your attention.
So we won't take any questions. Obviously. But of course there will be discussion sessions so that they will get to all engage in case there's some students, right? That is why we're all here in one space, because we can't cover everything in 15 minutes, 10 minutes, right? So we are talks are just there to galvanize conversations, stimulate them so that we get them streaming, and then we sort of engage at the end. All right. Thank you very much. Okay. So we will now have the second speaker. Talk is really you can put
Afternoon, colleagues, ladies and gentlemen. My name is Greg Luntfier. I am a wind farm design engineer with a company called SkyTech. It's an independent power producer. Doing my part-time PhD with the School of Geography, Archaeology, Environmental Studies and the Global Change Institute at WITS. My supervisor are Prof. Ranjwa Engelbrecht and Dr. Chris Leonard from UCT. Thanks for the opportunity today to present my research on developing tools to generate wind energy futures considering climate change in South Africa. It's a really good opportunity and I'm really excited about the research. Okay, so speaking of pressing problems, as you may know, and has obviously been discussed and will be discussed at this conference, the largest contributor of CO2 emissions globally is the burning of fossil fuels for energy. Quite simply, my day-to-day work is aiming to expedite methods of moving away from conventional high carbon emitting energy towards accelerating the installation of renewables. As you can see in South Africa, over the past 10 or so years, we're up to about 6.2 gigawatts of installed renewables. Of that, about 3.3 gigawatts of wind that is available on the grid at the moment. So we're all dealing with the struggle for sustainable energy in South Africa on a daily basis. Although we've had low load shedding for the past month with the World Cup, I believe we still need to be wary. There's some risks that we have to keep in mind. the future risks to our energy sector would be a focus on carbon intensive fuels unabated. Of course, the public renewable energy procurement program also had a mishap last year with round 6, where no wind energy projects were actually allocated. And the risk is that we don't recover from that. And the grid access rules that are being promulgated at the moment are not successful. Other than that, independent power producers and equipment suppliers, something we're seeing quite often is that they don't consider wind resource changes in the long term due to climate change. And then, of course, energy meteorology is required to forecast these variable resources in the short, medium, and much longer term, using particularly machine learning methods, computational, high computational requirements, and of course, we need the skills to be able to do that. So here's a brief overview of the research which I'm attempting. The key research questions. So to date, no research and modeling has been done in South Africa to try to quantify the future of variable renewable energy in terms of the systematic changes that might occur to the large synoptic systems that bring wind energy to South Africa. The key research questions that I'm looking at, firstly, what are these systems that bring the most wind energy to South Africa? Secondly, how will those systems change in the very long term? And then finally, looking at adaptation measures and how we can actually develop those tools to adapt in the future. So my area of expertise is wind farm modeling. What is wind energy yield analysis? It's really the process of calculating the energy production potential of a wind farm as accurately as possible. And it has many inputs, such as historical measurement data, digital terrain models, roughness data, wind turbine power curves, losses and uncertainties. And it requires quite strong computational capability as well, especially if you want to look at thousands of possible fictitious wind farms before you end up at the final product. Once you have that information on a time series, you can then map that onto concurrent synoptic systems that bring that energy. I'm well aware that I'm in a room full of climate scientists. So just some of the sort of major synoptic weather types that we can experience in South Africa would be temperate disturbances, tropical disturbances, and fine weather and mild disturbances. I won't go into much detail, so we've only got 5 minutes left. Some of the project results, which I think is the most exciting part. This is the first self-organizing map result for a small part of South Africa, just in the Eastern Cape area, which has a high wind potential. This is really the basis for my first paper, which has been submitted to the Journal of Theoretical and Applied Climatology. The patterns displayed for the top wind energy producing systems are the red outline positions, which point to the tropical and temperate disturbances across South Africa and show patterns resembling this ridging anticyclone off the west coast of South Africa. And then the lesser systems are the more, you would see that high pressure towards the south of South Africa. It's the yellow one in the bottom corner. When we know the most common synoptic systems, we can then map that onto the energy production. And this result is effectively the average ensemble total energy production per megawatt installed for 9 global climate models. And the average is the blue line, and we can see that there's a decline, a general decline in wind energy production in the spatial focus area in the Western Cape. This obviously has a marked knock-on effect on business cases, the internal rate of return of projects, and it's not being considered at the moment. It's not even considered in the loss regime of a non-wind farm. I won't go into too many reasons about why that's happening. We can talk about that afterwards, but in general, you can see that across all the GCMs and even on the ensemble, there's a decrease in the internal rate of return per PPA period. So I've looked at 3 various sort of PPA periods across towards the end of the century. Just in conclusion, what are the next steps? So given the state of South Africa's energy sector, it obviously needs a central, short, medium, and long-term renewable energy forecasting hub to sustain our energy future. These results that I'm proposing can be used in short, medium-term energy forecasting towards a trading market, which has been proposed even in the last week, the first sort of signs of a trading market in South Africa. Guidance for where to develop for wind farms in general, but also the renewable energy development zones, the integrated energy plans, and even when to go offshore. Where to build a grid, as the previous presenter talked about. That's the major consideration at the moment. And the GCI is obviously very well positioned for this further research for the whole of sub-Saharan Africa and beyond. This by incorporating the WITS African-based Earth System Climate Model under Prof. Engelbrecht, alongside other global climate models which are available. But to do this, we will require strong machine learning and computational capability applied in the emerging field of energy metrology, and of course, the skills to do that. So that's my plea to you today. We need these skills in the future. Thank you very much.
Yes.
Good questions. First question. I used to manage the Wind Atlas of South Africa at the CSR. That was my job for a while. It's a useful atlas, but it only shows an annual average. We do have very good high resolution annual average wind speeds. It's an excellent map. In fact, that's what guided us to the area that we're working in. When we look for wind resource, what we're looking for is a stable resource, which is very conducive to a particular power curve of a wind turbine. So you get different types of turbines, class 1, 2, and 3. In South Africa, the class 3 wind turbines are the most common because we have wind speeds in the order of 7.5 to 8 meters per second on average per year. So it's not necessarily just the high wind speeds, it's more consistency of reasonably good wind speeds.
Great, thank you. I just wanted to suggest a new unit for that graph that shows the decline of in energy productivity, which would be the stages of load shedding.
Okay. Thank you, appreciate it.
So what's what sort of level of, I mean, in absolute terms, how does that decline relate to whatever we drop, you know, at the stage 1 or 2 currently?
No, I don't think, well, I mean, that's the whole purpose of the research. And I think the future research, we want to expand this to the whole of South Africa so we can get an order of magnitude understanding of how it will impact our overall energy production. But these are very small numbers, I think, in terms of load shedding. It'll probably impact 1 or 2, I don't know, up to 5% at any one time. But the integrated energy plans also make provision for, I think it's up to 30 gigawatts of wind to be installed by 2050. So it's significant numbers in the longer term. And I think that's where we see the bigger impact as we transition from a coal-dependent grid to a more variable resource energy grid. We're going to need to understand these things much better. Good.
Okay, so next up we'll have Kate Turner. So she will be telling us about damaging winds. Interesting. Okay, yeah. Yeah.
Seems. Let's the content. We have a problem. Let me just reopen this account. It seems to have got stuck. It's not happy with something. Just bear with us, please. It's only your T that we're going to. We have to close this. Oh dear. We run into a technical difficulty, folks. We have to just hard shut down this and then try again. Okay, which one was this one? Eh? Let's see if we can just continue. Voila. Can you swap screen? Yep.
Oh, thanks so much for that. Yes. Okay, so I'm going to be talking about damaging tornadic type wind phenomena classified as land spots over the Western Cape during the year 2022-2023 of the last year. So in the background of that, in the past year, from August 2022 to August of 2023 this year, we've had 5 cases of damaging wind phenomena over the Western Cape, which have been reported as tornadoes by public and our journalists. This is something quite significant, especially over the Western Cape, which is generally not, we don't have all that much severe weather we do get, but however, I think the predominant severe weather is more for the central and eastern parts of the country. Yet we've seen 5 cases of these tornadic type events that have happened within the space of a year. So this has led to further investigations and field assessments and resulted in the confirmation of them being 4 land spouts and 1 being a water spout over the Western Cape. We'll go into the assessment process a little bit later on in the presentation, but in terms of the summary of it, just a table of the land spots that we've identified. I'm not going to go through it in too much detail here, but what I want to say is that we've had 2 cases during last year. So the first one was 13th of August and the next one within September, and then 3 of them within this year, 4th of June and then 25th of August, with 2 cases on that day. So most of these have been associated with cold fronts and 1 with the cutoff flow. So that's also something to take note of. And the spatial distribution of that is mainly confined to the western parts of the Western Cape. So next up is, what is a land spot to start off with? So here I've compared it with the counterpart. It's more familiar counterpart, the tornado. So tornado, as we would all know, is a rotating column of air extending from the base of a cumuliform cloud, which is often visible as a condensation funnel in contact with the ground. Whereas in contrast, a land spout or a water spout mechanism for this is very similar, or the mechanism for a land spout is very similar to a water spout, where relatively cool air is passing over hot ground, which produces updrafts and cumulus clouds. These then random swirls can be caught up in the updraft and so tighten up into a funnel and made visible by the raising of dust. So coming then from the ground up to the cloud instead of the cloud coming down to the ground is the basic difference between a land spout versus a tornado. So how rare are these events? So it seems to be that these frequencies increasing. We've had now 5 in the space of a year. But that then begs to question, is this climate change? Or is it merely that we are observing these events more frequently now that we have more access to social media? Is it possibly a combination of the 2? Is it possibly increase in population that we've had over decades, which could be another factor as well? Or on the flip side, is the frequency increasing at all? Is it just that we haven't noticed these in the past? Going into some historical cases, again, don't want to be going into the table too much in terms of the detail of it. It's merely to show that we've had some 29 cases that's documented in the Western Cape upon doing some digging. And the oldest of that report was backdated to 1905, September 1905, where we had first landspout in Malmesbury in 1905. But yes, then since 2000, it's on average that you have about one event per every 1.5 years. So that's then occurring most often, also looking at the data, most often occurring between August and September with 31%, and in December and January with 27% of these cases that have been documented. Again, the dominant weather systems for these that we have data for is cold fronts and cut-off lows. And then the highest number of events is again for that West Coast district. I'll put on a map to just show where those locations have been identified. And again, most of those cases are in the western parts of that Western Cape, over the West Coast district, as well as the city of Cape Town, with 31% and 21% of cases. Going into the formation of how do these landspouts form in very brief terms. So requirements for a landspout is wind convergence line that forms small scale eddies. As these convergence lines or wind converges, it creates eddies at the surface, small scale eddies, where then an updraft of a cumulus cloud then comes and passes it and coincides with that eddy. It pulls that eddy up into that updraft, creates a vortex, and actually then starts to develop a landspout. There's a schematic at the bottom that also to show that a little bit easier to understand then. And then going on to the assessment process for how did we assess these landspouts. So it goes into 3 phases: pre-assessment, the field assessment, and then the post-assessment. Whereas pre-assessment, it is verifying the authenticity of those reports. We're getting reports from public and our journalists, disaster management, and it's always vital to be to verify that authenticity because we're getting a lot of fake news. So then ascertaining specific times and locations, meteorological conditions of that to verify was there even cloud to start off with. All of those type of things will then be helped to analyze that meteorological conditions. Then it is crucial to be acting quickly once we get those reports in, to get a team out within 2 to 3 days of that. Otherwise, that damage would have already been mocked up. In terms of field assessment, it is then eyewitnesses, interviews with eyewitnesses, asking them specific questions of, is it rotating? Where did it start? These are just a few examples of questions that we would ask. Was there thunder and hail, rainfall as well? And then to look at the damage itself in terms of, was there any rotation? Is there evidence of rotation on the ground? Were there trees that were twisted? Was there the evidence of any rotation that you could see on the ground? And then to try and determine width and the length of that. Finally, in post-assessment is to assess all of that evidence and to determine a EF scale or the strength of it in terms of the EF scale, writing a confirmation report and then publishing that thereafter. I'm just going to go into a quick case study of the 25th of August of this year. We had 2 landspouts that developed over the city of Cape Town. The first being over Hanover Park, which is Cape Flats, around 7:30 in the morning. You can see that left map of city of Cape Town. The bottom location is Hanover Park. The next landspout was over Morningstar Airfield at 10 o'clock in the morning, which is denoted with the top star with an M as well. So that morning, a cold front passed during the course of the morning, as you can see from that satellite image. Then in terms of the skew on the left-hand image, there is fairly unstable conditions in the lower and mid levels, but that cloud would have been capped by around about 500 hectopascals, which is about 18,000 feet, or just below that, and quite strong winds in that low levels as well. You can see even a northeasterly direction at the surface here at about 10 knots. That picked up later on very strong to a northerly northeasterly knot of about 20 knots, but just above that surface that increased to a northwest of about 30 knots in that low to mid levels. And the two satellite pictures on the side, there's both of them showing the satellite images at the time of those land spots. With Hanover Park, you can see a band of showers that are passing over the Cape Town area with decent showers, but also nothing that you would expect any severe weather from. These are more insignificant cues. They are not, we would never have flagged this as cues that would produce severe weather. Then in terms of the wind field, the surface winds for that morning for Hanover Park. So the morning on the right-hand side, we've got Cape Town International's wind observations, which is very close to Hanover Park, and started off in the morning with a northerly wind about 22 knots, gusting up to about 30, and that was persistent for most of that morning up until 5 Zulu, where we had also 20 knots gusting 30. And from that main general flow of that morning was mainly a more of a northwesterly. So our station in town, in the CBD in town, that was giving us a northwesterly wind direction at about 340 degrees, also around 20 knots. So in terms of that, that's then giving us not a classic case of convergence line, but something in terms of convergence over that Cape Town International almost area. And that's maybe an idea of why that land spot developed in that area. And then just going in terms of some damage pictures to show you what happened on that day, and some roofs that were blown over, houses that were also pushed over. The one image of that land spot on the right. And then in conclusion, these are small-scale features that may even be more unpredictable than tornadoes, but still have the potential to cause considerable damage. These are often under insignificant cumulus clouds over a convergence line of sorts. They're most often occurring in your spring and summer months and associated with cold fronts and cut-off lows. The higher frequencies of these events have been displayed over the western parts of the Western Cape as well. And we should be looking into more research to understand this phenomenon better, and maybe in the future, in the distant future, be able to alert or warn for these type of events. Thank you.
Thank you, Katie. It's clear that there's a lot of research needed on this. Luckily, I'm busy with it. But what I want to ask you, you look at the damage and you look for turn. And then you look at the satellite image and you see there weren't some significant convection. And from that, then you deduce it's a water spout, not a tornado.
Yes, so for a tornado, you're looking for a thunderstorm. You're looking for more severe type of thunderstorm that would be then causing a mesocyclone to develop underneath it. So that would give you evidence of a tornado type formation. Where these are insignificant cues, there's nothing that would suggest severe weather for that day. Nothing in terms of the other models. I've just shown you a brief outlook of what the models were showing here, but it was not an intense cold front. It was a decent cold front, but nothing severe. And from the eyewitness reports, most of them would have said that they were then from the ground up to the cloud, and that's the thing. Also, the reports from the eyewitnesses would have said that there's no lightning, they didn't hear any thunder, they didn't have hail, things like that as well, would also give you an indication that these are not well-developed thunderstorms.
Get some. So we didn't consider getting to
That would be amazing if we can do that. I think at this stage, we are in the very initial phase. We just seen these reports over last year. So this is just sparked that first initiation of some research, but that's hopefully something that we can look into for the future. Thanks.
Yeah, I would also now like to introduce our next speaker, Sia Bonga.
Thank you so much, Shem. Can I start? All right. Hello, ladies and gentlemen. My name is Siabonga. Alongside me, working with Unosi Pozwani, and we are looking at the comparative study of the effects of climate change across 4 provinces along the western and eastern coastlines of South Africa. So the data sources that we'll be utilizing for this research are from the 75 that are based on the RCP 4.5 and 8.5 scenarios. With regards to our time frame, we'll be looking at the near future time frame that spans from 2035 all the way to 2065. And with regard to temperature impacts, both RCP 4.5 and 8.5 scenarios indicate a consistent increase along the coastline, with our RCP 8.5 suggesting a more severe temperature rise. With precipitation patterns as well, we see a notable difference in precipitation patterns that are observed, with higher precipitation rates along the eastern coastline and dry conditions on the western coastline. So our study area will be looking at the entire southern coastline with provinces, namely Northern Cape, the Western Cape, Eastern Cape, and KwaZulu-Natal. The study focuses on assessing the impacts of climate change on South African coastlines, covering 4 provinces. So for our data and methodology, with regards to historical and projected data, this study utilizes data from 9 global climate models with historical data that spans from 1976 to 2005, while the projected data covers the period of 2006 to 2095. The emission scenarios, as stated, we'll be looking at RCP 4.5, which represents moderate mitigation efforts, and RCP 8.5, which represents low mitigation efforts. And then our ensemble of high resolution models, they're all based on the analysis of multiple coupled atmosphere ocean general circulation models. And we use the RCA4 model, which is our primary tool to assess the climate change impacts of the study. So the member ensemble mean of average annual total rainfall and the temperature mean have been compared with the observational fields. So for the precipitation, we use the Global Precipitation Climate Center. And for the temperature analysis, we'll be using for the temperature, we'll be using the NOAA land temperature analysis. So we do recognize the fact that we acknowledge that the regional models may offer a different perspective with regards to climate change effects, but the RCA model was used for this analysis as it forms part of the CODEX, the Coordinated Regional Climate Landscaping Experiment. So these are the list of the 9 GCMs that we've used with all from the respective institutions. So looking at our results, for RCP 4.5, the annual mean temperature, we observed a coherent pattern that emerges alongside the coastal areas. Whether it's positioned on the east side or the west coast, they all show a uniform exhibition of a temperature surge of about 1 degree Celsius to 1.5 degrees Celsius. Notably, this consistency prevails regardless of the specific coastal orientation. For RCP 4.5 annual percentage change, we saw that the Eastern Cape stands out with a substantial decrease in coastal precipitation compared to other provinces, registering between -10 millimeters to -20 millimeters for the majority of the coastline. In contrast, KwaZulu-Natal coastline sees an increase in precipitation that is relatively to other provinces. So despite the shared eastern coastline, these provinces do showcase this similar shift in precipitation trends. On the other hand, the Northern Cape and Western Cape coastline display similar trends, where both respective coastlines indicate a decrease in precipitation rates of between 10 millimeters to -5 millimeters. So overall, both coastlines of the respective provinces are generally getting drier under the RCP 4.5 scenario. For RCP 8.5, the annual mean temperature, similar to RCP 4.5, the projected temperature increases across the respective provinces as they align with each other. So for all 4 coastal regions, we see an increase of about 1.5 degrees Celsius to 2 degrees Celsius. So however, the RCP scenario does have follows a more extensive increase when it comes to temperatures. Respectively as well for the RCP 8.5 annual percentage change, we see Eastern Cape witnessing a significant decline in the precipitation rates, whilst KwaZulu-Natal witnesses an elevated precipitation. The Northern Cape coastline seems to be getting drier under RCP 8.5 as compared to the Western Cape coastline, where the precipitation rates for the Northern Cape coastline, they fell between -10 millimeters to -20 millimeters, as opposed to Western Cape coastline, which fell between 0 millimeters to -10 millimeters. So in conclusion, we observe that the climate projections under RCP 4.5 and RCP 8.5, they do indeed present distinct features, where RCP 4.5 offers a more manageable climate outlook, but still requires proactive adaptation strategies, in contrast to RCP 8.5, which possesses considerable challenges and demands a more comprehensive climate action. So the importance of studying the CIMIC 5 climate trends, we observe that the CIMIC 5 climate trends still remains crucial for informed decision-making and effective mitigation strategies. So the findings can definitely contribute to economic and societal growth through disaster preparedness and resilience. So our limitations and contributions. So while the study relies on selected climate models, it contributes valuable insights to climate change impacts in South Africa, and it also aids with decision-making and policy formulation. So our future work, we are in the process of transitioning to CIMIC 6, as it is the latest that has been released. So we'll be looking at, I'll be looking at projected changes in precipitation and temperature extremes under the global warming levels over South Africa using CIMIC 6. So the transition to CIMIC 6 stands vital for gaining a more comprehensive understanding of climate change, its socioeconomic implications, and for facilitating informed decision-making and robust mitigation strategies. So our transition to CIMIC 6 does not necessarily offer a critique to the previous generations, but it does stand as a testament to the dynamic evolution of climate models. So expected outcomes for CIMIC 6, we are expecting outcomes that include a more enhanced understanding of regional climate change patterns, improved projections for extreme weather events in South Africa, and data to support evidence-based decision-making at local and national level. Thank you so much for your attention.
Um, um, uh, Dynamic evolution of models. Now, we have to confront the reality that at some point, our obsession with forecasting predictability on all time scales really, you know, everybody has different models, a lot of models, it's just a lot of data, but there isn't a lot of information. What aspect of dynamical evolution is relevant for your study from SIM 6 that you don't have in SIM 5, which is not there, right? So yeah, what because I'm just trying to invoke a conversation about our obsession with evolution of climate models and all that. And actually, I want us to come to a point where we say, I want this feature of a model. I'm waiting for it, right? So yeah.
Yeah, no, definitely. Thank you so much for your comment. It's actually a good critique, actually. I came to this presentation knowing that I'm using 75, which is I don't want to say outdated, I don't want to say obsolete. It's basically a continuation or an addition, right? So I'm well aware of the SINIP 6, that is SINIP 7, that is currently on the way. And yeah, so we still working on SINIP 6. We're still gathering the data. We are still trying to work on the downscaling and all of that, right? So the main reason why I couldn't do the SINIP 6 was because of the lack of resources, but I didn't want that to stop me, right? So, but yeah, I'm well aware of the fact that it's still evolving, and yeah, we'll definitely try by all means to get along with the times. Yeah, so that's a very good critique, and yeah, thank you for that.
Yeah, okay. Any other questions? Yes.
It's more a comment than a question. I think instead of giving rainfall values, rather give it as a percentage change. For example, instead of saying 10 millimeters difference, give it a percentage, because 10 millimeters on the West Coast versus something which is much greater on the West Coast is two different things. So I suggest doing percentage change.
Thank you for that answer.
Thank you. I think in addition to, I think it was Rossi, I think there is an importance of messaging, not necessarily focusing on the mean change, and sort of, that this is the Darius drawing. So, sort of really building that awareness that there is uncertainty, and it has to end, that information has to land into a sort of risk-based evaluations of future impact and adaptation and so on. So I think that's what I wanted to bring up. Yeah.
All right. Thank you so much.
I can get it to work, which is now. Computer surprising. With me, please. Now, with me. Second ticket. When I want, the computer is just frozen with me.
Hi everyone, my name is Hi everyone, my name is Patrick Martineau. I am a researcher at the Japan Agency for Marine Earth Science and Technology in Japan. Before beginning the presentation, I want to thank the organizer for accommodating my online presence this time. In this presentation, I'm going to be discussing of a seasonal rise in subweekly temperature variability that is going to affect southern hemisphere land masses, as observed in reanalyses and CMF6 model predictions. Synoptic scale weather systems, such as cyclones and anticyclones, through their development and motion, produce temporal fluctuations of weather observables, such as temperature and precipitation, when observed from a fixed geographical location. And concerning temperature fluctuations, or in other words, variability, they have been shown to be associated with the frequency and severity of weather extremes. Given the important socioeconomic impacts associated with these weather extremes, it is important to understand the processes that regulate temperature fluctuations and their trends. So concerning future trends, synoptic mid-latitude temperature variability is overall predicted to increase in the southern hemisphere. This has been shown by Schneider and co-author. In their paper, they have shown predicted changes in the CMF5 models. So overall in the southern hemisphere, there tends to be an overall amplification of temperature variability, but this is highly spatially inhomogeneous since both sectors of amplification but also weakening are observed. Concerning changes that will have a greater socioeconomic impacts, these include projected amplification over South America in austral summertime, and also predicted amplifications affecting South Africa in the southern coast of Australia in austral wintertime. And these have been associated largely with regional modulations of the meridional temperature gradient, or in other words, the large-scale atmospheric barometric density. And concerning the DGF changes, they have been shown to be accompanied or due to an intensification and poleward shift of the sector of maximum variability, and also an amplification of both cold and warm anomalies. Now, concerning the agreement between reanalyses and CMF6 models concerning the trends, it has been shown recently by Chemke and co-authors that over the satellite era, the eddy kinetic energy, or in other words, the wind variability, has amplified substantially more in reanalyses compared to what is modeled by the CMIP6 models. And based on this result, it has been assumed that CMIP6 models are biased. However, it is not known if reanalyses are reliable concerning synoptic variability in the southern hemisphere, because compared to the northern hemisphere, observations that are assimilated are relatively sparse. Also, the agreement between reanalyses and CMIP6 models concerning temperature variability, especially near the surface, has not been documented. So here we ask whether temperature variance is subject to similar biases as is observed in the eddy kinetic energy. So to answer these questions, we are going to have a look at the budget of temperature variance. The main quantity we're interested in is the subweekly temperature variance. To extract the subweekly component of variability, we are first applying a 10-day high-pass filter with the temperature field. And then by averaging the square of this quantity over each season, we can obtain its variability. This is evaluated at 850 hectopascal, and it is evaluated in 3 reanalyses, MERA2, GR55, and MERA5. And in this presentation, I'm going to show multi-reanalysis ensembles by averaging these 3 reanalyses together. Now, there are many source and sink terms for this subweekly temperature variance. Here we are going really to focus on one of these terms. That is the dominant generation term. We call it the horizontal component of generation. And this component is function of horizontal fluxes of heat that are produced by the subweekly eddies. Physically speaking, it is representative of baroclinic energy conversion, that is a transfer of energy from the seasonal mean circulation to the subweekly temperature variability. First, we will compare and contrast trends in temperature variability as observed in reanalyses over the satellite era with those modeled by the CMIP6 models for the same period. Here we are considering 27 models included in the CMIP6 project, for which these scenarios are available. The historical scenario, the SSP2 4.5 scenario, which we can consider to be more realistic, and the SSP5 8.5 scenario that we can consider to be a worst case scenario. In this figure, trends are shown with the red and blue color shading. And for reference, we show the climatology using the black contours. So looking first at reanalyses to the left, what we see is that there are some important trends observed to affect South Africa in both June, July, August, and also September, October, November. In contrast to what is observed in reanalyses, what is modeled by the CMIP6 models is much weaker and also tends to be more spatially inhomogeneous. Nonetheless, the models also actually denote an amplification of temperature variability affecting South Africa in the same 2 seasons. Next, we are going to have a closer look at the trends and their uncertainties. First, looking at the satellite era, what we see is that there can be important biases between reanalyses and CMIP6 models in consistency with the previous slide I have shown. So for instance, in June, July, August, while reanalyses show only modest increase of temperature variance, the CMIP6 models actually indicate much larger amplification. On the other hand, in September, October, November, now it is the reanalyses that capture a much larger amplification of temperature variability compared to the CMIP6 models. I want to point out the fact that in almost all cases, the multi-reanalysis mean is included within the large range of trends captured by the many different CMIP6 models. Now, concerning future trends, when we look at the SSP5 8.5 scenario, we see very important projected trends to affect South Africa They include an amplification of 4.6% per decade in June, July, August, and an amplification of about 2.3% per decade in September, October, November. Concerning the dynamical mechanisms responsible for these trends, here we have a look at the role of changes in the dominant generation term of temperature variability. So as I mentioned earlier, this term is function of subweekly fluxes of heat that are against the seasonal mean meridional temperature gradient. Again, we compare these changes among reanalyses and the CMIP6 models over the satellite era. Overall, there is a good match between changes in this generation term and the changes in temperature variance that I have shown earlier. Again, these changes tend to be weaker in the CMIP6 models compared to the reanalyses, and they tend to be more spatially homogeneous. Nonetheless, we see that both reanalyses and CMIP6 models agree on positive trends affecting South Africa in JJA and September, October, November. These trends are actually largely due to changes in the background temperature gradient over time. Again, comparing reanalyses to the left and CMIP6 models to the right, we do see that in the same 2 seasons, when we observed an important amplification of temperature variance, JJA and SON, we do observe an important amplification of the background temperature gradient in the vicinity of South Africa. Again, these changes are weaker in the CMIP6 models in comparison to reanalyses, but there is an agreement for an amplification of the temperature gradient affecting South Africa in the same 2 seasons. So in summary, we have documented important biases in the trends in temperature variability between the reanalyses and the CMIP6 models, in consistency with the biases documented by Chemke and co-authors in the eddy kinetic energy field. So the trends in CMIP6 models tends to be weaker and more spatially homogeneous compared to the trends in the reanalyses. Something I want to stress here is that I believe we should not hastily conclude that the models are inadequate here. Some points to keep in mind are that reanalysis trends are within the spread of CMIP6 models. And also the reanalysis ensemble mean contains internal variability, whereas the multimodal mean largely excludes internal climatic variability because we have averaged so many different models that each contain their own respective internal variability. So the difference between reanalyses and the CMIP6 models simply could be due to the fact that there is some internal climatic variability present in the reanalysis record. Now, concerning future trends, we have seen that there are very important positive trends predicted by the CMIP6 models to affect South Africa, especially in June, July, August, with a very important amplification by about 4.6% per decade. Concerning the dynamical mechanisms, the observed and projected trends in temperature variability are largely due to trends in the horizontal temperature fluxes associated with a strengthening of the meridional temperature gradient. Okay. So thank you very much for your time. I will be very happy to answer your questions and hear your comments.
Francois, I think I need to get hold of microphone. I need to be able to hear you. Patrick, I hope you can hear me.
Yeah, I can hear you. The sound is a little bit choppy, so if you could please speak
Thank you
very
very
close to
much,
the
Patrick,
microphone.
for joining our conference from far away.
Thank you.
So on that last slide, you've summarized and you've reported an increase in the meridional temperature gradient across Southern Africa. So mechanistically, how do you interpret that in the context of the Southern Hemisphere temperature gradient over the Southern Ocean getting weaker? So in the CMAP6 models, because of the polar amplification, of course, the general understanding is that the meridional temperature gradient over the Southern Ocean is getting weaker, and the frontal systems are consequently displaced towards the South Pole. So what would be the mechanisms resulting in this increase in the temperature gradient in the Southern African region?
Yeah, that's a very important question. So when we look at the climatology of temperature variability, we found that in GJA and SON, there's really like a local maximum of temperature variance just over the southern coast of South Africa. And this maximum is due to the land sea temperature gradient. You cannot hear me?
Okay. Almost. Is it coming out?
Can you?
Yeah. Patrick, we can't hear you.
You cannot?
Yeah, we can't hear you.
Can you hear me now?
Yeah, sorry, Patrick, we can't hear you on this side. We can see you talking, but we can't hear you, unfortunately. That's a good idea. So Neville says you should write us an email, Patrick, and we can read your answer tomorrow to the conference. Thank you very much. Thank you.
Okay, thanks everyone. We're done for the session. So I just wanted to say the afternoon tea is a working tea because it is also our first of our 2 poster sessions. So please get something to drink and then come and engage with all the different poster presentations. But linked to that, please, if you are doing a poster, please make sure you hang it up. There's currently only 7 out of the 13. So, and we are starting, I don't have the program on me. I think it's past. I think it's at past. It's at No. I think it's 3:30 though. Yeah. And we start again at 3:30. Oh no. So you don't get that much time, right? You just need it. Rid of the folder. But I'm not sure how they've been doing it in here. In the other room, they got an open folder. Yeah, I'm sure. Oh no. Okay. Okay. Gosh. Oh, yeah. Oh, just look at that thing here. Um, Put this slide back. Sorry, no problem at all. Send it to my email address. Then the 426-9088 at my UWC
Great, I'll send that across now. Sorry about that.
Thanks. No problem.
Oh, yeah.
Pamela, and then talk. I am missing one of them. I'm not sure. I don't know the program.
Hello. There are three talks after the panel, and one is by somebody's name, who's I can't pronounce the first name. The second name is Maviza. What person is there?
Can I?
Your talk.
Thank you.
This is one time.
Okay. Now there's 1, 2, 3, 4. Yeah, got it. Okay, so some of us were lucky enough to attend the WCRP's Open Science Forum in Kigali, which was, from what we hear, a very significant event and a very good conference. Apparently, it's held once every 10 years or so. And it was really an important occasion, I think. And, you know, ironically, in this year, which you saw this morning in the president's presentation, such a significant year for the climate, seeing all these exceedances and these new records. And there were several elements, and the panelists who are here are not everyone in the room that was at the conference, but they are representing 4 elements of it. One is the dynamics, the climate dynamics. One is about air quality. One is about modeling, and one is about seasonal forecasting. 4 elements of the conference. And so what the panel is going to do is just give initially their impressions of each of those particular elements of the conference. And then we will see if there's anything that they talk about which we think is important or is significant, which we can interact with between you and this panel. So we will kick off. I guess I'm going from left to right. If you're ready, Thando. Yeah, please come and use the mic. Thanks.
Good afternoon, colleagues. So as Neville had said, so my interest in a conference like that one would have been issues of climate dynamics. Even though I'm personally not a climate dynamicist, I may want to be a weather dynamicist. But climate dynamics is the most relevant issue. And then the other one that really caught my eye, which I thought was extremely important, Francois mentioned it earlier, the issue of attribution. I'm not going to go into the modeling of it. You can talk about that, Francois, but I think that the issue of attribution is a fairly urgent area of climate change work that South Africa really needs to go into. But I'll start talking about the attribution first. Now, the reason why one of the things that I didn't know I had for the first time there was that attribution is now sort of like operationalized or near real time. Why is that important? I think it's important because people need answers about extreme weather events that are being experienced, whether they are caused by climate change or not. That is important, in my opinion, to know, because then people can respond to things like early warning systems with the confidence of knowing that these extreme events are becoming the new normal. You know, and if an extreme event has occurred, and it's likely therefore to occur soon again, because you know it's happening in the backdrop of the climate change issue. And I think also that's important from a policy point of view. I think if the governments, and in particular our own, knows that these events are caused by climate change, that will, I think, accelerate issues of funding that needs to be galvanized in order for adaptation strategies to be implemented with speed. And then the second one, of course, is the issue of climate dynamics. I think that in South Africa, we are doing a lot of work in climate change work, as we know. We're doing dynamical downscaling that Prof. Engelberg is leading. We're doing statistical downscaling that is an activity at SASAS and so on. But what we are missing is an understanding of the climate dynamics that lead to the changes that we see over South Africa. I think that is important to do, not only because it is scientifically important to do those things, but also because once we know why we see the changes that we see, that, in my opinion, will build confidence in the models that we are using to try and see what the future looks like. Okay, so those were the two main points that I wanted to raise.
So Rebecca, you're up next. Going to talk about some of the air quality issues, or well, we'll find out. See.
No, thank you. Thank you for the opportunity to speak. I also have 2 points when I was reflecting on this and what could be interesting to the SASAS community. So I said about air quality because when people, ask me how WCRP was, I'm like, well, it's a little to the side of what I do, right? I do atmospheric composition and air quality work, and they're very linked to climate. But the WCRP I found was very focused on climate modeling, climate services. And there were very few people there focused on what I would call even atmospheric composition beyond carbon. So there was a lot, and the areas where it was focused was the land atmosphere exchange, but again, a lot with carbon, some trace gases, some also looking into, impacts of biomass burning aerosols, but I had to kind of find those people out, and it was the people I already knew really who were doing that work. So I think, as a atmospheric scientist and atmospheric chemist, it was a little bit to the side. And I think that that's something we should think of as a meteorology, climate, researchers, that these trace gases, aerosols, we know they're very important, but when they're not highlighting very much at a climate conference, so there's just very few speakers, very few sessions that I found, at least, that is an area for growth. And a lot of it is, of course, because they're very expensive to put into models. But I did speak with one of the modelers at NASA that they have, new aerosol cloud microphysics that they're testing out. Another modeler who had put together some nitrogen biogeochemical cycling coming out of the CMAP models, thinking, how can we put this information in? So I did think that that was quite interesting. The other point that I wanted to make, and also what I didn't really see a lot of was talking about future scenarios. And when we think of future scenarios, how do we also think about the impacts on climate, but also on air quality, and how we mitigate and decrease the emissions from both of them? But the other aspect I wanted to bring up that at least I noticed, and I think when I said SASAS the most, when I was talking with people, is there seemed to be a great need, and very much from the researchers in the global north, to have communities to reach out to when they wanted to do work in Africa. And unfortunately, I also heard proposals of developing networks like this. And I say unfortunately, because they also were coming from global north scientists, so not people based in Africa. So there seems to be a need. There is some interest in that. I noted that SASAS exists, and that SASAS exists as a great place where we have collaboration across institutes, the Weather Service, academia, and so on. And so that was a really strong example. And that, we should use existing networks that are led locally to kind of fill some part of that need as well. So I think there's some interest from what I've heard of going forward to some, African climate I don't know what the word would be for network, but with that, I would just really hope that I would think SASAS could play a role, because we already know how to do it. And we've done it for how many? Is 37, you said, conferences? And that it's not really driven from people who don't live on the continent.
Thank you. Thank you. No, absolutely not. I refuse to be, put in the box of seasonal forecasting. I'm a jack of all trades, master of none. Yes, I dabble in seasonal forecast, but I also dabble in attribution and climate projections. I don't touch weather nor the atmospheric chemistry, but I do modeling and statistics and a lot of this stuff. So no focus on seasonal. And besides, there wasn't really that many sessions or talks that were focused on seasonal forecasting at the WCRP conference. And what I wanted to bring up really is that I think that I might be the only person who actually participated in the first and the second WCRP conference. I've been there in Denver in 2011 at the first one. When I was there, there was this initiative of creating an African desk of WCRP, and we summarily walked off from the room. That called a bunch of people from Africa, because it was are relatively sort of top down, relatively arrogant, relatively like, okay, we organize you, and this sort of thing happening there. And the most striking aspects of this conference is really the change of tone, is the change of rhetoric, is the change of words that are used. Not always, not 100%, but there is a much stronger recognition of the African researchers or global South researchers in general, having a voice and having a contribution, a meaningful contribution to global climate science, and trying to recognize it. So that's what struck me during the conference, really. So in general, if I were to sort of give a couple of my thoughts and thoughts shared by my colleagues, so I have a couple of points there. So, for example, one significant element there was that there wasn't that much blue sky research. It wasn't like a research for research sake. There's a few sessions, a few talks. Quite a lot of, most of the talks, most of the sessions had a very strong application angle, a very strong climate services angle, had a very strong sort of actionable climate science angle. And even if it wasn't in the talks themselves, then it would have come up in the questions. The people were engaging in this pretty strongly. So when things like very esoteric things for us climate scientists, things like ethics and values of climate science were coming up quite often. An important thing that I've noticed that there was sort of a pushback against, for example, SINIP 7. Or initiatives such as EVE. That's one of the bigger European funded projects that is coming up, the computing projects also. And the pushback came from the sort of utility of this data for actionable, for actions on the ground, with actions at the country level, at the policy level, at municipal level, at the village level. I don't think that there is a the climate service community. Climate services community, I don't think that there is a recognition of the need for more modeling. It's really, making what we have at hand being communicated better to users of that information, and developing those links and filling those gaps. So that's the messages that I've seen. And in terms of sort of this, coming back to this global north, global south dynamics, what sort of emerged there, what I've seen is the sort of recognition of the need for us to start defining agendas. So not sort of follow European or American funded projects, but decide about how those projects are, what they focus on, and how we play the role in that. And what I wanted to say about this. And yes, that was it. Okay, thank you.
So to summarize, thank you to my colleagues for the excellent impressions. I would say this was a really positive experience to be in Kigali. There were about 700 attendees attending this conference, and another 800 or so online. So as Piotr has indicated, this conference is held only once a decade. It was wonderful that Africa was chosen as the venue of the conference this time. So my impressions were, firstly, in terms of modeling trends, to just report on that. I think there are two things we should take note of that are happening now internationally, and we run a risk here of falling behind. The first is that machine learning applications within climate models have exploded in the last 2 years. And maybe the single strongest trend, just to give you one flavor of what was discussed, is that very high resolution models that are run, say, globally at a resolution of 3 kilometers for 10 years are now being taken as the truth for machine learning methodology. So the machine learning techniques are trained to reproduce these 3 kilometer simulated global climates. And that is then applied to generate large ensembles of, say, 3-kilometer resolution global climates. That's one of the main lines being investigated. There are several others. For example, and another one is called equation discovery. So you apply the machine learning method to learn the equations that govern cloud microphysics, for example. Currently, those types of results are empirically pursued with some observations we have. Now, the machine learning methods are used to do. So, remarkable growth. I don't think we are active enough in the field. It's a new technology. Nobody is sure exactly what it's going to offer. It's completely unclear what exactly it will do within the climate models. But the last thing I'll mention is that there's some evidence that at short-range weather prediction timescales, in terms of predicting circulation, with ERA 5 being the benchmark, there have been talks that are claiming that these short-range predictions are already beating the ECMWF forecast. But it's in terms of circulation. And the methods are being trained towards the ERA 5. So there are some ifs. But exactly how far will it be able to go in terms of medium range forecasting, seasonal forecasting? The methodologies are currently being applied across all these timescales. There are huge issues, questions around reproducibility of the results, data leakage from the testing to the verification phase. One shouldn't believe everything you see right now in terms of machine learning produced results. But the point is the field is really growing. What are we doing as SASAS? And the second modeling point is these convection resolving runs, simulating global climate at 3-kilometer resolution or over a region at 3-kilometer. We are struggling to compete right now in South Africa because we don't have a high-performance computer that is functional. Currently, the Lengal cluster of CHPC, which was actually able to do this type of thing, is being slowed down a lot by power cuts. So we have huge technological issues. We run the risk of falling behind the field of so-called convection permitting modeling without a proper high-performance computer in the country. So that's another concern. I'll conclude by just saying I think the colleagues are correct. There's a wonderful amount of goodwill right now for the Global South, to reach out to the Global South. But of course, we need to be very clear that it's nice for the colleagues to come and help us, but it's just, they shouldn't have the attitude of coming to help us in the South, right? We need to show strong leadership in terms of our science. And then with equal partnerships, we can benefit a lot from the colleagues in the Global North being so keen to support us with our science in the South.
And misinterpret what was said so that we can get some conversation. Okay, so really interesting. If I can, first of all, I heard a little contradiction here between the idea of, and I think Francois just mentioned this idea of how do we connect up what we are doing with what's happening internationally, what opportunities, how do we break down those boundaries in a way that is genuinely empowering for us, enabling for us. I think Rebecca mentioned that there are people looking to work with others. Chipper mentioned that that there's a change of rhetoric and recognition. That there's a kind of an opportunity for an African SASAS type organization. I'm very surprised to hear that because I'm sure that there have been many efforts in the past to organize African climate science in the past. And I'm surprised to know that it doesn't exist or it may have lapsed or something. And of course, we have a big diaspora of African scientists that we know about. So that's something we need to really rethink strategically. And also South Africa's role in this is always complicated, as you all know. So that's one thing I'm a little bit confused about. There's goodwill, there's a need, there's an opportunity and the right attitude. How do we capitalize on that? That's one thing. Attribution issue is very interesting to me. Now, I don't know if we have time to discuss that now. Thando, I mean, why we need to attribute and how long we need to attribute for until that becomes a given, you know, and that we need to move on from that point. I'm interested in that. The air quality and the seasonality, I'm surprised to hear that those weren't more central topics, especially given that you said this is all about application. And I'm one of those that is convinced that the seasonality is so important and the extreme events and the exaggerations of seasonality is so important because that's how it manifests. That's how climate change, we saw it in September, in August, in June, those are the manifestations, and how seasons change. I won't go down that road. We know that know that's where I think it's all at. And then this final point about the AI. So I mean, you only said a sentence or two, and I'd really like to know more about the machine learning AI approach, and really, what does it mean? Are they just better at running? Is it just better algorithms that do things that people can't think? Is it the speed at which it's done? And then finally, just to think about the idea of the CHPC and our challenges there, which are obviously an impediment to progress. We need to find a solution. And if the solution is not in the country, then we need to collaborate, which maybe ties it all together. And that our demand for computer time is in fact met overseas and not here, maybe. So those are my points from your points. Let me see if there are any, first of all, any comebacks on what I've just said. If there are, please do. And then we can open the floor. So anything you want to respond to in what I said? If not, then Francois, you look like you want to say something.
I think on the issue of attribution that you raised, the question that you raised, I think we should think about this, on an operational basis. I don't know how feasible that is because it's quite an expensive undertaking. But I think attribution should be an operational imperative, because it would impact uptake of early warning systems. I think it will do so directly.
Coming back to this attribution thing, there is, that one has to realize that I think attribution is really underestimated as a sort of concept that brought the awareness of climate change to the public. It's in the last 10 years. I mean, what we see in the newspapers now, I mean, it wasn't there 10 years ago, 2010, 2011. That, I mean, you would perhaps have once in a week or once in 2 weeks time, some sort of information about some sort of extreme weather event. Now we have them 3 in a day, coming from all sort of, and most of them, they are accompanied by attribution statement. And, the fact that press accepted it, then, means that basically everybody accepted climate change. Though surely there are denialists still, but, we are in a different space now. And I'm convinced that it's, 99% due to attribution studies. And there are, coming back to sort of operational attribution, there are initiatives out there that NASA is developing their system. ECMWF is developing their system. There is that group that I take part in. This is called World Weather Attribution. We were talking last week about setting up an African desk and doing, because the issue with this attribution now is, I'm receiving like 2 or 3 invitations a week to undertake an attribution study somewhere in the world. And how we undertake those studies, it's basically if there is 2 or 3 people who are willing to commit time to do a particular case. So, for example, in case of the Western Cape cataflow from September, was it? Yeah. I mean, there wasn't particularly, nobody was interested apart from me. So we didn't do the study. So the idea there is really to do a systematic evaluation of most of the extreme events on the continent. That would, as my colleague mentioned, that should inform the uptake of early warning systems and general awareness and the need for action and the need to start taking these things more seriously than we already do. So that's the advanced game. Thank you.
I'm going to reflect tomorrow in my talk on African attribution systems. But I agree with Tanya and Piotr that it's another very key field that is growing in prominence. Its heyday is not yet over. And then just more generally, Nero, in terms of your comment, in terms of coordinating African research efforts, there certainly has been many such efforts over the years. I don't think we have to solve in this panel what the right way forward is, but I'll just point out on the positive side to comments that there is a very, very strong effort from the IPCC, the World Climate Research Program, and the World Weather Research Program, and the WMO to improve the representation of the Global South in all their expert groups. So if anyone is interested in joining that effort, visit the websites of those three WMO organizations, WMO itself, WCRP, WWRP. Look at the expert groups. Every year there's a call. They are making a concerted effort to make the expert groups representative, which is really positive for us. That's one way for us to influence the international time.
So there are two themes that have come out of this conversation. The one is about contribution, the other is about how African and global South scientists can become more involved. Those are two discussions, the latter of which I think is a strategic question, which we should find time to discuss. Again, South Africa leading these processes is complicated, but nevertheless should be done. And our colleagues that we all know in other parts of the world that emanate from Africa or are working in Africa, that we should probably get more organized. From an attribution side, I understand, I remember the talk you gave in January, Francois, about the storm in Durban, and you were speaking about how the president made this statement that it's attributed to climate change, and you unpacked that a little bit. And I understand the need for that from a policy and strategic point of view. I also understand that in terms of costs. What's the phrase? Loss and damage assessments in terms of claiming money back from the impacts of climate change. That I understand. But at some point, I want to ask, isn't it irrelevant whether or not an extreme event is attributable to climate change? I mean, in the big picture, yeah, we can see there are lots more of them, they're more intense, they're more frequent, whatever they are. At what point when does it become irrelevant? At some point it should become irrelevant, because what we actually have to deal with are the impacts of those extremes. So that's going to be my final comment, and then you might want to respond to that, and then I'm going to ask for hands.
It will be highly relevant if loss and damage payouts depends on proving that the event was made more intense by climate change, and that will be discussed again at COP28 next month. So the other aspect is there's much to learn about how climate change is changing weather systems from these modern studies. It's also about improving our understanding of climate change. You're also correct. It's no longer a surprise that they are all being intensified to some extent by climate change.
About the climate, the mechanisms, also critical. So attribution in terms of trying to understand why these things happen is important for us to understand climate better, and we see lots of gaps. So more of this on Wednesday about extreme events. Let's take the floor. Anyone got a comment on either of these two streams, on collaboration within Africa and or the global South internationally, and or on attribution? Yes, good. Please say something controversial.
I'll try my best. Maybe I'm the best person for that. Dr. Warren Barrett, sorry, I'm putting you on the spot here. So he told me this morning that he was talking to some German colleagues, and they had some instruments stationed at Sutherland, and now they're taking it out of Africa because there was just no one in Africa willing to collaborate and to work on the data. And I think personally, I also organized some experiments for the Germans in South Africa, and it's just difficult finding people actually using the data. And I think that so if we're talking about collaboration with a global market, then I'm not sure how to proceed, but I think maybe start by talking to the people who already invested here.
Thoughts? Others in the room? Comments on this please.
Thank you for the opportunity. Arthur from GCR. I just have one question that I was just thinking when you're talking about attribution. You know, it seems like it's a new frontier that basically needs to be explored. In looking at the complexities when you're looking at climate system, you know, to really tie it down to say this is attributable to climate change, when there's so many other aspects that could be contributing to whatever impact that could be seen, right? I was thinking like usually the cause effect kind of like approach, you know, usually the dilemma that usually may be given in the health studies, or we are saying this causes this. And if it is causing that, to what degree is that contributing to what you see? So is there any thought around how that is being addressed, or maybe with attribution studies, because the climate system is so complex, there's so many things that are involved. So I was just thinking maybe what are your thoughts regarding that as well? Thanks.
Let's go to Jessica, and then we'll go back to the panel. We've only got about 5 to 10 minutes left, so let's try and get a few in.
Jessica from the GCI. I just wanted to ask the panel, given your reflections on this conference, how do you see SASAS playing a role in maybe filling these gaps that you've mentioned, or leading some kind of change in the next few years, or what do you think SASAS's role should be?
Yeah, I'm going to take comments from the panel, and then I'm going to ask them a final question. So let's see. Who wants to go first? Start you.
Not an attribution expert. I think your question is very relevant and very difficult to answer. But attribution activities, we would be better off with an attempt to undertake attribution activities than otherwise. You know, as complex as the climate system is, there's a lot of value in doing this.
So I don't have any comments on the attribution aspect, but on the collaborations, of course, I don't know the specifics of these collaborations, but you know, I think this is something we've been thinking about for a long time, is the nature of collaboration as well. And I did see, well, of course, it's not perfect. I did also see the shift that the other Piotr and Francois noted as well. But you know, with that, we are small communities. And so collaborative efforts that are locally led and that help to fill in the gaps that we don't have, of course, but where we are equals within a collaboration are key. But I think one of the longer term goals of collaboration, or this African climate, whatever it is also to grow the fields in these countries. I also have, you know, an amazing scientist who is born in Africa, who wants to work here and can't find a job in this country because these fields are so small. And if we keep having just this transfer of like capacity building, but no long-term goals to making these fields larger, you know, it won't grow, and we won't have this local expertise. But I think we also have to realize there's not many of us. We're all overcommitted and we can't do everything. But collaborations can help to fill the gaps where we don't have them. But I still think this local led, you know, of the questions and those aspects, they have to have much more equal collaborations, which I think we are moving towards. I think but we have plenty of helicopter science. I don't know if we use that in the climate and air quality, we say that, right? They fly in, they do their science, and they fly out as well. So that is still going on. It's not as success. And what SASAS can do, you know, I've always kind of wondered, what is SASAS's role in just in talking about these aspects? Like, if we are the South African community, how do we then as a community relate to the Namibian community, or, you know, another country, the Nigerian community, the Kenyan community, even if they don't have a SASAS, you know, how do we start with that? Do we have a conference where we invite some people from different countries? I'm not really certain. I'd be interested to hear what people think as well.
So I just wanted to to bring an example of collaboration that's we experienced a couple of years ago. In 2000, there was a project called Safari 2000. I don't know if you remember this. It was actually, yeah, you should know about this. And so it was led from South Africa by Professor Harold Hannigan. And he said like this, you know, if you guys, Americans from NASA or whatever, want to work with us, come and work here. Come and work with our institute, in our institute, with our tools, with our people, and build up capacity here. Don't go there. There is no sample taken, there is not a single sample taken out of African soil and analyzed soil, and analyzed in the United States. We come and do all these things here. If there is no equipment in the lab, bring this equipment to do this in the lab. Okay? And that sort of didn't work entirely. It didn't work 100%. There was still sort of, you know, they of course, you know, they would bring the whatever pipelines and clients and like that, you know. But you know, there was a right rhetoric, and there was a quite a strong push towards this. And I think that's what we should start thinking about. You know, being more sort of radical in how we get involved in those European or American funded projects, and how we set the boundaries. And it depends on us, because ultimately we participate in those different projects, and you know, we have to sort of be more assertive and be more stronger position in these projects and how we manage the relation.
On that, they wrote, Bob Swapp and Harold wrote a science diplomacy paper that is just brilliant. It outlines the different types of collaboration and how Safari tried, you know, to be the transformative and not the exploitative or otherwise. So if you're interested in scientific collaboration, science diplomacy is really interesting.
After your question, I'll start with that. This was also discussed heavily at the conference. So one should also distinguish between attribution when it comes to the weather event and the actual impacts that it caused. For example, in the case of the Durban flood, was it climate change that made the storm so much more intense? Or are the damages attributable to the city of eThekwini not enforcing its own zoning regulations? These are very tough questions to ask, but you are right. It's complex. And in terms of us as SASAS, and Jessica, your question, that's a complex one. I'll just say something very specific I think we can do. Now, our previous president of some years ago, Mattia Raul, that we fought off this morning, he always said SASAS does three things. It has a web page, it has a newsletter, and it has a conference. That's it. Now the newsletter has died, of course. Nobody reads newsletters anymore. It's gone. The new council is reviving the web page. I think we still have a web page. But the biggest thing that has always defined this society is this conference. That's what makes SASAS, it's the conference. And it's a wonderful get-together we have every year. But it's maybe also one of our best methods as a community to reach out to colleagues in Africa and in the global north every year. Now, this year, you may have noticed we have some international colleagues who have joined us from Jamstack and from the UK Met Office at least. There may be more colleagues that I haven't yet seen. We appreciate them being here. But we can make a more coordinated effort to get international buy-in to the SASAS conference every year. Maybe every 5 years with some sponsorship from, say, a bank. We should go into Africa. Why don't we have a conference in Windhoek? If we have sponsorship and we can all go, right? We all want to go. But the conference is what we should use as a first step to increase our own visibility and to talk to the international colleagues and the African colleagues about what is important for us.
I have to finish off, unfortunately. I'm going to have the last word. And I just wanted to say, when you were talking now, I'm thinking of the SANCOR model. I don't know if any of you are familiar with SANCOR, South African National Association for Coastal and Oceanographic Research. They have an NRF-funded post, and they have membership from Southern Africa and have conferences outside of the country. So it's maybe a model to look at. And I also think there's a lot more, you could get more organized and do more than those three things, unquestionably. So perhaps that's something to be spoken about. I was going to say something else controversial, but I can't remember what it is now. So look, I mean, I guess I'm going to ask you to finish this with literally one sentence each. Okay. And the question I'm going to ask you to answer is, did this conference shift the needle, this conference in Kigali? Did it shift the needle, at least for you? And if so, in what way? And if it didn't, that's also okay. Who wants to start? Let's start this side this time.
Yeah, there's immense urgency. Another message of the conference is the urgency for climate action, both in terms of climate science informing adaptation and mitigation to still avoid some of the worst damages. So I think the climate science community is more consolidated than it has ever been. And I think there's a lot of goodwill to better include the global South scientists in international climate science. So we must make use of this momentum that we've seen at the conference. And right, okay. So yeah.
So I hope it wasn't the conference that shifted the needle. But I hope that there are forces behind the shifting the needle that we've seen at the conference in this way. I think that so that I think the conference was a manifestation of how the world is changing around climate science and the projections and understanding contribution to climate science to society.
Yeah, I don't know. I don't know necessarily. And I think it'll be interesting to see, I mean, the outcome, they're supposed to be a Rwandan statement, right? Of this, statements can help, statements can do nothing, but they can be a rallying cry as well. So I think it's to be determined. Right?
For me, I think it was good because it's the one opportunity that we haven't had in the last 10 years for science into the COP discussion. So for me, that.
So we have to end there. Thanks very much to our panel. What about them? Oh, I see. It was mentioned because you were there, right? Okay, good. I remember the controversial thing I wanted to say, and that was that I've been talking to Francois and a couple of other people who may have been in this room about the idea of developing a climate research strategy. Repeat the terms, not climate change, climate research strategy for the country. Maybe that's something that SASAS should be championing, but we'll discuss that at another time. Okay, so we're going to end there and then hand over to Jessica. Thanks very much.
Okay, so we are running a bit late. We'll finish at closer to 5. So we've got our last session of the day, which is on water security and drought. And I'd like to invite author Nafisa, for his first talk on climate change, land use, surface water nexus in the Northern Limpopo Basin.
Good afternoon. Good afternoon. Oh, my presentation is not on. Okay. Okay, thank you for the opportunity to present. I'll just run you down part of this work that we did in the Northern Limpopo as part of my PhD study. Climate change, land use, land cover, and surface water nexus. It's kind of like a climate change impact study, but incorporating also landscape change. We try to attempt to bring all this thing, Professor Engelbrecht and Professor Stefan Grab. So this is my layout of my presentation on the introduction to the conclusion. Right, basically, people have been keen so much on sustainable development goal number 6, which is water, availing clean water and sanitation. But most interestingly for us, is the issue of
availing clean water, to communities. With the projections that are there, that approximately 63% of the 8 billion global population being in water-stressed regions, including sub-Saharan Africa, by 2025, it has become more urgent now to really zoom into the issue of water security, try to come up with pragmatic, scientific information to guide decision makers on how to avert the imminent impacts related to ensuring availability of clean water. So one other aspect that is there is of keen interest, basically graphs like this. This is basically from the UN DESA, basically with increased, projected population growth and sub-Saharan Africa, they see that where the anticipation is that population growth is going to continue exploding despite other regions basically tipping off and maybe populations becoming more stable. So with this basically comes the challenge of water stress, water wars. This infographic basically from World Matters 2022, 700 million people being displaced because of extreme water scarcity by 2030, 72% of all water withdrawals for irrigation because to feed more people. Basically, all this paints a backdrop of the dire need for us to basically understand what could be the likely future scenarios of water availability, water wars. Someone was already muting or talking about the possibility of water wars, freshwater resources that are being against the increasing demand. Classical examples, you've got Ethiopia right now building the Renaissance Dam, and Egypt is already crying foul, all those dynamics that are there. But basically, can we better understand what could be the likely impacts of a changing climate? And not only that, but also try to incorporate if the landscape changes as well, because that's another factor that tends to influence or exacerbate water availability issues. So in that context, the study that we did basically follows a nexus approach where we tried to look at historical and future, try to project future land use scenarios using a geospatial approach. Then from there, we try to look at future climate, past and future climate scenarios. And then we try to use the outputs from these to force a hydrological model, a semi-distributed physical hydrological model, as you see in the upcoming slides, so that we can maybe appreciate future surface water resource scenarios. And the key question that we're trying to answer is, how does climate change and land use then cover impact surface water agriculture conditions? We're basically looking at stream discharge within the strategic catchment that I'm going to show you now. This is basically the Northern Limpopo Basin, part of the Northern Limpopo Basin here in South Africa. And the Northern Limpopo Basin stretches all the way into Zimbabwe. And the area that we looked at, this small sub-catchment called the Upper Mzingwane sub-catchment. And this place is very strategic in that it generates 9.3% of the surface flow that goes into the Limpopo Basin. Just being small as it is, but it has got great significance. So, and also it houses 5 of the major supply dams that supply water, fresh water for the second largest city in Zimbabwe, which is Bulawayo, which was once the economic hub of the country. So basically this is the catchment and the dams and the elevation basically filtered in the drainage there, as you can see. So basically the study follows, we followed five steps without, thank you, Jess. I will not labor much on the details, but there are basic 5 steps. Maybe you can, if you are interested, you can come there, can reflect a little more. Step number 1 was basically the land use land cover analysis, looking at historical trends in land cover scenarios using remotely sensed data, Landsat, and then we modeled future land cover scenarios up to 2038 using Markov chain modeler. From there, step number 2, we looked at the climatic data, right? We looked at the climatic data, climate scenarios we use CCAM data, right? From the VIS DCI, we try to look at the different climatologies from the different future scenarios and the baseline with the baseline period from 1961 to 1990. Then we tried basically to look at historical, we had in situ data from climate stations around within and around the catchment, which we used to try to validate the baseline period. That was step number 3. Then finally, after validation, we're satisfied with the results. Then we forced a hydrological model, which is basically called the HEC-GEO HMS. We can talk about that. We parameterized it, calibrated it, and we forced it with the different data sets and the future land use scenarios to see what could be the outcome. So here are the results. Findings for the land use land cover scenarios. This is the historical land use land cover scenarios. And these are the future land use land cover scenarios that we modeled and predicted for up to 2038. What we find basically is continued deforestation historically, and we see that also projecting into the future. So if there's continued deforestation or loss of woodland cover within the catchment. With regards to future projections, that's a sample of some of the outputs in terms of precipitation. And what we see here, future temperature climatologies for the different ensemble members. But basically what we see from here is generally drier and warmer conditions persisting into the future within this catchment. So from there, we forced the hydrological model. These are the main steps basically that we use to force the hydrological model from our projected future scenarios and our land use land cover scenarios. So we parameterize the model. Basically, this is how it works around when we're parameterizing the model and calibrating and setting it up, then doing the trial runs. Then they see the simulated runoff and precipitation and simulated discharge there from historical, then we project into the future. And those part of the validation results. I'll not dwell on that because of my time. Then this is basically what we finally came up with, what we saw. We give an example of some of the outputs from the 4 of the ensemble members. These are the discharge from stream discharge from the different models. What we're basically seeing is, this is basically near future into the distant future. What we are seeing basically overall declining, 1, 2, 3 are showing a declining trend with, of course, the exception of the CNR model, which was showing a slight increase in discharge. Maybe that could be attributed to another reason. That's an area of exploration that we need to look at. What we see now is the implication is this: with the reduced discharge, there's indications are possibilities of reduced surface water availability within this area, and that is consequential in a number of ways. So in conclusion, what we realized is there's been extensive deforestation. Thank you, Jess. Deforestation that is going to go into the long-term future, and progressively warming within the catchment area, and generally there's a decreasing annual total precipitation also, especially in the westernmost and southernmost extent of the area, and consequently we are seeing some magnitude discharge, reduced discharge in the main river systems within the area, and that is most likely to show or to result in water insecure futures in this catchment, and this can be very consequential, having knock-on socio-economic impacts. So there's still some aspects that we're trying to do, looking at the seasonality, then using cover scenarios, try to hold certain constant and try to do the trial runs again and see if we can further build on this. Otherwise, thank you for your attention.
Any questions?
Good afternoon. I'm not sure whether I'm going to end up with a question or it's just going to be some statements.
Please unmute you.
Okay. Now, Africa is largely an agricultural continent, which is heavily dependent on Nile River. If, I'm not sure whether I'm going to end up with a question or it's just going to be some statements. Okay. Now, Africa is largely an agricultural continent, which is heavily dependent on Nile River. If, I'm not sure whether I'm going to end up with a question or it's just going to be some statements. I think it's the evening and after long days. So it was after a few years ago, it was predicted that the Nile River.
Maybe put it back.
Yeah, sorry about that. So a few years ago, it was predicted that by 2050, I'm not sure if my information is absolutely correct, that the Nile River would be reduced in its flow by almost 50%. Whether that is true or not, absolutely. There's an added dilemma of the Egypt and Ethiopia that we spoke about. You know, so now, because it is largely an agricultural, pastoral, continent, largely dependent or heavily dependent on the Nile River, the most vulnerable communities are the poorest of them all. And the consequences, if these predictions are correct, can be devastating. Now, let's assume whatever I said now is 80%, 90% correct. The issue is, having said what we've said or known, whether it's true or not, I'm talking about risk management. What contingency plans should we develop to ensure that this estimated predictions, if I have to put it that way, don't materialize, or that our vulnerable communities are taken care of at least in some way, if not. So maybe it's food for thought from an agricultural perspective. But thank you very much.
Thank you for that. Is, I guess, a common food for thought for all of us, because the issue of water security is quite pertinent. And as we are discussing all the models and outputs, the climate, the impact studies, how all these basically filter down to the most vulnerable societies. The most important way we move away from we move out of our comfort zone as scientists and into that space where we can say, then what? What does it mean? What all this that we're doing, what does it mean to address the real problem that people are facing? But that's for all of us. And yeah. Thanks, Jess.
Right, next up is Anna Bradley, talking about exploring historic drought heat wave compound events in South Africa. No. Back across. Yeah. It was that. Oh. So yes. Hello, my name's Anna. I work at the I work at the Met Office, and I'm part of the WCSSP program in South Africa, which is the Weather and Climate Science Services Partnership. And today I'm going to be talking to you about exploring historic drought heatwave compound events in South Africa. It's a very quick introduction as to what are compound events. So compound events are combinations of interacting physical processes that occur across numerous spatial and temporal scales and contribute to risk. And they were first mentioned in the IPCC special report on climate extremes in 2012. So why are they important? Well, many climate-related disasters have often been attributed to compound events, and the impacts associated with them can be greater than those associated with the isolated hazards. So in this case, if you looked at drought and heat waves independently. And many traditional risk assessments typically consider these events quite separately, even though which can lead to an underestimation of the potential hazard, the potential impact associated with the compound hazard. So a very quick example of the compound events that I've been looking at. So these are called multivariate. So in a sense, it's when you get multiple hazards happening in the same place at the same time. And you can see kind of the process through that there, which then result in an impact. And the main reason that as a climate scientist, I'm interested in this is because climate change is likely to have an effect on any part of this process and therefore on the overall impact. So my methodology is that I've been using the maximum daily temperature and the standardized precipitation index to have a look at these compound drought heatwave events and the ERA 5 data set from 1980 to 2019. So I've been looking at warm season compound drought heatwave events and have used the threshold, as you can see on the slides, to find this. And a compound drought heatwave event is defined as a heatwave that occurs during a month in drought conditions. And the impacts of these can be significant, especially for health, agriculture, and ecology. So these are my very initial results. I'm still working on these through the partnership, but yes, so these are some of them here. So firstly, the total numbers from 1980 to 2019. So you can see there the heatwave days of drought months and then the compound drought heatwave days. And as you can see, the first thing to point out is that compound drought heatwave days have occurred in South Africa using the methodology I showed from 1980 to 2019. And it kind of more closely follows the pattern of these heatwave days. But you have obviously also got the influence of the drought months because it's not directly the same. And then you've got the percentage change. So I've just split the time series in half here. And as you can see, there's some quite distinct patterns. So for heatwave days, you've got, for the majority of South Africa, you've got this increase, but there are also pockets where you've seen a decrease in the early 21st century compared to the late 20th. Whereas drought months, you've kind of got a lot, there's like a smaller area, but there's been a large increase in that area. And then for CDH days, your compound drought heatwave days, it follows a pattern similar to heatwave days again, but not directly. And that will be the influence of the interaction between your drought and heatwave days. And then this is the Mann-Kendall trend test. So I've done this across the whole time series for each grid square, and this is showing if there's a statistically significant trend in these events. So again, for heatwave days, you've kind of got these pockets around South Africa. Drought, it's more concentrated towards the northeast. And your compound drought heatwave days, again, is a kind of take elements of both of them. So what I'm showing from this is although your compound drought and heatwave days does have similarities to your heatwave days and your drought months, the areas where you're seeing these changes are sometimes areas that you wouldn't expect, that haven't seen kind of that statistically significant increase in heatwave or drought, and therefore may kind of have the consequences of these may be unexpected if you think about drought and heatwave separately. So now I've got two quick case studies where I've compared Johannesburg and to Cape Town's, just two case studies. So as you can see, so you've got heatwave days at the top, drought months at the bottom, in the middle, and then your compound drought heatwave days at the bottom. And you are getting these kind of these peak events within the data set. Thank you. And you've got some key years there. Coming into, yes, so these are some key years here that I've picked out where you've got these compound drought heatwave days, and where the peaks are, you can see actually they're increasing in height as the data set goes on. So I've picked those out just to have a look at the interaction between them. And most of the time when you've got these compound drought heatwave days, it's because you've got kind of a larger you've got a large drought and heatwave, but there are some instances where one of them is kind of relatively, it would not necessarily be described as extreme, but is leading to these compound drought heatwave days because there's an extreme in the other. And again, so this is now the monthly average across the whole time series. And again, your months where you've got your most compound drought heatwave days does tend to follow those of your heatwave days and drought months individually.
with December having that high. However, it's important. So if we look at December, for example, your actual heat wave days is, you've got months where they're higher. In fact, October, November, and January are higher than that. But actually, it's your highest month for your compound drought heat wave. So again, it's think about the timing of these and how they may lead to unexpected impacts because you've got this compound nature that occurs not necessarily when you have an extreme in one of the variables individually. And that's just showing the statistical test results. So you've got an increasing trend in all of those results, which shows that there may be a link that I need to explore more clearly. But yeah, you've got this increasing trend as well as these peaks in the data. And then this is for Cape Town. So as well, I've done a similar thing and picked out some key years. As you can see, the pattern is quite different, as would be expected. And this is a relationship again between the different variables. So again, it's mostly where you've got that increase in both, that you're seeing the increase in compound drought heat wave days. Although again, interestingly for the monthly analysis, the month of March in particular stood out because actually for heat wave days and drought months compared to other months, they're relatively low for those individually, but actually for the CDH days compared to other months, it's one of the highest. So you could have this unexpected impact later on in the warm season that may be unexpected because of the nature of the combination of both of those events. For Cape Town, there isn't a statistically significant increase in these events over this data set just for the warm season. So these are my conclusions, is that compound drought heatwave events have occurred over South Africa from 1980 to 2019. There's quite a lot of variation in this change, with some areas experiencing these statistically significant increases and others not. And the spatial variation in CDH change is similar to that of heat waves. Although there are differences suggesting that some of these changes are associated not with an increase in both drought and heat wave, but more with a change in the timings of them. And then that leads to the increase. So that's also something quite important to think about, because those trends could be hidden if you've just got this change in the overlap. And then also, yes, there I've mentioned as well, CDH events do not necessarily occur during the months of the greatest number of individual drought heat wave events. And this is quite important when you're thinking about adaptation, because if they are occurring during months where you wouldn't usually expect them, then the measures may not be in place to kind of cope with those. And this is some of my future work. So I'm hoping to rerun the analysis using different definitions of heat wave and drought events, because obviously I want to see what influence this has on my analysis. So this is from another paper that looked at these over the Mediterranean. So that's using many different definitions. Thank you. And then also investigate using the wet bulb globe temperature, which has been shown to have quite a lot of close links through to heat stress. So if we're linking this back to a health perspective, what difference does this have to the results than using just the maximum daily temperature? And the wet bulb globe temperature also includes things like humidity, wind speed, and surface pressure to help look at those. And then also explore what is causing these events. Yes, so if you have any more questions, please do get in contact. This is very much the beginning of an ongoing piece of work that we're doing through this partnership. So yeah, it'd be great to hear. So thank you very much.
Mine is more of a idea, and that is, we know that diarrheal diseases are optimal conditions for diarrheal diseases hot and dry. So it'd be really interesting to look at these relative to our incidence data, because we haven't looked at that in particular. We've looked at other relationships or individual relationships with precipitation and with temperature, but not on that. That's one. And then I just wanted to emphasize the point you made about the idea that if something is aseasonal, it's an extreme event, even if it doesn't meet the criterion for an extreme event for that period of time it is. And I think that's critical as well to understand. Yeah, those are my 2 comments. Thanks.
Thank you.
I'm wondering whether it's meaningful to look at short-term drought in the dry season in Cape Town and in general in the southwestern parts of the country, and whether it might not be more meaningful to consider longer-term drought and its interaction with heat waves in summer, because I saw you had a decrease in drought months around Cape Town, despite the fact that we've had severe recent droughts, but presumably that's because they've occurred primarily because of insufficient winter semester or cooled season rainfall. Thank you.
Yeah, thank you very much. And that's something I definitely want to look at, is the SPIs from the 3 months is often considered, I think, meteorological drought. So that was where I started. But yeah, running it all the way up to 48 months, which I think is more linked through to things like agriculture, that kind of thing. So yeah, there's definitely, I think it depends which sector you're looking at in terms of which SPI. Yeah, definitely want to look at the different SPIs and then all those different definitions as well that I had later on, how to define them. So yeah, thank you very much. Thank you very much.
Right, so then the last talk of today is Nomvula Mpogo's extreme rainfall events in southeastern Africa during summer. Ah.
Yeah. Thanks very much. Yeah, cool. Technically, I've got half an hour, given it's the last talk of the day. Straight. Perfect. There we go. Good evening. Good evening. Good afternoon, everyone. I was saying this morning to some of the students that the worst time to give a presentation is right at the end of the day because no one pays attention. And now I found out it's even worse that you can give a presentation and it's not even your talk. So we'll see how this goes. This work forms part of Nomvula's Masters. It's looking at extreme rainfall events over southeastern Africa during the summer months. It's not brought about due to the extreme flood event that took place last year. It's in fact brought about by what's happening to the water levels in the northeastern parts of KwaZulu-Natal. This is Lake Sabaya. And what you're looking at are photos taken by Sue van Rensburg. Top left is 2015, bottom left is 2019. You can see those lake levels dropping. Then you've got satellite images, top right corner from 1978 to 2019. And you can see that something drastically is happening in Lake Sabaya. And this is quite a big problem because there are lots of communities that rely quite heavily on this lake. These are small subsistence agricultural communities. There's no river that flows into this lake, so there's still unclear what controls the lake levels. But we got given an emergency alert of what is happening. And the funny part was, is the local communities, they think that this is all linked to extreme events. They say the lake levels are determined by extreme rainfall, not your total rainfall over the summer months, but your extreme rainfall events. So we thought, well, let's have a look into it. Now we've gone to the end. Sorry, not technology. No, I don't know what I should have like this sometimes. Here we go. Right, so where we're talking about is right in the northeastern part. I don't have a pointer here, unfortunately. There we go. Just a second on. It's quite a ecological sensitive region. It occurs between the tropical ecosystems and subtropical ecosystems. And along the plains, along the eastern coast is the one of the UNESCO World Heritage Sites, which is the Isimangaliso Wetland Park. And apart from tourism, which is its dominant form of income for the region, it's a lot of subsistence farming, and then also fishing activities also control the region. And I know if Mathieu was here, he would raise his hand and talk about the Gallus current. So of course, I'm just going to do it. And as you can see, right attached close to the shore there is the warmer Gallus current. So that's our region that we are looking at. it was quite interesting when we were hearing about the importance of extreme rainfall events. The question became, well, okay, well, let's have a quick preliminary look. This is work from Diedrich's Morake on the left-hand side, which is a mesoscale convector system. So the top left-hand panel is cloud top temperature. So that shows you a nice mesoscale convector system over the East Coast. The top right-hand panel is rainfall produced by the system. The bottom left-hand panel is the late summer rainfall total. The bottom right panel is the contribution of that one system to regional rainfall. And I think that MCS produced about 50% of the seasonal rainfall. That's just from one event and one night. And then, of course, we all know what happened last year in Durban. So this gives us extra motivation for this sort of study. And what we are interested in is looking at extreme rainfall events from 1984 along the east coast of South Africa. I'm just for this talk going to focus on the northern parts. We have done the southern parts too, but just for this, it's going to be the northern parts. And then we want to look at internal variability of these events, and then also some of the mechanisms or some of the drivers behind their variability. So the first part is actually coming up with an extreme event database. So we use the CHIRPS rainfall data set for this from 1984 to 2019. So this work was done pre the Natal flood last year. And unfortunately, we finished only during the summer months. So we did October through to March. We didn't do April. So that is a bit of a flag. And then what we wanted to do is get the intensity of these extreme events. And the way to do that is you're looking at just not the rainfall produced, but also its aerial extent. So we adapted a method by Ramos et al. That used it for Europe, which where you look at the extreme events on a grid scale base, and then you look over the entire domain. So just to give you an example, the figure in the middle there, that's just one particular rainfall event. And what you do is you isolate the rainfall from that event. You then go onto the grid scale and work out how significant that rainfall was. And then what you end up with is with a table where you've worked out the aerial extent of that event. So what we did for the 36 years, I think it was, is calculate the top 50 extreme rainfall events. The second component to the work was looking at, well, what resulted in this in the rainfall? What was the dominant weather system that produced the rainfall? We used ERA5, GridSat, SAWS, Neil Hart's cloud band tracking, and then IB tracks. And that's to look at sort of cutoff lows, tropical weather systems, mesoscale convector systems, and tropical cyclones. It sounds very easy, but often these systems are integrated and it's very hard to identify between a cloud band and a mesoscale convector system. So this took a lot of the painstaking work by Nambula to get that right. This figure here just shows the top 20 events. It's going to be very hard to read it because it's one of those stupid little panels. But the top left two systems are the same event, which is Des Moines back in 1984. That's ranked system number 1 at the top and ranked system number 20 down the bottom right. And what you have from this summary from rainfall is that tropical lows accounts for 19 out of the top 50 systems. MCSs were 10, but only 2 of those MCSs were in the top 20. Cutoff lows were the interesting one. We all know very much about a lot about cutoff lows given the extent of the damage they've done recently. 9 of the top 50 are by cutoff lows, and most of these, 8 of those 9 are in the top 20. So cutoff lows are one of the biggest producers. And then cloud bands are the other one, where there's 8 out of the top 50, but only 3 of them are in the top 20. And you get quite a bit of spatial variation between the different types of systems. So cloud bands and cutoff lows generally have a large spatial variation, while mesoscale convector systems and some of the tropical lows are very coastal related. The top left panel is the seasonal cycle of the extreme events along with rainfall. So the blue bars is your seasonal rainfall. Your black bars are your top 50 extreme events. And what you'll see is you'll see a peak in the rainfall in December, January, which is, I said blue bars, but then you can see from your extreme events, they actually peak in your late summer months. So January, February, March. This is purely because you're having more tropical systems that are producing extreme rainfall events. And then if we look at the bottom bars, what you have there is they color coded to the different events, just in case it's hard to read the text. Black is cloud bands, red is cutoff lows, blue is mesoscale convector systems, green is tropical storm or tropical lows, and then purple is tropical storms. You can see cutoff lows very much in the early parts of the summer months, and then your tropical systems, which are very much your JFM part of the period. This is expected given that there's papers such as Deirdre's work looking at how Cape is largest during the late summer months versus the early summer months. So we kind of expect that your tropical systems do dominate during JFM and not OND. I don't know what happens to the text there. So sorry, a few panels on here. Your top panel is rainfall anomalies. Your second panel is rain days of 10 millimeters or more, or 25 millimeters or more. Your panel, which has got the purple arrow on, that is your extreme events and when they occur. And the bottom panel is ENSO. And what the takeaway from this is a couple of things. One, in OND, most of the extreme events took part in the early part of the record and very little took part in the late part of the record, which is going to be different, which I'll show you now from JFM. Other components is that ENSO correlates relatively well with extreme rainfall events, but it's not that strong. Where it's a lot stronger is with your 10 millimeters and the 25 millimeters of rainfall, which is actually very interesting because this is one part of South Africa where your ENSO signal is actually very clear. Yeah. For JFM, the takeaways I want you to look at here is one thing, which is the very dry parts of the last decade, which is lined up. And you remember those pictures of the lake levels going down. This is quite important. Your JFM has been very dry in that part of Southern Africa. The other thing that's very important to take away is that your extreme events here actually spread quite evenly across the entire period. But more importantly is that you're getting dry late summer periods, but they would be a lot worse if you didn't have those extreme events. If those extreme events didn't occur, I mean, it's one or two extreme events, it'll be a lot less significant. That's why it's very important with these extreme events to take notice of them. The last slide I also want to show you here, for lack of a better term, is just we can call them bubble plots. And what's this showing is the relationship between El Nino, the number of rain days greater than 10 millimeters, temperature, and also then the number of dry spells. And what you can see is what you expect for La Nina, which is the far right panel. Generally, you have a lot of rainfall, which is the big bubbles. You have lots of days with greater than 10 millimeters, which is the x-axis, and your y-axis is dry spells. So if you go now to the complete other side, which is El Nino, you can see you've got small little bubbles, i.e. a little bit of rainfall. Most of the bubbles are dark, which means it's a lot of hot days. And then what you also have, you do have one or two outliers. And I don't have a pointer, but 2011 for La Nina is down the bottom right here in the panel. And then there's also, I think it was 2008, December, January, February, where you have a sort of a contrasting signal. But for the most part, ENSO is quite common, or the impact of ENSO is quite common across this sort of domain. So that was just a sort of a glimpse of what we're trying to do for the region, is trying to explain to these communities with extreme events, saying, right, extreme events, they do contribute towards your seasonal totals. But what we are trying to understand is, okay, if it's not extreme events, if that's not the explanation for what's going on, what is it? And what we think is happening is you're starting to see drier late summers. You're having a decrease in extreme events in the early summers. And what this is resulting to is your overall seasonal totals are decreasing. You're also having hotter conditions. And that's what one of the primary concerns about lake level going down. But it's not the only thing. What we also found was that there's been a change in land use around the lake. And what they've done is they started producing a lot of eucalyptus trees in the region. And that is taking up a lot of water. So climate is only one side of the story. But what we do know is that the extreme event story, it does seem to hold, because we are seeing a decrease in these extreme events during the early summer. And that is tied into where we are seeing the decrease in the lake levels. But out of interest, just to sum up with regards to extreme events, I think mesoscale convector systems are severely overlooked in this region. And I think they can produce as much rainfall as your cutoff lows. And what you'll see is that 10 of the top 50 are mesoscale convector system related, cutoff lows are only 9. But yet, we haven't really done too much attention in the scientific community of these systems. And I think going forward, that is where we're going to start addressing a lot more, are these convector systems. All right, thanks very much. End of the day, it's the worst talk.
Thanks for that, Ross. I'm just curious about the relationship between having less extreme events from the study up to 2019, but as we are progressing forward, that potentially there could be more extreme events observed in this area. So I'm sort of curious, how do you think that there could be potentially some sort of decadal scale, which then again comes back to ENSO being a
correct.
So yeah, I was just wanted to hear your thoughts on that.
It's definitely one of the challenges in trying to communicate this sort of information, saying climate change could result in more extreme events. And some of the communities are going, yes, that's good for us because it means our lake level is going to go up. But at the same time, when you look at the sort of the early summer period, or extreme events are decreasing. It's not a significant decreasing trend, but there's evidence that they're not as many as they used to be. Are we seeing, for example, cut-off flows occurring more in the late summer months? So we still in future might get more, but it's OND that seems to tell the story. But again, it's how we communicate the information. The community saying that OND, the early summer is what we need to watch out for, but you could have more coming in the future. And yeah, the ENSO story is actually fascinating for that part. The one part of South Africa where ENSO signal was very consistent. Thanks all. Oh.
So he's going to talk about where South Africa is in terms of climate services and policy stuff. He starts at 9 o'clock, so please be on time. But tomorrow evening, we are going to have dinner at the Blue Peter Hotel in a long-established, well-known place in Cape Town. We are transporting those that asked for transport from here back here. We will leave straight after the session, or reasonably soon after the session, and go there and watch the sunset and then have dinner and come back. We can negotiate, I shouldn't be saying this, but because I was told we can't, but we can negotiate with the driver to potentially drop you back to where you want to be instead of coming back here and then. But I do have to take one more count of the menu. They asked me at the hotel to check to see who wants fish and who wants meat. Okay, so I need someone to help me count. Okay, so there's a delicious Cape fresh seafood dish or a delicious lamb chop, I think. Those are your options. Okay. So for those that are coming to dinner tomorrow night and are going to have fish, put up your hand high so I can count. Okay.
Just to be clear, this is going to stay here this whole week. As far as it looks like. Okay, perfect. On Wednesday, apparently, is a moving to a different building. They're moving to a different building.
Oh, okay.
Yeah.
Take that away with me.
Okay. But we will have it for the whole week, right?
Yes.
No, I'm talking about this end. Yeah, okay.
Yeah.
Yes, and you plug it in there.
Okay, that's fine.
From the
Oh, I see, I see. Is that what the issue was? I heard you messing around with that, then suddenly it disappeared.
Yeah.
I think. That. Stop. And I got that. Right. Let me see if there's somebody going back to UCC.
Look. Passing on the way out. Thank you. Another really good.
Tomorrow night we have a long day. I'm working home until we finish. We'll fly across the road in a minute.